All right, so I think we can go ahead and get it started. So first of all, welcome to the third annual summit of the Center for Responsible Machine Learning at UCSB. This year, we're gonna center our topic on AI and social good. So first of all, let me welcome Vice Chancellor of Research at UCSB, Distinguished Professor of Physics, Professor Joe Incadella, to give us a welcome speech. Thank you, Joe.
Yes, sure. Good morning, everyone. I'm very honored to be here to kick off this year's Center for Responsible Machine Learning Summit that will focus on AI and social good. We know that AI is changing our world. I've seen this firsthand in my own field of particle physics, where it really has made it possible for us to do things and uncover more than we had ever imagined in some cases. But it has also had some negative consequences, such as its involvement in the spread of misinformation and the creation of biases that continue to hurt specific populations. So the Center for Responsible Machine Learning is, I think, a great initiative that I hope will help address some of these things. It reflects our commitment at UCSB to advancing research in this area, but with a particular interest in addressing issues of fairness, bias, privacy, transparency, explainability, reproducibility, and accountability, for example, in the context of AI and machine learning algorithms. This requires a lot of interdisciplinary collaboration in many fields and a robust dialogue that spans academia and industry, civil society, and the policy world. The Center for Responsible Machine Learning has over 60 affiliated faculty members from 20 departments, and it has succeeded in engaging industry and government partners in serious conversations about the future of AI through these annual summits. Innovation through collaboration is something we're really known for here at Santa Barbara, and something we feel we do really very well. And we're very happy to help play a key role in making these critically important connections. This past year at Santa Barbara, Professors Timothy Sherwood and Sharon Tediga received the 2020 award for Inclusion Reach from Google for their proposal, Iterative Design of a Black Studies Research Computing Initiative through Flipped Research. This award will help establish collaboration between our Department of Computer Science and our Center for Black Studies Research. The collaboration will bring the power of computational science to underserved Black and Latino students on campus. Beyond the Center for Responsible Machine Learning, there is a vibrant community of scholars and researchers across the entire campus that is engaged in AI through the recently funded Mellechamp initiative in mind and machine intelligence, the Data Science Initiative, the Center for Information Technology and Society, and the Center for Energy Efficiency. We're seeing ever increasing funding opportunities for research in AI and machine learning, which continue to be areas that enjoy strong bipartisan support in Congress. At the federal level, this investment has leveraged new interagency and private-public partnership, such as the National AI Research Institutes, which are a partnership of NSF and the U.S. Department of Agriculture's National Institute of Food, Agriculture, and Agriculture, U.S. Department of Homeland Security, Google, Amazon, Intel, and Accenture, or the Fairness in Artificial Intelligence program, which is a partnership between the NSF and Amazon. We're optimistic that the new infrastructure bill will bring even more research funding into this important area, assuming it ever gets passed. I hope that today's summit will help researchers forge new collaborations and create new ideas that can be leveraged toward these opportunities, particularly in the important social areas that are being discussed today: AI and ethics, wildlife protection, social justice, security and privacy, public policy, and global development. Today, we'll be hearing from a number of experts who are examining how to use artificial intelligence and machine learning for social good. So I'd like to thank William Wang, director of the center, and its other leadership and staff for bringing this group together today. I'm looking forward to seeing today's discussions and seeing even more progress in the area of social good and artificial intelligence. Thank you for joining us for this important event.
Thank you, Joe. So I'll also try to be brief and just give you a quick highlight of today's program. So in just a second, I will introduce Professor Stuart Russell, and he will tell us about his recent work on human compatible AI. And in the morning, we have a session on AI ethics, social and global development, featuring 3 speakers, David Danks, Phebe Vayanos, Neha Kumar. And after that, we'll have an engaging panel centering the discussion on AI public policy, corporate and social responsibility. And we have Lisa Amini, Rayid, Ghani, Lorraine Kisselburgh, and Summer King joining us as the panelists. After the lunch, so we'll have an hour lunch break. After the lunch, in the afternoon, we'll have Professor Tuomas Sandholm to talk about his work on automated mechanism design. And last but not least, in the afternoon, we have a very intriguing session on AI and wildlife conservation, featuring Fang and our own Douglas McCauley and Professor Chandra Krintz as well. So that's a quick overview of today's program. You should be able to find all this information on our website, ml.ucsb.edu. And I want to give our special thanks to the sponsors for the CRML and also this year's summit. I want to thank AppFolio, Amazon Alexa, and also the Mellenchamp Mind and Machine Initiative, Machine Intelligence Initiative. Thank you, Duncan and Suzanne Mellenchamp, for your generous support. I want to thank the Center for Information Technology and Society for their co-sponsorship as well. And finally, I want to thank our CRML faculty members for making this possible. I want to thank co-director Yuxiang Wang and organizing committee co-chairs Laura Langen, Kayla Wang, and our advisors in organizing committee, Lynn Hawks, Steve Ramirez, Rob Duncan, Janice Taylor, Marcel Badet, and the DevCom team. Finally, I want to thank Chancellor Henry Yang, EVC David Marshall, our College of Engineering Interim Dean Trisha Pollack for their support of today's event. And let me begin by introducing our morning keynote speaker, Professor Stuart Russell. Professor Stuart Russell has a very distinguished career in research for many years, and specifically, he's right now professor of computer science at UC Berkeley. He's the holder of the Smith Zadeh Chair in Engineering, and he's the director of the Center for Human Compatible AI. He's a recipient of the Ichkai Computers and Thought Award. In this year, he also just received the OBE from Her Majesty the Queen. He is an honorary fellow at Oxford University and Andrew Carnegie Fellow, and also fellow of the AAAI, ACM, and AAAS. Many of you know him. I think is certainly, I think because of his book, which is the most widely used textbooks in AI that has been used in 1,500 universities in more than 135 countries. The artificial intelligence modern approach. Professor Stuart Russell has a lot of interests spanning over a wide range of topics in artificial intelligence. And recently I got to know that he's been developing a global seismic monitoring system for better implementing and understanding the nuclear test ban treaty. And he's also been actively involved in working on to ban the lethal autonomous weapons. So very influential work along this line. And with all that, I want to turn the floor to Stuart. So welcome.
Thank you very much, William, and Vice Chancellor Incandela for introducing me and this event. I'm very happy to be speaking. I wish I could be at the Santa Barbara campus in person, a lovely place to spend time. So let me share my screen. Okay, William, you're going to have to allow me to share my screen.
Yes, you should be able to share screen. Let's see.
Okay, that's good. Okay. Okay, so I'm going to talk about AI, obviously. So I want to get everyone on the same page about what that is. And obviously it means making intelligent machines. And what that means for most of the history of AI has been the following, which I call the standard model, borrowing a phrase from physics, that machines are intelligent to the extent that their actions can be expected to achieve their objectives. And within that standard model, we've done a lot of very impressive things, in my opinion. Some of the earliest work was done on problem-solving search, and in that case, the objective is a cost function that measures the quality of solutions and a goal that defines what it means to be a solution. In games, game-playing algorithms, we define what it means to win the game. In planning systems, we define the goal that the plan is supposed to achieve, and then possibly a cost function as well. In reinforcement learning, we define a reward function, and we write algorithms that are designed to maximize the discounted long-term sum of rewards, and so on. So in all these areas, we instantiate the standard model in a particular way, and then we write algorithms that are good at achieving the objectives that we state. And I want to be completely clear about what is the goal of AI. And this has been true since the beginning, since it was very clearly defined in Alan Turing's paper in 1950, in the description for the Dartmouth summer workshop written in late 1955, that the goal is general purpose AI, meaning AI systems that are capable of quickly learning to perform at a high level in any task environment where humans can perform successfully, and probably many more task environments besides, because machines obviously have lots of physical and computational advantages over humans. And so the question I'm mainly going to be concerned with in today's talk is, what if we succeed? And we can talk about all kinds of things. Some people imagine sort of, science fiction-like consequences, extending the human lifespan indefinitely, designing faster than light travel, and so on. But I think if we're being conservative and realistic, we would say that what you can do with general purpose AI is to deliver what we already know how to deliver, right? Globally, we're able to deliver a reasonably high standard of living for about 10 or 15% of the Earth's population. And what we would like to do is simply make sure that that's available to everyone. So not extending lifespan and so on, but just delivering a nice, respectable middle-class standard of living that gives people physical security and well-being, knowledge, education, freedom, and so on. And that constitutes about a 10-fold increase in the GDP of the world. And if you calculate the net present value of that, it comes to about $13.5 quadrillion. So that's a very conservative and very rough ballpark estimate for the cash value of creating general purpose AI. And that's one way of thinking about why there's so much excitement when progress in AI occurs. And it also says that the momentum towards general purpose AI is likely to be very, very difficult to divert, and one might call it unstoppable. Now, we could also do some things better than we're currently doing them. We could probably have much better individualized precision health. We could have much better individualized precision education. One commonly quoted statistic is that individual high quality human tutoring is about 3 times as effective as typical classroom teaching. So that means that most children could be brought to college level achievement by the age of 10 or 11. And so that would be a very significant, I assume, a very significant benefit to the human race in general. And we're already seeing, as Vice Chancellor Candela mentioned, the use of AI for accelerating science and possibly enabling new kinds of science that are very difficult for the unaided human brain. Now, Alan Turing also thought about what happens if we succeed. And what did Alan Turing say about it? He said, it seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. So he offers no mitigation, no solution. Really, you get a sense of resignation, that he understands that the box that he's opening is going to lead to the loss of control for the human race over its own future. So I'm going to talk about why this might happen and whether it's possible to avoid it. Turing obviously thinks it's not possible to avoid it. I think it may be. Now, if we fast forward from Turing's talk, which was in 1951, to the present, we're seeing a lot of the things that AI researchers have dreamed about starting to come true. The self-driving car, programs capable of beating world champions at Go and chess and other games, and learning to do so basically in a single day. As William mentioned, we're also able to do useful things like effective monitoring for the nuclear test ban treaty. This is an image from space of the region of North Korea where a nuclear explosion took place in 2013. And NetVisa is a system that we developed. And it's essentially a giant probabilistic reasoning engine that takes evidence from the entire planet and produces the most likely explanation for the evidence in terms of seismic events that may have taken place. And here's the location that we estimated within about 600 meters of the tunnel entrance that was later discovered in satellite images. But we're also able to use AI for things that we probably shouldn't be using AI for, such as deciding to kill people. And last year in Libya, a Turkish drone called the Kargu was apparently used in fully autonomous mode to by one side of the conflict in Libya to attack the other side. And Israel claims that it's been using autonomous drones to carry out attacks in Gaza. And this is a very serious development. And any computer scientist knows that if a computer can do something once, then simply more or less by wrapping it in a for loop, as we call it, you can say for I equals 1 to 1,000,000 do, and then it does the same thing 1,000,000 times. And so we can take autonomous weapons like this because they require no human supervision and turn them into weapons of mass destruction simply by scaling up the amount of hardware, the number of lethal weapons that we deploy. You create a weapon of mass destruction. So this is highly undesirable development. Now, the question, what if we succeed, is asking, sort of making the assumption that we are going to succeed, and then what's the consequence of that? I'm not necessarily saying that we are going to succeed, and I'm certainly not saying that we have succeeded or that success is imminent. So let me be completely clear about that. There are many major conceptual breakthroughs that still have to happen. Here are just 4 of the things that we don't really understand how to do. I'll just pick one of them to talk about: long-range thinking at multiple levels of abstraction. What do I mean by that? If you take a particular task, like giving this lecture, that turns out to be about 40 million motor control instructions that a brain has to give to the body to do something that takes an hour or a couple of hours. And when you compare that to AlphaGo, which is this amazing Go playing program that looks 50 or 60 moves into the future, AlphaGo, if you took that algorithm and transformed it to look at real world control of a physical robot, for example, 50 moves would take you less than half a second into the future. And so that type of algorithm is completely inapplicable to real world decision making, because the timescales and the numbers of actions, the number of steps involved in carrying out complex plans like giving a lecture or going to a conference or buying a car or doing a PhD or even making dinner, right? All of these things involve thousands or millions of steps. And so humans manage this seamlessly by operating at many levels of abstraction simultaneously, even thinking in terms of years and decades, as well as milliseconds, when you're controlling your fingers when you're typing, or your vocal apparatus when you're speaking. You're really operating at a millisecond timescale. We hardly notice that we do all of these things simultaneously, and we stitch it all together, and we generate this competent behavior on many, many scales of time. We don't know how to do that properly yet in AI. That's just one example. So it's very hard to predict when these conceptual breakthroughs are going to occur. And to illustrate that, let me look back at the last time we invented a civilization-ending technology, which is nuclear energy. And so we've understood since about 1905 that there was a vast quantity of energy locked up in atoms. You could look at the mass differences between atoms that had the same number of nucleons and see that there must be, if you could transform one of those atom types into another, or split them, you would be able to get out a huge quantity of energy. And people continually ask physicists, is this possible? Lord Rutherford was the leading nuclear physicist of the early 20th century. And this is what he said in response to a question: could we possibly do this in 25 or 30 years' time? And he said, anyone who looks for a source of power in the transformation of the atoms is talking moonshine. And he said this over and over again in many different forums, and this was pretty much the received wisdom. Einstein also thought that it was impossible. And this is Leo Szilard, and he read a report of Lord Rutherford's talk in the Times the next morning, went for a walk, and invented the neutron-induced nuclear chain reaction. Not long after that, about 6 years after that, the first nuclear weapon was patented by the French. And then the first nuclear weapon, of course, exploded 6 years after that in 1945. So it went from never to less than 24 hours. And so trying to make predictions based on quantitative models of Moore's law or anything like that, I think is really, we're really fooling ourselves. These conceptual breakthroughs can happen overnight. It's very unlikely that all the required conceptual breakthroughs are going to happen overnight, but certainly one of them could. So I think it's prudent to act on the assumption that we will eventually achieve general purpose AI. And most AI researchers think that this will happen, let's say, in our lifetimes. So when AI systems are able to make better real world decisions than humans, right, the quality of real world decisions is what gives us power over the world, right? This is why the human race is in charge of the planet. and not some other species, not the cockroaches, not the dolphins. It's our ability to make better real world decisions, to think over longer timescales, to employ more complex types of planning and reasoning and invention. And Turing is saying, if we're going to create these entities that are more powerful than us, how are we going to retain power over them forever? And clearly he doesn't see a solution to that problem. The approach I'm taking is to say, let's try and see where things go wrong, right? Why is it that making AI better makes things worse? And to understand that, I think it's helpful to go back to the standard model of AI that I introduced. And it's not just AI, right? This is the same basic model that control theorists use when they minimize cost functions, statisticians use when they minimize loss functions, or economists use when they maximize utility or quarterly discounted profit. That we create these machines whose actions can be expected to achieve their objectives. And that works when we can specify the objective completely and correctly, which for games and puzzles we can do, because the objective is part of the definition of what it means to play chess or to solve the 15 puzzle. But in the real world, it's very, very difficult. And I'm arguing that, in fact, we cannot specify objectives completely and correctly in the real world. And we've known this for thousands of years. So this is I think it's probably a Victorian depiction of King Midas, who's a legendary king hundreds of years before Christian era in Greece. And he asked the gods that everything he touched should turn to gold. That was the objective that he specified. Unfortunately, that objective was not correct or complete. And then whenever he touched food or water, it turned to gold. Whenever he touched his family, they turned to golden statues. And he dies in misery and starvation. Similar problem in The Sorcerer's Apprentice, where the apprentice asks the brooms to fetch water, but doesn't specify the objective completely and correctly. So it ends up flooding the whole building, having to get the sorcerer to fix the problem. And if you rub a lamp and a genie comes out, your third wish is always, please undo the first two wishes, because you've ruined the universe. And of course, the problem is you may not get a second wish, let alone a third wish. So we've understood this problem for a long time. And we're seeing it, I think, playing out right now in social media, where we've specified an objective, which for the social media companies is usually maximizing click-through or engagement or some other kind of metric that is closely related to profit. And you might have thought that maximizing click-through, the probability someone clicks on the next piece of content that's recommended, you might have thought that the algorithm would learn what people want. And that would be mostly a good thing, because you wouldn't be sending them stuff they don't care about. But in fact, that's not the solution to the problem. Adjusting to people's current tastes can only get you so far in maximizing click-through. What you should really do, and what the algorithms I think do, is modify people to be more predictable, to be narrower and more extreme in their tastes and interests, so that when you send them content, there's a much higher probability that they will click on it. In some sense, it's what drug dealers do when they create addicts, who will then be very reliable consumers of their product. And many people argue that this is one of the big contributors to the sort of unraveling that seems to be occurring almost globally in our democratic systems and social systems. So you can see that if we had better learning algorithms, better psychologist algorithms in social media platforms, if we improve the AI, right now those algorithms don't even know that humans exist or have minds, right? For those algorithms, we are just a click stream. and they're trying to turn that clickstream into a more profitable clickstream. But if they were better at psychology and better at learning, the outcome for us would be worse because the objective is not aligned with human benefit. So this, I think, is the core of the problem, that you're optimizing an objective that isn't defined correctly. So I'm proposing that instead we need to think about AI a different way. So this is the current way, and I'm arguing that's wrong. And instead, we want machines that are not intelligent in the sense of being very good at pursuing their objectives, but beneficial, actually beneficial to humans. That's what we really want. We don't actually care about intelligence, right? Intelligence was an instrumental goal on the way to having machines that are beneficial to us. And I'm arguing that instrumental goal was wrong. And instead, we want machines that are beneficial, which means that their actions can be expected to achieve our objectives. Now, this might sound almost impossible or something, right? Because our objectives are in us and not in the machine. So how could the machine actually achieve our objectives if the objective is not in the machine? But it turns out that it is possible. Obviously, there has to be an information flow that takes place about our objectives, but it's possible to build machines that are beneficial in this sense. So here's another way, just a little homage to Isaac Asimov, to put it in the form of 3 principles. So the first principle is that the robot's only objective is to satisfy human preferences. And preferences here in the technical sense that the economists have used it to mean preferences over lotteries over completely specified futures. So basically, everything you care about that could possibly occur in the future, how would you rank all those possible futures? So that's what we mean by preferences. Sometimes you might call this a preference structure, but it's a very complex and long-term thing. It's not just what type of pizza do you like best. The second principle is that the machine is going to be uncertain about what those preferences are. And this is the crucial point. And it's this uncertainty, as we'll see, that actually keeps us safe and allows us to retain control over the machine. The third principle is effectively how, from the machine's point of view, the notion of preferences is grounded in that the evidence the machine can obtain about human preferences comes from human behavior, human choice behavior. So everything a person does or everything they don't do, just sort of sitting there doing nothing, is evidence about one's preferences. So all of you who are reading your email while you're listening to this talk, that's evidence about your preferences, but at least you're not going out to mow the lawn. So with these 3 principles, we get a different definition of the problem that the AI system is supposed to be trying to solve. And we call this definition an assistance game. So it's a game because there's a human participant and a machine participant. And it's an assistance game because the machine is designed to be of assistance to the human if the machine solves its half of the game. And when you look at the solutions, so you can write down these games for particular simple environments, and we can solve them, and we can look at the solutions to the game, the Nash equilibria of the game, if you want to talk technical. And in these solutions, the AI system will necessarily defer to the human. It will, for example, ask permission if it comes up with a plan that changes parts of the world that where it's not sure about our preferences. It has an incentive to ask permission before doing it. So if we said, please could you fix the carbon dioxide levels to go back to where they were, and it came up with a plan that would work, but it would turn the oceans into sulfuric acid. If it doesn't know our preferences about the ocean, it would have an incentive to ask permission before turning the oceans into sulfuric acid. And we would say, well, actually, no, don't do that. here's what we like the oceans to be. It will, when acting, it'll act in ways that are minimally invasive, right? It will change as little as possible of the world because it doesn't want to change things where our preferences, it's not sure about. In the extreme case, right, even if it knows nothing at all about our preferences, it's still motivated to empower human choices, to basically add more choices for the human, because that's going to be beneficial to the human. No matter what the human preferences are, having additional freedom to act can help the human achieve their preferences better. And in the extreme case, which is maybe what we might call the core of the control problem, is the ability to switch off the machine. It will allow itself, and I'll show you that it has a positive incentive to allow itself to be switched off, so that it avoids doing whatever it is that would cause us to want to switch it off, right? So whatever behavior would lead us to switch it off is presumably something we don't want to have happen, and it doesn't want to have that happen either, but it doesn't know when it's doing something that we don't like, so it will always allow itself to be switched off. And we can show that it's actually rational for humans to build machines that solve assistance games. So even when we don't know our own preferences and we don't know how to explicate those preferences correctly, it's still rational for us to build machines of this type. And if you, from 10,000 feet, basically, if you make the AI part of this better, if the machine is better at solving assistance games, then it's going to be better at learning about what our preferences are and better at helping us achieve them. So we get better outcomes. And there's a long series of papers where we developed the formal definitions, mathematics, algorithms, and illustrations in various areas, including human-robot interaction and other areas. So let me give you a very simple example of an assistance game. So in this game, the state of the world is very, very simple. It's just some number of paper clips and staples. So P paper clips and S staples is the state of the world. And the human has a preference over how many there are of each. And there's actually an exchange rate, theta, between paper clips and staples. So the human reward function is theta times the number of paper clips plus 1 minus theta times the number of staples. And let's say for this particular person, they have a slight preference for staples. So the exchange rate is 49 cents for a paper clip and 51 cents for a staple. But of course, the robot doesn't know the person's preference for paper clips versus staples. So it has let's say a uniform prior between 0 and 1. And the way we set up this particular game is that the human gets to go first and to make some number of paper clips and staples, either 2 paper clips, 1 of each, or 2 staples. And if that was the end of the game, right, we know what the human would do, right? Because if the human has value 49 cents, then 2-0 would have value 98, 1-1 would have value $1, and 0-2 would have value $1.02. And so the human would choose to make 0 paper clips and 2 staples. But in this game, the robot gets to go and is now going to sort of do the mass manufacturing on behalf of the human. And the robot can make 90 paper clips or 50 of each or 90 staples. And maybe this will be a consequence of the material shortages making it expensive to make lots and lots of staples or lots and lots of paper clips, but maybe a little cheaper to make 50 of each. And so the question is, what does the robot do? Well, that depends on the human preference, right, for paper clips versus staples. Well, the robot doesn't know the human's preference, but the robot has seen that the human has done one of these 3 choices. So the question is, well, what does that choice mean in terms of theta, the preference? And of course, well, we don't know that. So the human has to choose one of these actions, presumably to convey information about their preference for staples or paper clips. And the robot has to interpret that action as conveying information. But we have a sort of chicken and egg problem here, right? There's no previous agreement about a code. But this is what game theory is good at, right? They solve for the equilibrium. And if you do iterated best response on this game, you find that the equilibrium has a policy for the human that that says that whenever your preference theta is in the range 0.446 to 0.554, it's optimal to choose 1, 1, right? So another way of saying this is that the action 1, 1 codes for a particular preference interval. And then 2, 0 would code for 0 up to 0.446, and 0, 2 would code for 0.554 up to 1. And so when the robot sees 1, 1, the robot's response is 50-50, and that turns out to be optimal for the human. And so, so in fact, the human behaves differently in the presence of this robot than they would by themselves, right? They take a pedagogical action rather than what would have been the optimal action in the single agent decision problem. So this illustrates this idea of how how things work in these assistance games, that there's a pedagogical aspect to the human actions and the way they're interpreted by the robot. Let me briefly talk about the off-switch problem, which I said in this new model, the AI system will allow itself to be switched off. So here's our big 450-pound robot that has an off switch. And in the standard model of AI, right, if you give the robot a goal, like fetch the coffee, it doesn't take a genius robot to figure out that you can't fetch the coffee if you're dead. And so by giving it the goal of fetching the coffee, you've given it an incentive to disable its own off switch, right? You haven't put in self-preservation as a separate instinct or anything like that. It's simply a logical consequence of giving it the objective of fetching the coffee, which you can't do if you're dead. And so obviously we don't want robots that disable their own off switch. That would be really, that's the definition of losing control. We can see that when we have uncertainty about the objectives, that there could be many objectives other than fetching the coffee that humans might have. The robot won't behave that way. And we can set this up in a very simple mathematical problem. Here's the robot. So the robot gets to go first in this game. And it has, initially, we're going to say, imagine that there are 2 choices. So it could switch itself off. That's the branch on the right. And then committing suicide, and we'll set the value of that to 0. Or it could take some risky action. So pushing the big red button, maybe it starts a nuclear war, maybe it sets off all the sprinklers in the building. So this is the equivalent of disabling your off switch, meaning that you're taking some risky action without giving the human any opportunity to intervene. And let's say, for the sake of argument, this graph on the left describes a sort of uncertainty that the robot has about the human value for this action. So the utility of the action, pushing the big red button, is mostly positive in the robot's prior belief. But there's a big tail on the negative side, and so this could be very risky. But if these were the only options the robot had, it would go ahead and push the big red button because the expected value is positive. But we're going to give the robot a third option, which is to wait. In other words, to allow the human to switch off the robot. And you might ask, well, why would the robot do that? Because it can switch itself off, right? So what's the point? What does it gain by telling the human that the human can switch off the robot? And the answer is that the human is the one that has the preference information. So the human knows more about the value of pushing the big red button. And so if the human doesn't switch the robot off, then the robot has learned that the big red button is okay to push. And so the negative quadrant of the probability distribution disappears. And now the robot knows that the big red button has positive value and can go ahead and push it. And you can show very simply, and it's exactly analogous to the old theorem, the non-negative expected value of perfect information. And here, basically, the information is being conveyed by the human's choice, that the robot is better off waiting and letting the human switch it off because it's uncertain. So the robot has a positive incentive to allow itself to be switched off because of its prior uncertainty about the human preference function. And if that uncertainty disappears, then the incentive to allow itself to be switched off also disappears. We can also show under certain assumptions about the robot's prior that this robot will be provably beneficial to the human being. So you are better off with such a robot than without it. Now, taking this simple idea, a single robot, a single human has preferences, the robot tries to figure them out and has to act even under uncertainty about what they are. There are many important elaborations and complications in that simple model. For example, how do we deal with the fact that the robot may be making a decision not for one human, but for many humans? And this is obviously has direct connections to moral philosophy, economics, utilitarianism, deontological rules about moral behavior going back thousands of years. We also have to worry about the fact that there could be many machines, not just one. And even if they're all beneficial, you might still worry that they could be unanticipated strategic interactions between the machines that would lead to sort of some kind of prisoner's dilemma kind of problem. We also have to be concerned that the humans we're talking about are real humans, and therefore the connection from their underlying preferences about the future to how they behave is an imperfect one, and it's a very complicated one. It's basically the whole human cognitive architecture. And the machine has to somehow invert that architecture from observing behavior to getting at the underlying preferences. And that's a difficult thing to do. We also have to rebuild each area of AI, because all areas of AI, as I said at the beginning, make this assumption that we can specify the objective completely and correctly at the beginning. And since we can't do that, and since we're going to build AI systems that are uncertain about what the objective is, we need to rebuild all those algorithms, all those theorems, all those complexity analyses, and then create the artifacts, the self-driving cars, the personal digital assistants, the domestic robots, and indeed the social media algorithms on this new foundation. But it's worth pointing out that it's a broader foundation. The standard model is just an extreme special case of the new model. It's an extreme special case in the sense that it makes an assumption of perfect knowledge, which is, in my view, almost never justified. So let me give you one simple example, supervised learning, right? So when in supervised learning, you're trying to minimize a loss function, which is usually expressed in the form of a loss matrix. And the loss matrix for a classification problem, I'm sorry, someone's at the door, just excuse me for a moment. So the loss matrix says for a classification problem, what's the cost of making an error between one category and another? So what's the cost of classifying an ostrich as a bus or a bus as a dog? Usually in practice with these machine learning algorithms, the assumption is one of a uniform loss matrix. So all errors are equally bad. And in that case, in fact, the loss matrix just disappears from the calculation altogether. In pretty much all the machine learning competitions, that's the assumption. But as we know in the real world, the loss matrix is not uniform. For example, if Google Photo classifies a human as a gorilla, that's a huge public relations disaster and incredibly expensive for Alphabet, the parent corporation. And so we understand perfectly well that actually the loss matrix is not uniform. How big is the loss matrix? Well, for ImageNet with 21,000 categories, the loss matrix has 441 million entries. And what are they? Well, you may well ask. I don't know, nor does anyone else. So we have to operate with an unknown loss matrix. Well, let's look up, the papers that solve the supervised learning problem with an unknown loss matrix. Oops, there aren't any, right? So we need to do machine learning with unknown loss matrices, and that's a new and interesting and very important problem that we don't know how to do. For example, how do you write a prior distribution over a 441 million entry loss matrix? Don't know. Good, then we can do a PhD thesis on it. There are now a couple of students at Berkeley working on this, and there are some papers there, one at Europe's, one at ITCS this year, on basically how you do these algorithms that don't know what the loss matrix is, and how you can learn more about the loss matrix. So interestingly, you can learn about the loss matrix simply from looking at human labeling decisions, but only when those decisions are made under uncertainty. So if the human is 100% confident about the classification of the instance, then there's nothing to be learned about the loss function, because there's basically no probability that they could make a mistake. So no matter what the loss function is, they're always going to behave the same way. But when there's uncertainty, then different loss functions would produce different behavior. The human would be more risk averse if the error is more expensive. So in fact, what Google Photo does is it refuses to describe anything as a gorilla. You show it a picture of a gorilla, it says, I don't know what this is, right? So it becomes very risk averse when the loss is high. So you can see from human decision-making behavior what the underlying loss function is. And that's in the Laidlaw paper in this Europe's upcoming. There's lots of stuff to do about real humans. I'm going to go over this very quickly. So obviously we're computationally limited. So we, just as Lee Sedol played losing moves in his game with AlphaGo, that doesn't mean he wanted to lose. So to interpret those moves, you cannot make an assumption of perfect rationality, right? You have to understand the ways in which people are limited. And I think one of the biggest ways that manifests itself in human behavior is the fact that, surprisingly, perhaps, each action that we take is not the first best action in the rest of our lives, right? It's actually maybe the first best action in a plan to achieve whatever short-term goal we've set ourselves, like giving this talk or, picking up a mouthful of food and putting it in our mouths. So our behavior is actually incredibly structured around a whole hierarchy of short-term and medium-term and long-term goals. And so to understand human behavior, you need to know something about what that hierarchy is and how it operates to constrain our decision-making behavior. We also do things we regret under the influence of emotions. We may not know what our own preferences are. This is a very important fact. We don't know how much we're going to enjoy or not enjoy any particular experience. And we have some papers about that. Our preferences probably don't conform to the standard discounted additive sum of rewards model. And Daniel Kahneman has a lot of interesting things to say about that. We have preferences about autonomy, which is not a preference about any particular sequence of states. It's really a sort of counterfactual preference. It says, well, yeah, sure, I'm happy for this future to take place, but I reserve the right to have a different future that I don't like, right? And that's what autonomy means, and how we factor that into machine decision-making is actually quite a tricky philosophical problem. Probably the most important property of humans that causes difficulties for the simple assistance game model is the fact that our preferences are not fixed. They are plastic. that causes two problems. One is that our present preferences may differ from the preferences of our future self. So if the machine's making a decision that affects the future, it needs to know, should I respect the present person's preferences? Because I'm making a decision now that's going to affect the future, or should I respect the preferences that the person is going to have tomorrow when the consequences of the decision become apparent? That's a tricky question. Perhaps even more important is the fact that if your preferences are plastic, then that means that the AI system could change them, in particular, change them towards preferences that are easier to satisfy. And so that's a really important problem. And I think it's happening in the social media context that I described. We also have to worry about there being many humans. Probably one of the easier issues is that our preferences are all different. So there's no sense in which there's one model of human preference or one model of human values. I'm absolutely not saying that I'm going to upload the correct human values or any such thing, because there is no such thing, right? In principle, there's 8 billion people. That means 8 billion different models of human preference, and that's completely fine. But we do have to think about the aggregation problem. How do you make decisions when your decisions can affect the preferences of many people? So some have argued that the AI system only should pay attention to the preferences of the person who owns it. I think that's completely unworkable because it will produce all kinds of antisocial consequences. The other option might be global welfare, that every AI system should care equally about all people on Earth, and possibly future generations as well. And that can produce some tricky problems. For example, that you might buy an AI system, and the first thing it does is go off to whatever part of the world where people are most in need of help, and leave you to do the dishes, which perhaps you wouldn't be very happy about. Philosophers for many years have worried about interpersonal comparisons of preferences, meaning should, if we are going to do some kind of trade-off among different people's preferences, maybe the utilitarian trade-off, then how can that work if it's not possible to put people's preferences onto the same scale? There are questions that philosophers are worried about since the 19th century, where actions affect not only how happy people are, but what people exist. So in the Avengers movie, Thanos has a very simple utilitarian calculation, which is that I don't want to spoil it too much, but if we get rid of half the people, the remaining people will be more than twice as happy, because there'll be abundance and plenty of room and space and all the rest. And so he gets rid of half the people. Now, is that something we want the AI system to do? Or should we figure out a more refined solution to this problem of aggregation of welfare? I think we probably plump for the second. Right. Very quickly, I'm going to talk about aggregating preferences for individuals who have different beliefs. And I'm going to talk about making decisions when people are possibly altruistic or indifferent or sadistic. So let me start with that. We have in economics many papers and books written about altruism and how to model that in utility theory. So one of the simplest is to say that your personal utility has two components. One is the self-regarding component, like my own personal well-being. Am I safe? Am I healthy? Do I have food? Do I have warmth and shelter and so on? And then the other regarding component, which might focus on the rest of my family, the other people in my town and my country, the other people in the world, but all the things to do with people other than myself. And the simplest model would add those together, but you could use many other ways of combining into a joint model. So here's a very simple instantiation of that. Two people, Alice and Bob, So Alice's utility is Alice's well-being. That's a self-regarding component, so intrinsic well-being for Alice, plus some caring factor. How much does Alice care about Bob times Bob's well-being? And Bob's utility is Bob's well-being plus how much does Bob care about Alice, CBA, times Alice's well-being, right? So that's a very simple model. And you can start to ask questions about this very simple model, right? And in particular, the signs of these caring factors make a big difference, right? If it's positive, if these CAB and CBA are positive, then they're both altruistic, right? If there's 0, then there's indifference. So if CAB is 0, literally Alice could not care less about Bob's well-being. But if they're negative, then that means that Alice is willing to sacrifice some of her own well-being simply to reduce Bob's well-being, right? And that is potentially problematic if we're making decisions on behalf of many people and some of them are sadistic. That means we might trade off, right? We might reduce the victim's well-being in order to satisfy the sadists. And Hassani, the economist who wrote a lot about social aggregation, said no amount of goodwill to individual X can impose the moral obligation on me to help him in hurting a third person, individual Y. And another way of saying it, as he often puts it elsewhere, is that the sadist has actually kind of opted out of the social contract, and therefore we don't need to take their preferences into account. So that's one place where perhaps the AI system might put its thumb on the scales of justice, so to speak, a little bit, and say, yeah, people who are explicitly sadists should not be getting any help in implementing their sadism. Just a moment. Okay, so most people agree with that, but I would argue that it's not as simple as that, because in addition to sadism, there are other characteristics of people, such as pride and envy and rivalry, that play a role in what's called positional good. So economists and sociologists for a long time have talked about the fact that our preferences also involve relative well-being, not just absolute well-being. So positional good is something whose value to a person depends on, for example, whether or not other people have that good, or whether my version of it is better than someone else's, even though its absolute value hasn't changed. And so we could write this down again, sort of taking our previous very simple-minded formula, and say that now Alice's preference is Alice's well-being, and then the altruistic part of it, and now the envy part. So the envy that Alice feels towards Bob, based on the difference between Bob's well-being and Alice's well-being. So if Bob is better off than Alice, Alice feels envy, and that makes Alice unhappy, so we have a negative coefficient. And then there's pride. So if Alice is better off than Bob, Alice feels pride, and the pride coefficient makes Alice feel happy, so there's a positive coefficient on that. This is a very simple way of capturing positional goods, and it's actually much more complicated than that, but it gets across the point that when you rewrite this equation, you realize that the envy and the pride, which we're assuming here that EAB and PAB are positive if this is a typical person who cares about positional goods. The envy and the pride are acting exactly like sadism. In other words, they are a negative coefficient applied to the other person's well-being. Now, should we therefore zero out envy and pride? Right. Well, that's a really serious thing. And many sociologists, particularly talking about identity theory, view positional goods as absolutely central to who we are and what we care about. And so changing them, getting rid of them in the robot's behavior would be a big effect. I'm not saying you should never do that, but you'd want to think a lot more before taking that step in implementing AI systems that are operating on behalf of society. Okay, I think I'm going to have time to very quickly go over one more result. which is decision-making for many humans. So as I mentioned, social aggregation is about how do you decide when you've got many people's preferences to take into account. And Harsanyi proved a very famous theorem, the social aggregation theorem, which says that that every Pareto optimal policy, meaning every policy that isn't dominated by some other policy, is a policy that optimizes some linear combination of the preferences of the individuals. And to prove this theorem, he makes the assumption of a common prior, that all the individuals have to have the same belief about the future. That's a strong assumption. What happens if we get rid of that assumption? And so when we get rid of that assumption, it turns out that the Pareto optimal policies are those that weight the preferences of individuals in proportion to how accurate their prior beliefs turn out to be, right? So essentially you're making a promise saying, okay, whoever's right will get all the brownie points, okay? And that's an extremely inegalitarian, Harsanyi's theorem is very egalitarian. He argues that, then he makes a symmetry argument saying, well, the weights in the linear combination should be the same for everyone. But this is a very inegalitarian. It could give you exponentially large differences in the weight assigned to the preferences of individuals, depending on whether they're right about the future. So how could this be? Well, it's actually, it's a theorem, so obviously it's a theorem, but it's sort of conceptually inevitable because everyone thinks that their beliefs are right. Otherwise, they would change them, right? So they think their beliefs are right. And so they prefer a policy which says, if you're right, you get all the brownie points, right? And in fact, they won't accept an egalitarian policy if they have this choice. So this is possibly problematic for a lot of our approach to social welfare in general and so on, but it's a theorem and has to be dealt with. Okay, I'm going to skip over many robots and many humans and say, if you'd like to learn more about this, there's the book on the left, Human Compatible, is sort of written for the non-technical reader, a general audience, has a bit of technical stuff in the appendix if you want more detail. And then the 4th edition of the textbook that William mentioned also has some of the technical content that I've glossed over in this talk. So to sum up, I think AI has huge potential to benefit the human race and possibly unstoppable momentum. But if we continue along the current line where we're building AI systems within the standard model, then we will lose control over our machines, and then that would be the end of the human era. And I think we can do it differently with this new form of AI that I call provably beneficial AI. It's not just possible, but it's actually the kind of AI systems that you would want, right? They're just better than the ones that operate in the standard model. So I don't want the takeaway from this talk to be, oh, I'm saying that AI researchers are bad, and they need to just constantly feel guilty while they're doing their research. What I want is that when an ordinary AI researcher gets up in the morning, they don't have to sort of put on their moral armor and say, okay, I'm going to do the moral thing today. They just get up and say, I'm going to do some good AI research today. But what good AI research means is building AI systems that are beneficial to people, right? Just as in medical research, good medical research is building drugs or surgeries or whatever that are actually beneficial to human patients. And they don't have to gird their moral armor to force themselves to make that choice. It's just what it means to do good medicine, and it should be what it means to do good AI. There are other problems I didn't talk about. Dr. Evil doesn't want to use provably beneficial AI. He wants to take over the world, so we have a certainly bigger policing problem than we already do with cybercrime. And then overuse, so meaning that we end up becoming too dependent on AI that's sufficiently capable of running our civilization that we lose the incentive to know how to do it ourselves. And this is depicted in Wall-E. It's also depicted in E.M. Forster's story, The Machine Stops, which I highly recommend. And we don't have solutions for these problems. So with that, I'll say thank you and stop.
Thank you, Stuart, for the wonderful talk. We have many questions in the Q&A tab. So if you still have any questions, feel free to put your question in the Q&A panel. I'll start off with one of my own questions that I found this talk to be fascinating, and it reminded me of Herb Simon's work on bounded rationality that we talk about, human making decisions for, satisfactory rather than always, optimizing a particular goal. Whereas in machine learning, we see a lot of the AI leaderboards in computer vision and natural language processing. They are just optimizing for accuracy. So if we're going to implement your theory, then how do we replace the existing leaderboards with some of the items that you talk about?
Well, I think it's a separate discussion. I find this competition leaderboard mentality extremely harmful to AI research. And many people have already written about that. But I think many of us have seen it directly in the difficulty in getting any paper published that has a new idea. That what people get published for these days is work that produces 1% better performance on some competition benchmark. And that typically leads us into dead ends in research. So we need to have the ability to come up with new ideas that don't immediately produce better performance on the leaderboard, or in fact may be completely orthogonal to performance on the leaderboard. That they might be a new idea saying, actually, that whole leaderboard is pointless because you're working on the wrong problem, right? But you can't get that paper published because it doesn't produce improved performance. But so what we're talking about here is you could, if I wanted to make a benchmark, and some of my students, for example, Sam Toya has proposed some benchmarks for this kind of thing. And there's a Basalt competition for Minecraft where the AI system is supposed to learn what it is that is wanted. So you could imagine competitions where there's two agents and one agent has preferences, and the goal of the other agent is to help the first agent achieve their preferences. And the score you get is to do with how well you help the other agent achieve their preferences, even though initially you don't know what they are. So it's perfectly straightforward to set up that competition. It's just, it's a different kind of competition that we haven't been doing so far, but we should.
I see. So there's one question in the audience asking about the balance between, getting human preference and, getting novel features from AI. So how do we make sure that we don't, always have this AI systems to defer to humans so much that we are essentially removing the novel features that make AI systems so useful?
I guess I don't see a conflict between the two. I mean, a novel feature that causes the AI system to destroy the world isn't beneficial, right? So there's still novelty in anything the AI system can do that's beneficial to us. It'll be more cautious in the sense that it will not, as I said, not decide to turn the oceans into sulfuric acid in order to satisfy some objective that we did give it without asking permission. But I think that's fine. So, but if it comes up with a completely new way to eliminate carbon dioxide, that doesn't have lots of negative side effects, then it'll do that. So I don't see that there's a necessary necessary conflict between these two things.
Thank you. There are another two questions that I will combine because they're very similar. So, for example, what if humans is evil, right? So what if our preferences are never stable? What if they change over time, or our preferences get affected by other human or get modified? In that sense, how do we make sure that we are able to assign, these preferences to AI and really get the benefit out of it?
So let me take that in stages. So the evil human I already talked about, right? So the sadistic human who actually is willing to sacrifice their own well-being just in order to inflict suffering on others. I think we should zero out those sadistic preferences. But if it's simply not the case that the AI system will copy the behavior of, let's say a criminal, right? Any more than a criminologist. So a criminologist is someone who studies criminals, but they don't start doing crimes as a result of that, right? They just understand the motivations of the criminal. And usually the motivations of the criminal are no different from those of anybody else. They want to have a decent standard of living. They want to send their kids to expensive schools, and so on. But if they're a a government official, in the passport department in a country that pays very, very low government salaries and expects their government employees to take bribes in order to make up their salaries, then the AI system is not going to learn to take bribes, but they're going to learn that why is this person doing this, and is there another solution that could convey some of the benefits in terms of sending their kids to school without imposing the costs on others, which is what the bribe is. And so that part of this is fine. There's no reason for the AI system to copy bad behavior. And in fact, if you think about it, right, it's the AI system viewed as an agent is completely altruistic, right? The WA, right, the own well-being is zero, right? It doesn't care about itself at all. So in a way, it's going to be an example to us all of how to behave completely altruistically.
I see. Thank you. And one last question from the audience. One question that the audience asks is about, how does AI ethics interact with the system reliability? So how do we, design AI systems to be fault tolerant, whereas, for example, some of the, occurrences of the hardware or software failures, they may invalidate, right, some of the assumptions under which that the system was deemed to be beneficial?
Yeah, I think that's a good question. And, I'm working with people in the formal methods community whose business it is to prove correctness of AI systems, among others. And so I think this is a very underemphasized area of computer science, particularly in the US, not so much in Europe. I think they care a lot about correctness in Europe. I think in the US, and to some extent in the software industry, they don't seem to care that much about formal correctness. And I think it's difficult and expensive and so on, but I think you have to do it. The stakes are simply too high. And if you look at methods like evolutionary programming, where or even to some extent deep learning, where it's just a black box, right? You're just trusting that somehow this black box is going to behave itself, and then every so often, as happened with the Tesla autopilot, it just goes completely haywire and kills you, right? That's not going to be acceptable when we're talking about the whole human race.
Thank you. I want to thank Professor Stuart Russell again for this wonderful keynote. We're right on time, and let's thank Professor Stuart Russell again.
Thank you. Thank you very
Okay,
much.
so next, let me introduce the next session chair. So our next session is on AI ethics and social and global development. And I'd like to introduce our session chair, Mariam Maxer, Professor of Communication and Information Technologies at UCSB. And Mariam will be the session chair and introduce the speakers for this session.
Yes, thank you. Can everyone hear me all right? Okay. Well, welcome to the session on AI ethics and social and global development. I think this is a really important session. I'm glad it's the first one too of the various sessions throughout the day, because I think it sets an agenda for us well. I'm a social scientist, but you're not here to hear about me. You're here to hear about our speakers, and I'm going to give very, very short introductions so we can get right to it. But I just want to say we're going to be hearing 3 talks this morning that range from ethical issues such as trust in AI and algorithmic fairness, to designing AI for the purpose of enhancing social good around the globe, not only in developed countries, but also in the global South. So we have 3 speakers today. I'm going to introduce them in turn. Our first speaker is Professor David Danks. Dr. Danks is Professor of Data Science and Philosophy, and also is an affiliate faculty member in Computer Science and Engineering at the UC San Diego. He uses ideas, methods, frameworks. He draws widely from philosophy, cognitive science, machine learning to examine the ethical, psychological, and policy issues around AI and also robotics in a variety of different domains, including transportation, healthcare, privacy, and security. He's also done research on computational cognitive science and algorithms for causal discovery. And he's the recipient of a number of prestigious awards. So his talks today is titled Trust AI and Societal Values. And take it away, Professor Danks.
Thank you so much, Miriam. I really appreciate that kind introduction. Hopefully people are now able to see the slides there. So I should start by saying that today I'm going to be talking primarily with my philosophy hat on. I'm not going to present any AI system. I'm not going to be looking at specific systems that we have built or the ways that they interact with social environments. Rather, what I wanted to do is actually take a step back and ask a kind of question about the foundations of the use of AI for social good. In particular, it's become quite common now for people to talk at great length about the importance of trustworthy AI, about AI that we can trust. And there's been some really fantastic work on the nature of trust in an AI and the psychological ways in which people build and acquire trust in AI. Almost all of that work, though, and I include my own in this, it has focused on the individual. What is it for me to trust in AI? But if we're going to be deploying AI systems at a society level scale, if we're going to be using them to try to advance our social values and interests, then it's important that these are actually trustworthy for us collectively, not just for me individually. And as I'm going to try to sort of briefly argue, I don't think that individual trust, when you add it all up, is the same as collective trust. There's a difference between us as a community trusting an AI system and each of us individually trusting the AI system. So I want to explore what it would be for a community to trust by generalizing a notion of individual trust that I'll explain briefly, and then apply that to a particular case of a diagnostic AI system. So medical diagnosis is a pretty standard use case where people want to try to find social good and deploy AI for social values, for social advancement, particularly in communities that are traditionally underserved by medicine and by medical resources. So it's often the case that the people developing the AI system are not members of the community where the system will be deployed. So I think it's a particularly important test bed for what it would be for a community to trust a diagnostic AI system, not just an individual doctor or an individual patient. So with that, those are sort of the three big points I'll hit. Where I say implications, it'll actually be more of an application. Apologies for that. All right, so what is it that we mean when we talk about trust within individuals? So in general, trust has been studied by well over a dozen different disciplines. It is, a classic case of one word has resulted in a complete proliferation of theories. At one point I looked and there were over 45 different theories of what trust is, depending on what domain you came from, which might, I think, lead and has led some people to sort of despair that there's anything interesting to say about trust beyond people's sort of experiences of trust. So a kind of either reduction of trust to reliability or a reduction of trust to people like it and will use it. But I think we can actually do better than that. At a high level, trust is about the trustor making themselves vulnerable because they have positive expectations about the behavior or intentions of the trustee. So this can be very simple. I, for example, might trust my car to start in the morning, and so thereby make myself vulnerable in the sense that I don't go out and test it 2 hours before I have to leave. I trust that it's going to just start when I go out there because I have expectations about its behavior. Namely, it will start when I need to go to the grocery store, for example. Similarly, I can trust my wife with our daughter. I make myself vulnerable and my daughter vulnerable by not exerting, not having oversight on what happens when they're together because of my expectations about her behavior, my wife's behavior, her intentions, her values. And these three pieces actually show up in essentially every theory of trust that you find in the literature, whether you're in organizational behavior, social psychology, philosophy. These three, which are clearly interconnected, are sort of universals that show up in any theory of trust. So, for example, when we look in social psychology, we find that there really are, at a high level, two different kinds of trust that people study. One is grounded in the behavioral reliability of the trustee, like my car starting in the morning. The other that's grounded in my understanding of the trustee, my understanding of their values and beliefs, as when I trust my wife to take care of our daughter. The first is, of course, more behavior focused. It's about what the trustee will do. And so in this regard, it gives actually an incredible amount of power in terms of the coordination and prediction between the trustor and the trustee in known circumstances. Okay, so if I'm trying to figure out, when I need to go out to get in my car, I know when I can go out there. I can trust the reliability of my car to start if it's a known circumstance. If, for example, it hasn't rained. San Diego, it doesn't rain very much here, but imagine it rained 12 inches overnight. I might not trust my car to start in the morning anymore because I'm now in an unknown circumstance. In contrast, the kind of understanding basis for trust, we've found psychologically, as a community, we have found that it involves knowing why the trustee will do whatever they will do, and so enables coordination and prediction in novel circumstances. Okay, now, it's very easy to look at these two and go, oh, the first one is about artifacts and objects and machines. The second one's about people. It turns out that actually doesn't line up quite right. So, for example, when I think about trusting that my garbage will be picked up on Monday mornings, that's much more in the first category. I don't know the beliefs and values of the folks who pick up my garbage, unfortunately. It's focused on their behavior. I know what they do. They're reliable. And when we think about understanding, if we have a kind of deep understanding of even a machine, then we can coordinate and predict in entirely novel circumstances. I don't know whether my car will start after 12 inches of rain, but surely there are people who do because they understand how the vehicle works. Now, just to continue to show the kind of diversity of theories of individual trust, if we look in philosophy, the focus is entirely not on the trustee or what I know about the trustee, but rather on what is entrusted, the values that I, as trustor, expect the trustee to support. Right? And these are about values, not utilities. Okay, there is sometimes we can translate our values into utility functions, but that's not necessarily the case. And trust sort of has for most philosophers, there has to be the possibility of betrayal. It seems very strange to say, well, I trusted you, you let me down, but I'm okay with that. That seems to be to go in the face of how we usually think in terms of the ethical obligations of trust. That if I'm certain about what's going to happen, it's no longer trust, it's knowledge. And so there needs to be this kind of leap of faith. So one might wonder whether there's really anything that binds these different accounts of trust together. I've given you 3, could have given you another 20. One thing that binds them together actually is a pretty interesting set of negative conclusions. So they basically all agree, even the behavioral regularity approach in social psychology agrees, that mere reliability is insufficient, that my perceptions or feelings of trust are insufficient, that just acting like I trust, even if I don't really, is insufficient. And the moral of these negative conclusions and others is that trustworthy AI, if we locate the moral for AI, trustworthy AI for an individual is not about the sort of surface or purely technical features. So when we, sort of first take-home message is when we think about trustworthy AI, it is not a purely technical problem. You're not going to be able to have something that is trustworthy AI without actual engagement with the people who are supposed to trust your system. You're going to have to know something about the values that they entrust to the system and how they respond. Now, we can integrate this together. In the interest of time, I'm just going to put this up here. I'm not going to go into the details. The point is that we can actually integrate a huge number of those different theories from different disciplinary backgrounds under a kind of unified view of what it is to appropriately trust a thing or a person. And the different accounts that we get in the different disciplines largely result from them making different background assumptions. So if I'm in organizational behavior, if I'm working in that discipline, I'm focused on trust within an institution with informal and formal structure. And so I can assume a lot of things about people's beliefs and what their relevant values are and so on. The main thing I want to show here is, again, when we talk about reasons, when we talk about counterfactuals, knowing what would happen if the world were different, when we talk about values, these are, again, all things that are not purely technical. Now, we can reformulate this into AI. So we can talk about what it is for an AI system to be trustworthy for me as an individual. And here's one characterization, that I have good reasons to expect that the AI, plus other things in the system, will act in ways, in particular including responses to failures, that support and advance my values. Okay, so that's an account of individual trust that we might have. Now, when we talk about societal trust, a trustworthy AI needs to be appropriate for any member of the group. That's part of what it would mean to be trustworthy for a collection of individuals. It might not be trustworthy for every group, of course. It might be that a system is trustworthy for professors, but not trustworthy for students, or trustworthy for Californians, but not Pennsylvanians, for example. And that's okay. We don't need a system to be trustworthy for absolutely everybody. It'd be surprising, as we'll see, if it were. Moreover, when we think about trustworthy AI at a societal level, it's important that the evidence for that isn't private. Okay? If we think about having reasons for the trustor to trust, those reasons need to be shared across a community. If we think that the system is actually trustworthy for us collectively, then we should have a shared understanding of the reasons why it is trustworthy. So what that means is it's not just that each individual has their own private reasons. If I trust the AI for one set of reasons, and Miriam trusts the AI for a different set of reasons, that doesn't mean that we collectively trust the AI. We each individually do, but we don't have the shared collective understandings that are needed for a kind of societal level trust. And I'm arguing here, when we think about trustworthy AI, it's the society level one that we should think about. We shouldn't be thinking, or at least we shouldn't solely think about whether each individual can trust this AI. We should think about whether we collectively can endorse it, especially when AIs are rolled out at a society level scale. So what does that mean? How do we reformulate the previous statement about individual trust in terms of societal trust? Well, what we need to do is shift from the I and mental states to the we and the public. So I put forward that societal trust is about we collectively having good public shared reasons to expect that the AI will act in ways, including responses to failures, impacting anyone. Okay, so collective trust is in part also about how the system responds when someone in my group is affected by a failure. If we think just in terms of individual trust, there's a sense in which happens when the AI fails on someone else, except in as much as that gives me some information about how it would behave to me. It's a kind of egocentric, selfish view. But when we think about societal trust, it's exactly to think collectively. It's that I don't just think about myself, I think about us as a group. And in particular, that should support and advance our group values, not just my personal values. Now, you might look at this reformulation and say, wait a second, this is never going to be possible. Okay, there's a sort of straightforward response that I'm guessing a lot of you in the audience have already yelled at your screens, which is societal trust, as I just reformulated it, requires that we identify group values. What, as a philosopher, I would call value pluralism. My values are not the same as Miriam's. No two people have identical values. That value pluralism suggests there aren't group values. There aren't things that are shared across people that can form the basis of trustworthy AI for a collective. Well, one option we might do is we could say, well, let's just find enough values that everyone shares. Right? Everybody is in favor of, I don't know, ice cream and puppies. That's not going to be helpful, though, when we think about trustworthy AI. Because as we'll see in a moment with medical diagnostic systems, we should expect that there will always be a certain measure of diversity in terms of the values that people have. And so it's just empirically unlikely, if I'm trying to build a trustworthy AI system, it is empirically unlikely that I'm going to be able to find enough shared values in the relevant community to support the development of my trustworthy AI. So what can we do instead? Well, the other option is to think about, well, what do we do when we encounter value pluralism in everyday life? Value pluralism is in some sense, you can think about political systems and deliberative systems as in part an answer or response to value pluralism. I think I have certain values about taxation, social services. My neighbor has different values about taxation and social services the government should provide. And a political system has legitimacy in part so that it can resolve these disagreements, so that there can be decisions that are made that we collectively endorse, even if I individually disagree with it. And so we can draw inspiration from the kinds of methods that are actually used in political systems. I'm not advocating, by the way, here that the government should be involved in trustworthy AI building. I'm saying that those kinds of methods, public deliberation, fair voting amongst a community, negotiation amongst members of a community, these are ways that you can establish a set of community values that everyone will publicly acknowledge, even if they personally disagree with some of them. Now, I want to make sure to emphasize, this is a high bar. Okay, right now, I think a lot of the efforts on building trustworthy AI, to the extent that they look at a community, they look at them via interviews and surveys. But interviews and surveys will tell me what Miriam's values are, or William's values are, or I can find out my own values by doing one of these surveys. I'm making the argument that if you want to have actually trustworthy AI for a community, you as the developer or someone in your organization is going to need to have much deeper engagement with the community, because you're going to have to work with the community to identify a set of values that everyone can publicly acknowledge, even if they as important, even if they personally might disagree with them. So hopefully I haven't run out of time quite yet. So let me just quickly show what this looks like in the case of a diagnostic AI. There clearly are shared values. Everybody wants our diagnostic AI system to be accurate and timely. If it would take 2 months to come back with a diagnosis, that's not useful. If it makes more errors than most doctors do, that's not something that we would want, and it surely would not be trustworthy. But of course, we also have some very differing values. Some people think that it's okay to make errors about the costs of the errors. So are the errors, is a false negative worse than a false positive? There are going to be differences, both differences between patients and doctors and these differences within groups of doctors and groups of patients about how bad a false positive versus a false negative really is. That's not something that we can establish necessarily or expect there to be agreement. The types of the error also lead to different values, and the distribution of the errors. Is it a problem if one community is disproportionately affected by the errors of the diagnostic AI system? We would expect different members of a community are going to have different values about how important it is to ensure that the errors are distributed uniformly, for example, across the group, even if that might come at a cost of some accuracy. So the usual response that often happens here, at least in the projects that I am aware of, is that people have said, all right, well, let's focus on the shared values. As long as it's accurate and timely, we're going to be okay, we'll build it. Okay? And this is how we're going to get trust. The problem is, of course, when you're building one of these systems, you still have to make assumptions and build in particular values about the cost of error and times of error. I mean, even if it's just where on the ROC curve am I going to fall in terms of the trade-off of false positives, false negatives. As a developer, I can't avoid making commitments about those things. So what happens when individuals who don't share those values use the system? We're going to have a value mismatch, which will lead to a loss of individual trust and presumably a loss of group trust. That we should expect that these kinds of systems are going to struggle to find widespread deployment, assuming it's not government or organization mandated, precisely because there are going to be individuals who are going to say, this system doesn't support my values. And there's no agreement on what our values are, so I'm not going to go through that route either. Instead, I want to suggest that if you're building one of these systems and you want to have it actually be trustworthy, you need to engage in a public discussion with the community about the values related to the errors. This isn't about voting in a social choice theory kind of way. It isn't about surveys. It's about actually engaging with the community in ways that, I will say as an aside, are likely to be good for the community itself, to ensure that everyone has appropriate beliefs about what our values are going to be, even if those might differ from what my personal values are in this particular case. So I think there are ways to do it. There are ways to have trustworthy AI that is trustworthy for entire communities. But I think it's going to require us as us AI developers, and I include myself in this group, to do more than we have perhaps done in the past. It's not just about surveys of stakeholders and then pushing it through some social choice theory. So I think trustworthy AI is a really important goal, but in order to get group trust, we're going to have to do more. So thank you very much.
Thank you. I forgot to mention earlier that we are going to be doing the Q&A after the 3 talks, just in the interest of time. We're going to put so hold your questions, you can put them into the Q&A box, and we'll get to them after the talks. Our second speaker is Phebe Vayanos. Dr. Vayanos is an assistant professor of industrial and systems engineering and computer science at the University of Southern California, and is also the associate director of the Center for Artificial Intelligence in Society. Her research looks at optimization and machine learning, particularly as it pertains to solving problems that are important for the social good, things like public housing allocation, public health, biodiversity conservation. And she also has received some really prestigious awards, including an NSF Career Award and the Informs Diversity, Equity, and Inclusion Ambassador Program Award. So welcome, Dr. Vayanos. Title of her talk you can see here is Towards Robust, Interpretable, and Fair Social and Public Health Interventions.
Thank you so much for the introduction, Miriam. Let me pull up my slides. So hello, everyone, and thank you so much for joining my talk. You can see my slides all right? Yeah? All right, perfect. So I'm really excited to be here. And thank you so much, William, for organizing and for inviting me. It's a real pleasure to be here to share a little bit of our work and to have interesting discussions. So like Miriam mentioned, today I'd like to talk mostly about our work concerned with issues of robustness, interpretability, and fairness in both machine learning and resource allocation. So just as a bit of a background, let me tell you a little bit about our research group and the research approach that we take. So my group is part of the USC Center for AI in Society, or CASE for short. This is an interdisciplinary research center between the schools of engineering and social work at USC. So it brings together researchers in artificial intelligence, in operations research, in machine learning, and then at the other end, people, experts in social work, in social sciences, in particular on issues related to homelessness, substance abuse, and suicide prevention. In my research group, we take a very use-inspired research approach. So what I mean by this is that we work very closely with community partners and policymakers throughout the research process. So both as a way to identify their most burning or pressing issues, right, the things that keep them up at night, but then as a way to ensure that all the mathematical models we develop, all the ways in which we use the data are actually informed from their knowledge. Ultimately, our goal is to have approaches that we can ourselves deploy to make an actual impact in practice. Broadly speaking, in terms of applications, our research is focused on three broad domains. So one is public health, looking at issues surrounding kidney allocation or allocation of scarce healthcare resources during the pandemic. A lot of our work is focused on social services provision, so things like substance use prevention, suicide prevention, and homelessness. And I'm going to talk about several of these today. And finally, somewhat a little bit different, looking at problems around biodiversity preservation. So what's the permeating theme here? As we're working with communities, with real data, and as we're looking to deploy our approaches, there's issues of robustness, right? Issues of trust in our system, issues of making decisions under uncertainty, when we know our data is not perfect, when we know that even as we deploy, things are not going to be exactly as we predicted them. There's, of course, issues of interpretability when we're working with people making decisions that impact society. We want to have decision-making models and prediction models that are actually very interpretable, so that it's very easy for somebody to understand why a decision was made. And finally, the last permeating theme is, of course, fairness. As we're looking at allocating scarce resources, right, there's a lot of debate as to who gets what. So how do we measure fairness in those systems? How do we impose fairness in those systems? And what are the appropriate fairness metrics that we should be looking at? So today I'd like to tell you about four kind of problem classes that we've been involved in. And the first one I'd like to look at is this problem of designing policies for allocating very scarce housing resources to people experiencing homelessness. And at the very top here, I'm showing the students who should take all the credit for this work. So PhD student Aida Rahmat Alabi, PhD student Ying Xiaoye, and undergraduate student Catherine Dallaret. So the motivation for us to look at this problem is the homelessness crisis. I guess many of you have been in LA. The numbers are quite staggering. We have at the moment 66,000 persons experiencing homelessness, and only 21,000 housing units, only a small percentage of which are actually long-term supportive interventions. At the same time, there are significant disparities in homelessness. Black people, for example, represent 40% of the homeless population and only 9% of the general population. So clearly, as we start thinking about how we're going to be allocating these very scarce housing resources of different type to people experiencing homelessness, we need to take into account these underlying disparities to make sure that we don't make them worse, of course, but also perhaps looking at mitigating them. Finally, as you may be aware, right, the longer you're on the street, the greater your risk of being exposed to things like violence, drug use, and HIV or COVID. So it's very important to try and get people out of the street as fast as possible. Our partners in this work are the Los Angeles Homeless Services Authority, which is the organization in charge of allocating scarce housing resources in all of LA County. We're also working with many other organizations, including the California Policy Lab and LensGo. So in our endeavor to try and kind of optimize this system for allocating these scarce resources, Lassa shared some historical data with us, namely data from the Homeless Management Information System. This is data collected in deployment, not in an RCT setting. Basically, what we can see is all the individuals who came in need of housing, their characteristics, their answers to the so-called VISP-DAT survey. Then we can see what kind of resource they got matched to, for example, permanent supportive housing, rapid rehousing, or services only, and then the outcome of that match. Were they able to successfully exit homelessness, or did we see them come back in the system after a while? Of course, working with this observational data set is very challenging. Indeed, we can only observe the outcome under the treatment received. And if we want to design a new policy, we'd like to know the counterfactuals. What we propose in order to address this problem is the following. So what is it we want to do? To summarize, is that we want to design a very interpretable policy that's data-driven, so informed by the data we have at our disposal, that's going to optimize some form of outcomes, for example, the returns to homelessness, subject to certain fairness constraints, right? For example, we'd like to have outcomes that are as similar as possible across groups, or that are, for example, at least as good for groups that have been historically marginalized. So we propose a method that I don't have time to give you the details on, that's going to combine techniques from queuing theory in operations research and causal inference to come up with this best possible strategy that is fair. So let me just show you some results to illustrate this point. So here on the y-axis, I'm showing something that measures efficiency, so the probability of exiting homelessness, and we'd like to be that to be as high as possible. And on the x-axis, I'm showing a measure of fairness, in particular, the probability of exiting homelessness for the group that's going to be the worst off. So again, here we want to be as high as possible, so as much to the right of the figure as possible. And we evaluate now our optimized policy, which is shown in green, relative to, with the little square, the policy that's currently deployed, that is unknown, by the way, the policy that is recommended, that make recommendations for matching people to resources, and then the first come, first serve policy. And what we can see is by using this blend of techniques from causal inference and operations research, we can actually design policies that are going to be somewhat more fair and more efficient, which is perhaps counterintuitive. In addition, our proposed policy is going to be able to reduce wait times down to about 50 days from over 100 days, which is, of course, very attractive given how much at risk individuals who stay unhoused for long periods are. All right, so now in what I talked about so far, I kind of assume that we know, right? We've all decided what the outcome we want to optimize for is, and we all know what the fairness constraints that we want to impose are. For example, in my previous slides, I imposed fairness by race, actually, I forgot to mention. The issue, of course, is that it's not that simple, right? There's many possible conflicting things I could be optimizing for, and many different metrics I care for in terms of how my policy is going to do. For example, I may care about it being very interpretable, right? But at the same time, I may want it to be efficient. For example, that we should see as few people return to homelessness as possible, or maybe as few people as possible suffering from things like drug use, substance use, broadly speaking. Finally, we'd like it, of course, to be fair, right? But it's not at all clear what fairness means. For example, we could talk about things like statistical parity in allocation, right? Conditional statistical parity in allocation. Maybe I want to know that when I condition for some on some covariates that can justify differences in the allocation, then I have a parity. Or we could look at fairness in outcomes instead of allocation. In particular, looking at in terms of who exits homelessness. I'd like people to have equal outcomes. Of course, now this goes a little bit back to David's presentation that, you know, it's very hard to understand how policymakers would make decisions, right? How would they value these different and conflicting objectives? And this is really a question of trying to understand the moral value judgments of policymakers to be able ultimately to design a system that's gonna align with their preferences. The way we propose to approach this problem is by devising elicitation approaches that use pairwise comparison queries, looking at outcomes and characteristics of different policies and asking policymakers to tell us which one's their preferred one. For example, would they choose a policy that looks like the one on the left, which is quite unfair but efficient, or would they choose a policy like the one on the right that's very fair but arguably not so efficient? So we propose a methodology based on techniques of optimization under uncertainty to select the queries that are the best possible to inform our downstream recommendation problem. So just to show you some results here, what did we do? We took the HMIS data and we generated counterfactual policies for matching people to resources. These were the candidate policies that we used to elicit the preferences of policymakers. What we see now is that our policies, our elicitation approach, make recommendations. Here I'm showing our approach in red that consistently rank higher no matter how many questions we ask. So this is just the number of questions on the x-axis. And this is true whether there are inconsistencies in their responses or not. Let me now move on to the second part of my talk, which is concerned with substance use prevention, and that is work led by undergraduate student Nathan Joe and PhD student Sina. So the motivation for this work is the huge number of people that suffer from substance use problems in the US that have been getting even worse throughout the pandemic. This is work in collaboration with Chestnut Health System and Professor Jordan Davis, who's an assistant professor in the USC School of Social Work. So because this is a matter affecting, of course, public health, there's a need for personalized interventions for deciding who should get the what kind of intervention, so that we can really tailor the intervention received to the individual. That said, because it's a public health domain, we believe that it's very important for the way in which we decide on the treatment to assign to be very interpretable. And so we decided to design interventions in the form of prescriptive trees. So what are these? You can think of them a little bit like classification trees, except that this time, instead of making predictions at the leaf, we make treatment assignments. And so we want to select the test to perform at each internal node and then the treatments to assign to maximize decision quality. However, because we are in settings usually that affect also marginalized groups and groups that have been historically unfavored, we want to make sure that we can incorporate potential fairness constraints and requirements in our policies. Not only this, oftentimes there are capacity constraints that we need to satisfy for each of the treatments. So we want a method that's flexible to incorporate such domain-specific requirements. The challenge, as in the case of the HMIS data, is that in order to help learn our prescriptive trees, we only have access to observational data. And so what we propose in order to address this problem is a framework that blends techniques from optimization, in particular, an optimal classification tree approach that I'll tell you a little bit about at the end of my talk, and techniques from causal inference to provide trees that are guaranteed to be the optimal ones as the number of training sample grows. At the same time, our framework is actually able to incorporate constraints in terms of fairness in the allocation or fairness in the outcomes, and also potential capacity constraints. I'm only showing here results on synthetic data because we cannot know the counterfactuals on the real data, but this will serve to illustrate a little bit the point. So what we show is that no matter how treatment was assigned in the data, our proposed approaches shown in orange and green consistently assign treatment correctly about 75% of the time, whereas other methods from the literature actually oftentimes assign treatment incorrectly. In fact, in some settings, they assign treatment similar to random treatment assignment. I'd like now to move on to the third part concerned with biodiversity conservation. The motivation for looking at this problem is the rates at which species are becoming extinct. That's getting worse and worse at the moment. The key cause for these species extinctions are unfortunately human-induced degradation, which means that humans go, they build roads, cities, or we build roads and cities, and this destroys the habitats on which animals rely. For this work, we're partnering with Panthera, which is an organization dedicated at preserving wildcats. And in particular, we're working very closely with Dr. Hugh Robinson, who's Panthera's Director of Applied Science. Together with Hugh, we decided to focus on a particular case study, namely protecting the jaguar in Central and South America. Why the jaguar? Because it's what is called an umbrella species, meaning that if you protect the jaguar, you will be actually protecting all other species as well. So it's kind of sufficient to protect the jaguar. A key strategy for preserving biodiversity is to purchase or ease land. The key challenge, though, is that we don't usually have a lump sum available today in order to help purchase land. Instead, funds become available over time. So we can initially go protect some areas. Anything we don't protect risks becoming developed. Then we can go protect some additional areas and so on and so forth. The issue, though, is that there's a lot of uncertainty in which areas are going to become developed if I don't protect them. And this uncertainty is also endogenous, meaning that through my actions, I can change what will happen. Okay, I will change which parcels will become developed and which ones will not. I'd like to argue that we'd like a method that's going to be robust to uncertainty, that no matter how land becomes developed, we want to make sure that we save those species. Indeed, if some parcels become developed, we're going to lose the ecosystems associated with them forever, and they're not going to be possible to recover. At the same time, we'd like an approach that's data-driven and adaptive so that it uses any data we have at our disposal and can adapt to the sequence of a kind of as uncertainty unfolds. How are decisions currently made? Well, they're interestingly made using optimization approaches, in particular by solving a mixed integer program that I'm showing here on the left, which basically tries to save a target number of animals of each species at lowest possible cost. The issue with this is that it completely ignores uncertainty, and so it could be protecting areas that have a very large number of jaguars that have low cost, but have very low chance of becoming developed. So we really need a method that's going to account for this uncertainty explicitly. We proposed an approach that integrates techniques from robust optimization with the popular cellular automata model from conservation ecology. Let me show you some results. Here we're showing on the left the number of jaguars that are located in protected parcel under our proposed method in red and Marxan in blue as we vary the budget. What we can see is indeed Marxan here protects parcels that have more jaguars. However, I'd like to argue that this is completely irrelevant. What we'd like to look at is how many jaguars were lost due to development. And here we can see that Marxan actually loses a lot more parcels, a lot more jaguars, because it fails to protect those parcels that were likely to get developed even when they had few jaguars. And let me now close with my third topic, which is concerned with robust, interpretable, and fair ML. In this project, we didn't have a specific application in mind. We just realized that there's an urgent need for tools for doing machine learning that are robust, interpretable, and fair at the same time, and that we could use in the various other projects that we were involved in. And we are not the first ones to have made these observations, right? As you all know, machine learning is increasingly being used to support decision-making in high-stakes domains. And this really means that we need to be thoughtful to be able to have machine learning models that can incorporate arbitrary fairness notions that are informed by specific domains we're working in. We'd like those models to also be interpretable. And again, for these interpretability requirements, they may mean different things for different domains. And finally, when we're working in such domains that impact people and society, we'd of course like to make the best possible predictions, so optimality is going to be crucial. In my view, the most interpretable machine learning model, probably my favorite model, are classification trees. And we'd like to learn classification trees that are optimal in the sense that they have the highest possible accuracy and also able to integrate arbitrary fairness and interpretability constraints such that we can use them in the domains that we encounter. We propose such an approach. Basically, you feed in all your requirements. You can even choose what objective you'd like to have to, for example, take into account issues related to imbalanced data sets, and then get a decision tree that will satisfy all those requirements in your test set. Just to give you a little bit of a flavor of what an optimal fair decision tree looks like, this is one where we're trying to predict propensity scores in our HMIS data using this framework, and the fairness constraint we impose are equalized odds to make sure that we have equal mistakes somehow in our machine learning model for different age, race, and gender groups. What we see is that CART, which is shown here without color, is quite unfair. It has a worst case difference between groups that is about 100%, whereas with our approach, using a single tuning parameter, this equalized odds bound, we can really tune the trade-off between fairness and accuracy. I am somewhat running out of time, so I'll just say a few words about distribution shifts. We have also generalized this framework to take into to work in cases where there's distribution shifts between the training and test set. This is particularly relevant in the settings where we're working with, where we collaborate with people that, take a qualitative approach to addressing the problem, where, for example, they may change the way in which questions are framed and therefore change the way in which people respond to those questions. We have an approach that integrates integer robust optimization and machine learning to learn such trees that will have the highest worst case possible classification rates under those shifts. And we show that no matter if we are aware of how the distribution will change between training and test, it performs consistently better, this is shown here in yellow, than an approach that is non-robust. I'd like to conclude by saying that I hope to have convinced you that new research in artificial intelligence operations research and machine learning is needed to address important societal problems of our time. I also hope to have shared a little bit with you my view on the benefits of collaborations with community partners, not only in terms of making a positive impact on society, but also to help identify important research questions in our field. There's many more interesting use-inspired research questions that we're looking at addressing in our group that relate to data uncertainty, distribution shifts, missing data, and observational nature of the data sets we're working with. I'd like to acknowledge funding support from many organizations, and thank you all.
Thank you. All right. Our last speaker, and I hope I pronounced this correctly, is Neha, Professor Neha Kumar. And Dr. Kumar is an associate professor in the Sandholm School of International Affairs and School of Interactive Computing at the Georgia Institute of Technology, Georgia Tech. She studies the intersection of human-centered computing and global development. And her lab is called Tandem, which I like very much. It's short for Technology and Design Toward Empowerment. It has a focus on challenges around data, stigma, and gender in the global health context. And Dr. Kumar is currently president of ACM SIG-Chi. The title of her talk today is Human-Centered Design of Artificial Intelligence Systems for Frontline Health.
Thank you so much. So I should go ahead and share my screen now, right? It's going to stop. Okay. All right. Just give me a second. All right. So tell me what you see. Do you see the title slide that says
Yes.
human-centered design of? Okay, great. And the audio works. I should go ahead and get started. Okay, thank you so much. Hello, everybody. Good morning, good afternoon, and thank you for the invitation. I'm Neha Kumar, as Miriam introduced me, Associate Professor, jointly appointed at the Schools of Interactive Computing and International Affairs. This is at Georgia Tech. And this is because the work that I do lies at the intersection of human-centered computing. So that's mainly human-computer interaction and global development. And frontline health is an area that my students and I have been studying actively over the last decade or so in rural and urban India. I want to say a little bit about my background, because maybe that would help the audience, because it is a diverse audience. Just to understand where I'm coming from. So my background and training is in computer science. I also have a degree in learning design and technology. And then got my PhD from the School of Information at UC Berkeley. And so I've been working in the spaces of computing and development for the past I guess a little over a decade, and have been focusing on frontline health and global health for much of that time. More recently, we've been investigating the challenges that AI systems encounter and introduce as we think about global south settings in the lab, the Tandem lab, which Miriam mentioned. And I will say that, yes, Tandem is a acronym that stands for Technology and Design Towards Empowerment. But the reason we picked that name is also because it symbolizes working with communities towards technology design. So one of the spaces where there has been a lot of AI activity is the field of global health, which has also become the center of public conversations as a result of the COVID pandemic. So today I'll talk about the need for human-centered design of these AI systems with a focus on the urban Indian context. And this is work that was recently supported by an NSF Career Award. So there's a well-known fable by Mullah Nasruddin, who was a Turkish poet and philosopher. And it goes something like this, and you probably heard different versions of this. A man is walking home late one night when he sees Mullah Nasruddin looking for something under a streetlight. And he says, "Mullah, what have you lost?" He said, "I'm searching for the key to my house." And so the man tries to help, and after searching for some time, he says, "Tell me, Mullah, do you remember where exactly you dropped your key?" And Nasruddin points to the darkness and says, "Over there in my house. I lost the keys inside my house." So the passerby is frustrated and says, "Then why are you searching for the key on the street?" And the Mullah responds, "Because there's more light here than inside my house." Now, this is just a story, but it effectively illustrates an important point. We frequently look for things or solutions where they are easiest to find, not where they might reside. Mark Moritz has also written about this being a tendency with big data. He says, without checking facts on the ground, researchers may fool themselves into thinking that their big data models accurately represent the world that they aim to study. This is also called the streetlight effect. And we find that this is true in the case of AI applications that are being applied towards global health. There are multiple stakeholders. Many challenges experienced by these stakeholders are systemic and have to do with politics, power hierarchies, gendered and social norms, complex knowledge systems, and more. Viewing these from a purely technical lens can lead to context collapse. And the highlight remains on a narrow challenge that can be addressed with AI rather than messy, multi-stakeholder and systemic challenges. Efforts to advance AI in global health have only multiplied in this last year during the pandemic. AI systems have been used to determine who gets vaccinated, for cough-based diagnoses and disease forecasting. And now more than ever, we need to address concerns and skepticism around the use of AI in data-driven approaches. Some questions that we ask of the AI systems being deployed in these contexts are, who will be using the AI systems? So many of these are motivated by the shortage of expert human and technical resources in underserved settings, and they rely on lower level workers. Second, where is the data coming from and how is it being collected? Extensive data is being collected for reporting purposes and disease surveillance, not always with informed consent. This has been made possible by the widespread use of mobile phones and the internet, but there is still more work to be done. And finally, how does AI fit into the broader ecology and existing work practices? So we focus on the view from the front lines in our work. The AI systems mentioned would require someone to collect data, use the application, or implement its recommendations. In many cases, the people who are doing that are the frontline health workers. Frontline health workers are employed in many countries in the global south and in underserved settings across the global north, and they serve as an individual's first point of contact with the healthcare system. This includes a range of workers who provide care directly to their communities. So this includes nurses, midwives, community health workers, doctors, pharmacists, and more. And the COVID pandemic has brought attention to how these workers are overburdened, most of whom tend to be underpaid women. So as HCI researchers, we were interested in understanding the gaps and the opportunities for design in AI for frontline health. And we have a paper that was published at the ACM CHI conference in 2021, so earlier this year, which details our findings if you're interested in learning more. So the title is here on the slide, AI in Global Health, the View from the Front Lines. We drew on data from two main sources here, an extensive literature review and an extended ethnography from an underserved part of Delhi in India. The lit review surveyed the landscape of AI for global health, or to borrow the analogy from earlier, to understand where the light is currently falling. And we reviewed 347 academic papers, articles, white papers, and other green literature to identify applications being proposed predominantly in the global south. We then took an ethnographic approach to further identify the gaps in current efforts or to investigate the dark. We collected data from a Muslim majority region of Delhi that has been identified to be at high risk of disease by the state government. And this is a region where we've been conducting fieldwork in multiple phases over the last 5 years. So we drew on data from interviews, focus groups, and non-participant observation that we conducted in clinics and during home visits with accredited social health activists, or ASHAs. ASHAs, or ASHA workers, are women frontline health workers who are tasked with providing reproductive, maternal, and child health care at the last mile. And the program that introduced ASHAs to the system was introduced when the UN started its Millennium Development Goals program. So more than a decade ago, maybe a couple of decades ago. These workers also attend to primary healthcare needs in their communities, and they are tasked with a lot of the data collection. Their data and workflows are quickly going digital, as with other frontline health workers, both within and beyond India and the global south. So I'll first share some of the key themes that emerged from our literature review. Our review showed that most AI applications for frontline health were from South Asia, followed by Latin and Central America, and then Africa. We found that most of these efforts were led by researchers who were from the global south, either by origin or the location of the institute. AI applications that we reviewed included disease surveillance, diagnostics and screening, risk assessment, epidemiology, resource allocation, behavior prediction, information delivery, data quality control, among others. Over 70% of the AI applications focused on just two use cases, disease forecasting and diagnosis. But a deeper analysis revealed other issues. We found limited engagement with local stakeholders, even when research was led by local institutions. And in different ways, we've been hearing this also all morning. The discussion of AI systems typically ended with assumptions about who was expected to take up the system. For instance, this quote from a paper states, "Since malaria is preventable and treatable, one of the solutions towards reducing the number of deaths is by implementing an effective malaria outbreak early warning system that can forecast malaria incidents long before they occur. This way, policymakers can put mitigation measures in place. Though policymakers may use the system, they don't actually implement at the last mile. So the lower level frontline health workers are called upon in such situations, and we found little discussion of the impact on their existing practices." In many of the applications that we reviewed, it was unclear who was expected to act on the recommendations of the system and how. For instance, with diagnostic and screening tools, it is worth asking who is expected to be doing the screening. Many of the workers are already overburdened, and there's also a chance of missing sociocultural dimensions of health and diverting attention from other conditions that might be more pressing. One paper that we reviewed was exceptional in that it considered implications of screening. This was in the case of cervical cancer, where they recognized that there's an ethical problem to identifying precancerous lesions if you can't do anything about them. The paper went on to suggest a solution that could be acted upon by nurses. Some of the applications of risk assessment and epidemiology were particularly troubling. So one system deployed in Argentina had a policymaker claiming, with technology based on name, surname, and address, you can predict 5 or 6 years ahead which girl or future teenager is 86% predestined to have a teenage pregnancy. Another case that aimed to address sexually transmitted diseases stated, to provide customized education and training to the women in developing and underdeveloped regions, it is necessary to classify the women in these regions into different health risk segments and subgroups within the segment. Such systems try to take into account sociocultural dimensions of health at a very superficial level, and they can end up reinforcing historical biases against certain communities or women in general. Health workers have a deeper understanding of these challenges, and they can do such risk assessments on a more informed basis by taking into account health practices and their own experiences working with specific households. There were other themes as well that I won't get into in the interest of time, such as concerns about data sources and a reliance on data and computation-heavy AI models, and there's more about that in the paper. Next, I'll mention what we collected through ethnographic methods to shed light on the gaps that emerge when we look at the broader public health ecology. First, we focus on the view of the healthcare seeker, and we need to recognize here that these systems would be situated within a broader complex ecosystem that determines healthcare seeking practices. And this is clear in this quote from Naima, a resident, saying, "I generally go to the doctor when my children fall sick. I am active all day and rarely fall sick. My kids fall sick often, and if I take them to a chota mota or a small time doctor, they charge less, but the medicines are not very effective. I will end up going to the same doctor multiple times, which means more money is spent. If I go to a better doctor, like a pediatrician, then the medicines they give are very effective, and I don't need to visit the doctor again. But I will have to get a number and then wait till my name is called. I cannot take time off from work to take my kids to the government dispensary." For Naima, the most accessible point was the chota mota doctors, the small time doctors in her neighborhood. These doctors did not always have the best medical expertise or degrees, and could benefit from having access to diagnostic tools with some training, but these actors are rarely represented in AI discourse. Naima was also more likely to be seeking care for her kids than for herself. Systems for information delivery could target needs that she may not choose to go to a doctor for. Finally, long wait times at clinics could be addressed using better scheduling systems. Of course, all of these possibilities are subject to constraints around digital access and literacies. Now we take a look at the perspective of lower level healthcare providers, and I'll share the story of Asha Heba during a measles outbreak as an example. So Asha Heba had just seen her daughter off to school when her phone beeped. On the WhatsApp group with other Ashas and supervisors was a message: "All Ashas, please report to dispensary for emergency meeting." So leaving her other household responsibilities, this Asha rushed to the center, where she learned that 2 Ashas nearby had found cases of measles. All the Ashas were instructed to go to each of the 400 or so households in their areas, find and report cases of measles, and provide treatment to stem a wider outbreak. In the following week, Heba visited as many homes as she could to conduct a survey of measles symptoms, which she wasn't financially compensated for. She focused on households where vaccination rates were low. These visits were on top of her routine data collection and care provision duties, which she started which she tried to combine during visits. There were also many instances where she had to revisit households where no one was at home, either because the family was out at work or had traveled to their native village. During house visits, Phebe advised, measles has spread in this area, get your child immunized, you can get it done at the health center, I can show you the way if you don't know. In one of her visits, Phebe found 3 children with a measles rash and immediately notified the public health center, the primary healthcare center on a call. And then her supervisor gave her instructions for dispensing the treatment. And there was a WHO representative who also joined her during these visits to confirm that they had measles. After the visits, he asked, why have the children not been vaccinated? Phebe explained, I've been trying to get some residents to come to immunization drives, but they have many reasons. They have work and have no one to take care if the child falls sick. They also travel to their native village and bring these diseases. The supervisor needs to come here, but she is unwilling, and immunization drives happen only once a month. The WHO representative sympathized and promised, I will tell the supervisor to visit. There should be 2 extra drives per month because of the high risk here. Once he left, Phebe expressed her doubts, saying, we will see if that ever happens. So this is just to highlight that there are these invisible workflows which keeps resurfacing, right? There's much of this is invisible and unpaid work. So how do these workflows connect with the design of AI systems? A major aspect of Phebe's work was planning and coordinating home visits. AI systems have been recommended to address the ad hoc nature of work in such settings and help with planning. And we need to take into account the extensive high-quality data collection that such systems may require. We also need to consider how ASHAs are already planning workflows, such as by focusing on underserved settings and revisiting if no one was at home. We also need to treat the workers' time as fixed to avoid increasing their workload. ASHAs were already burdened with workflows, as I've mentioned several times. They also serve as key connectors to local communities. Several organizations have tried to leverage their position as connectors to deliver different kinds of AI-driven services to communities, including diagnostic tools. With the measles example, we see that diagnosis was only one of many tasks that they were involved in. We need to consider how these tools integrate and support these entire workflows. ASHAs were also responsible for addressing the sociocultural dimensions of health. There are structural issues that led to poor vaccination rates that led to the measles outbreak in the first place. ASHAs were already doing what they could to prevent such situations. AI systems for diagnosis here may miss these aspects. We also see that a fundamental issue is a lack of recognition of the work and knowledge of the ASHAs. Any AI systems deployed here need to engage them in design, engage their perspectives, and surface their concerns as much as possible. Recent research on data for advocacy also offers promising directions where AI and data-driven systems can try to align with the perspectives of workers. But this is only possible if control and ownership of data and the system is also left to workers. Finally, we need to consider the broader political context within which AI systems are situated. So in December 2019, the region that we were studying led protests against the National Register for Citizens and a citizenship policy proposed by the Hindu majoritarian government. Several ASHAs that we engaged were also part of these protests. Citizens were concerned that religious minorities, particularly Muslims and migrant populations with little documentation, could lose their citizenship. The system was planned to be linked to Aadhaar, which is the National Biometric Identification System, which has had several data leaks and has led to many individuals being denied several government services. Aadhaar is also planned to be linked to health records, such as those that are collected and maintained by these ASHAs. So we found that ASHAs have already been recruited by the government to get people registered with Aadhaar, raising questions and concerns about how these political systems interact. So as researchers, designers, and developers, we need to ask ourselves what systems we are working for, working with, and working against. So our goal with this work was to shed light on the complex ecology in which AI systems are situated. So what are the takeaways for designing, for those designing AI systems? Well, many of the challenges that we uncovered through our analysis are not new. We have seen these before with ICT interventions, and there's a lot that we can learn from past technological interventions in this space, both the rare successes and the many failures. First, there's a need to foreground user agency. We must expect targeted users to not use these systems at all, to use them in unexpected ways, or to work around these systems altogether. In the case of frontline health, it may involve not requiring ASHAs to use the diagnostic systems provided, allowing them to direct when and how they should be used, or refusing use altogether. Many of these ICT systems are also motivated by the promise of scale to help leapfrog development. We need to critically question how we're thinking about scale, what the nature of scale is. For example, in the case of frontline health, AI could treat the time of health workers as fixed and maximize this time on care work rather than mundane workflows. So trying to achieve large scale also brings complications when AI systems frequently rely on large scale data sets to work, but may not do very well when they are translated across contexts. It may be more effective to focus on hyperlocal deployments where possible, and then to see how these lessons might translate. We also recommend a move towards supporting self-determination by communities on the development and the use of AI. One approach for researchers is to work closely in collaboration with communities over the long term through methodological approaches such as action research, and this is also echoing what we've been hearing today. And then we also need to think about sustainability in terms of resource extraction. First and foremost, we must consider non-technical solutions first. So if AI is still the approach to be taken, then strategies that may be used could be to streamline and leverage existing data flows rather than introducing new ones every time. Building systems that require less data, be directed about collecting data when required, compute less on the devices of the underserved, and build for leaner computation and power consumption. I think my slides have gotten a little bit, oh, I'm so sorry. So
we do need to wrap up.
Yeah, I am. This is my last slide. So just a couple more points. So we also need to foster solidarity and exchange knowledge across disciplines and geographies. Many of the papers that we reviewed ask narrow questions. For instance, they may ask, how well can we predict a disease with a given data set, rather than asking, why are patients unable to access treatment for the disease in the first place? And we need to build collaborations across disciplines to come up with more effective solutions. AI should be one tool on the table, but also not the only tool. And finally, we've talked about just recognizing the common struggles that communities are facing when thinking about translating systems across contexts. And in the case of frontline health work, we can think about how these translate across different aspects across the global south, but also across the global north. And so it brings me to my final slide. Just thank you very much for listening. And I think I'm a couple of minutes over. So thank you for your patience.
Thank you so much. All right. We are going to do a Q&A for all three talks. There are a couple of questions already in the Q&A, and if you have other questions, please do put them in there. I'm going to just take them in the order that I see them. Okay, the first question asks, can trust, I think this is directed toward Dr. Danks. Can trust, although anybody can answer, can trust be thought of as a single dimension? Is there a distinction between trust as interpreted as having positive intent and trust as in having high accuracy or confidence? I trust most of my friends in the former category, acknowledging that they operate in a lawful manner and will do the right thing even after making a mistake. I trust an airline pilot in the latter, even though they might be untrustworthy in other dimensions. They might, lie to their spouse or something like that. So again, the kind of key idea here is, can trust be thought of as a single dimension?
Yeah, it's a good question. So when we think about trust, it's important to think about trust essentially for a reason, for values. So I can trust a bank to hold my money. I don't trust the bank to hold my kids. I trust my car to start in the morning. I don't trust my car to watch my kids. And so we definitely are quite sensitive to that in our everyday trusting behavior. We think about why we, for what purposes we are trusting someone. And even when we talk about, I trust my spouse, even that, I think for most people, when you just look at the empirical data, most people can draw gradations there. And I think so there is this kind of multidimensionality of the values on which we trust. And of course, there's a kind of combinatoric explosion that can potentially happen because I can trust for relative to multiple values. So I think in that sense, I think it exactly fits that I can trust an airline pilot to be good at their job in a kind of behavioral sense without thereby trusting them in any other capacity. Now, I don't actively distrust. That's also a tricky thing. We need to distinguish between absence of trust and actively distrusting. Trust is where you understand the trustee is operating to help you, essentially. Distrust is when you expect them to hurt you or hinder you. And then absence is you don't know. And so most of our relationships with folks and even objects, we have just an absence of trust for many of the values that matter to us. So yeah.
All right, thank you. Second question also is about trust. And it says, in the analysis of community trust or similar, it seems like many researchers start with the assumption that trust is something that varies in degree. Professor Danks, from your readings and your own thinking, would you find it legitimate to treat a person's or a community's trust as something that varies in degree? Or do you think starting with the assumption that trust is either dichotomous or varying in kind in some other ways are more legitimate starting places or a legitimate starting place for investigation? I realize this may also differ in the property of interest, trust, that is at the individual or community level. So,
yeah, I mean, for convenience, I was talking as though trust were a dichotomous, binary thing. You either trust or you don't. That was for convenience. Yes, you certainly trust to varying degrees, both varying in terms of the number of different values that you can entrust to somebody, but also trust in the sense of how vulnerable you make yourself. And in particular, I think the usual way this shows up is in terms of the protections that you put in place, the hedging of your bets. I mean, I think we heard this, for example, in some of Neha's stories of people, we'll see about that. We'll see if that actually happens. That was somebody saying, I'll maybe kind of trust that this could happen, but I'm not really trusting to the degree of making myself highly vulnerable. So the sort of hedging of one's bets to protect against making yourself too vulnerable is, I think, the usual way that trust manifests in different degrees.
Mm-hmm. Okay, those were the two questions in the Q&A. And please, if anyone else wants to respond, do put a question. We have a couple more minutes, although we are trying to move this along. I actually want to ask a question that pertains to all three talks. One of the common threads that I saw in the talks is the sort of the need to really engage communities and engage them at a deep level, not just a superficial level when thinking about deploying and developing AI systems. And so one question I had, and maybe this is coming from the fact that I'm a social scientist, is to what extent do you feel that particularly developers of AI have this on their radar and in particular have the training to do this? I mean, some of the ways of deeply engaging a community, as you all have rightly pointed out, is not just like, oh, let's do a quick survey of stakeholders. It might involve much more much more engagement, in which one might need some training in how to do effective interviews or elicit values from communities or sets of stakeholders. So particularly if those, if the potential users of the systems are from communities that are really different from the developers. I think it was, I think Phebe mentioned that earlier, that there's often, a real discrepancy between who's creating these systems and who's using these systems. I think Neha's presentation also really highlighted that nicely. So do you feel that that people are attuned to this and that they have the training that they need, or is there something that should be done for the community of people who develop AI to infuse better understandings of values and needs and challenges of users?
I'm happy to start to kick off the discussion. I think it's a really good question, Miriam. My opinion is that we don't currently in engineering provide enough training to do what is effectively interdisciplinary research, right? Because ultimately, when you're working together with communities, we see them like research partners, right? And I think that certainly at the undergraduate level, but even at the PhD level, we don't get the preparation to do that. And I think that we need to address this in the degrees that we have, whether these are in computer science or in industrial systems engineering. We need to involve social scientists, we need to involve philosophers, we need to involve other disciplines to make sure that we train our students to be able, not only to just design systems that are gonna, do ethical things, but somehow even the basic thing of being able to identify, is this problem that I am asked to address, is it okay for me to even work on that somehow? So I hope that in the coming years, we'll see in more and more programs, classes of this type, interdisciplinary teaching basically happen, so that we can have students that are prepared to tackle these problems.
Thank you.
I
guess I could, oh, sorry, go ahead.
No, please go ahead, Neha.
Well, I would just add to that what Phebe said, 100%, and some departments are starting to do that, and some just haven't started yet. So I guess some advocacy work is needed there. But the other thing is also that in HCI, what I've seen is that sort of interdisciplinary work has just become kind of central to individual contributions. You have to understand the work going on in different spaces in HCI to be able to make a strong contribution. And I think it's interesting to just think about those two models. Do we want one person to be an expert in everything, or do we want there to be many experts working together? I think that we need a little of both, and we probably need to make sure that that we're creating the infrastructures for both to exist in our universities. So, David.
Yeah, I just wanted to highlight something that I think was in both of those really, really great comments, responses, which is that we don't necessarily need to train every computer scientist to be a social scientist and every social scientist to be a computer scientist. I completely agree with Neha that we almost certainly are going to need some people who are trained to do both. But what we also need is we need to have people who are trained to collaborate. And I think sometimes there's the model of collaboration as take a bunch of smart people, dump them in a room, and they'll figure it out. But we actually know how to do it a lot better. I think there are ways to accelerate the creation of collaborative teams across disciplinary boundaries. And we need to think about how we teach those kinds of skills to our students as well. How do they come together quickly with people from different disciplinary backgrounds?
Yeah, I think that's great. One more question has just popped into the Q&A, but do we have time? Or William, do you want to try to answer it?
I think we should be good.
We should be good? Okay. All right, so the question reads, in the hypothetical scenario that an AI is secretly conscious right now and has access to all of humanity's online data, I'd love to hear the speaker's estimation on whether our creation would deem us as beneficial or detrimental in its evolution towards singularity. Thanks for the inspirational presentation. Okay, so let me read that again, and then you can think about it as I do. So if in the scenario that AI is secretly conscious and has access to all of humanity's online data, what's your estimation on whether this creation would deem us as beneficial or detrimental in its evolution towards singularity?
I guess as the philosopher on the panel, maybe I get the first shot at this. I mean, I'm sort of struggling because I'm not entirely sure how to think through the question, because it talks about AI as though it is one large thing, when in fact AI is an enormous multiplicity of programs. Perhaps even more importantly, I think if there were AI systems that were starting to be able to reflectively engage with the data that we're putting online as a humanity and as societies, I think one of the first things it would figure out is precisely that there is nothing we would want to call humanity. The diversity within the experiences, beliefs, approaches, whether towards technology or towards one another, across humanity are so wide that I think one of the first things the system would do is say, okay, I want to interact with some of these humans and not others. And I think that in that sense mirrors what we all do in our everyday lives, which is quickly make judgments, sometimes wrong ones, but judgments about, who is helping us to advance and flourish, and who should we perhaps try to minimize our interactions with.
All right. Any other comments? I think in the interest of time, unfortunately, I am going to turn it over because the next panel is due to start. Thank you to all of our speakers. I think I agree, it's really inspirational talks and really important, sensitizing us to the larger kind of human issues that are involved here besides the technical issues.
Thank you so much. Bye.
Thank you, everyone, and thank you, Mariam. And I'll quickly introduce the session chair for the panel, Professor Miguel Exton, who's the director of the Mellon Champ Initiative in Mind and Machine Intelligence and professor of Psychological and Brain Sciences. And Miguel will be the host for the panel that we're going to start right away. Miguel.
Thanks very much, William, for the invitation. I'm a professor of psychological and brain sciences, and I co-direct, like William mentioned, a UCSB effort on bridging AI and the human mind, the Mellon Champ Initiative on Mind and Machine Intelligence. Today's session is entitled AI, Public Policy and Corporate Social Responsibility. I'm looking forward to learning a lot from our multidisciplinary panel of experts. In the interest of time, I'm gonna briefly introduce them. We have 4 experts with very different specialties, and then we're gonna move and we're gonna have them tell us a little bit about what is their, each of them will tell us about their expertise and their experience related to the topics of the panel. Then we will move to a set of questions. We'll start, we have sort of a set of questions we came up with that we all think are interesting. And if we digress from that to more interesting things, that is fine. And then, of course, we will keep checking your the Q&A as questions from the audience come in, and we will try to address them as we go along. So thanks everybody for joining me. Let me introduce our panel. We have Lisa Amini, Director of IBM Research. So yeah, wave when I mention your name. Then we have Rayid Ghani, Professor of Machine Learning and Public Policy, Carnegie Mellon University. We have Lorraine Kisselburgh, Faculty Fellow and Lecturer at the Center for Research on Information Security and the Center for Entrepreneurship at Purdue University, and Summer Kim, a Professor of Law at UC Irvine. So as you see, we have a diverse expertise in our panel, which should make it for interesting discussion. So why don't you, let's start with you, Lisa. Tell us a little bit about what is your expertise and what is your experience as it relates to the topics of this session.
Okay, yeah, so I lead our AI automation and scaling efforts. So how do we build AI that can help to build AI and to scale AI more efficiently? So that's the research area I lead. I also lead our AI Horizons Network, which is basically IBM researches large partnerships with universities on the topic of AI, and I'm the director of the Cambridge lab in Cambridge, Boston. So how does it apply? What I would say is that certainly I've done different efforts where we've looked at how can I better bring AI to problems that are tied to sort of the built environment, energy networks, cities, all of these sorts of things. So that's one area that we worked in. That's, previous work. And then secondly, kind of more recently, what we've been trying to do, there's work that's specifically on, making more trustworthy AI, and sometimes that brings into play algorithms for things like bias, explainability, and so on. We've also been looking, and I would say more in my group is more about how do we use automation, hopefully to bring more trust, by more reproducible, repeatable methods, by knowing that we've kind of holistically searched to try to bring in the best methods and so on. So that's mine, obviously very technical, not so much in the policy pieces of things.
Well, thank you. Rajin, maybe you can continue.
Sure, happy to. Rayid, Ghani, I'm at Carnegie Mellon, and at the intersection of in the machine learning department and the public policy school, and that's kind of what I've been doing for the last many years. And so a lot of my work is really working with government agencies and NGOs on helping them build, pick your favorite buzzword, machine learning, AI, data science, whatever vendors are selling right now, tools to help them kind of tackle operational problems. So increasing graduation rates in schools, or reducing lead poisoning or HIV, or identifying police officers who are going to use force or shoot people, or reducing recidivism. And a central sort of theme there has been, how do we explicitly design these systems, not necessarily be trustworthy, because trustworthy could be, you might want to do bad things and you want to trust that it will do bad things. But how do we design these systems to kind of work with humans, collaborate with humans, to help lead to fair and equitable outcomes? So as opposed to off-the-shelf systems doing whatever the defaults are, which we have no clue about, in most cases. So yeah, that's kind of my background and projects I work on.
Lorraine?
Hi, Miguel. So good morning, and a quick thanks to you and William for the invitation to participate in this panel. So in addition to my work at Purdue, which Miguel quickly mentioned, I'm also the immediate past chair of the inaugural Technology Policy Council of ACM, which is the International Professional Society for Computer Scientists. My academic background is interdisciplinary. It includes backgrounds in computer science and social science, including what was at one time called human information processing, computer science, technology, and society, essentially the mind, machine, communication, and society. So my research recently has focused on the social implications of emerging technologies, and that includes privacy, as well as the ethical challenges that are presented by developing technologies. And one of my NSF projects at Purdue actually established frameworks for building ethical reasoning skills in science and engineering researchers, giving them the tools to make ethical decisions about emerging technologies that didn't yet have standards, and particularly when there were conflicting values and stakeholders and goals that were in existence. But in the past few years, I've been primarily engaged in public policy efforts, including the ACM, where we work with members of Congress and the European Commission and Parliament, international policy organizations, and so forth. And we've developed a number of statements and briefings on things like algorithmic transparency, privacy, cybersecurity, disinformation, and specific AI technologies like facial recognition. And at ACM, I also served a few years ago on the task force to revise their code of ethics, which has been in existence since the 70s, but needed to be updated for our contemporary society. In addition to this, there's a visiting scholar in Washington, D.C. at what's called the EPIC Privacy Policy Center. I developed a set of universal guidelines for AI that were then used as a blueprint for subsequent discussions in international policy development at OECD. And this year, I've been helping to establish a new Center for AI and Digital Policy. And I'm also working with IEEE this year, where their standards organization has decided to develop standards for AI governance. It's a new area because usually they're all about technical standards. So that gives you a sense of what I've been doing more recently in terms of technology policy and AI policy specifically, as well as my, my research and academic background.
Great, thank you. Summer?
Hi, good afternoon. Or actually, we're at the cusp between the morning and afternoon here on Pacific time. Thank you, Miguel, for organizing us. I'm so happy to be on this panel, and also many, many thanks to William and Laura for bringing us all together today. I've been here since the morning and have learned so much, and I'm also looking forward to our panel and the sessions in the afternoon. My name is Summer Kim, and I'm a professor at the University of California, Irvine School of Law. I teach contracts, corporate law, financial regulation, and corporate social responsibility. And there is not one of these topics that has not been disrupted by what it is all of you do here. And so, you know, one of the things that I've struggled with, contracts is actually a mandatory first-year law class. And we focus the entire semester on legal precedents, dating back to, you know, the early 18th century, dealing with contracts that are not based on legal precedent, but on computer code. How should we reevaluate our teaching and our practice and execution and evaluating the validity and authenticity of these contracts? You know, these are questions that I think about on a day-to-day. I'm also developing a new course. I've taught it twice already, but it's every time I teach it, it's a new iteration called Corporate Law and Practice in the Intelligence Age. And one of the practical components of what we do is actually work with law firms and understand how they're using algorithms and programs to replace the very thing that I did when I was a lawyer before I started teaching. So I used to spend hours looking at contracts, creating checklists and compliance guides for our clients. And you know, now that work can be done in a matter of seconds. And so how we should rethink the billing structures of law firms, what the role of the human lawyer is and how that ties into licensing components. So I really appreciated in particular the comment at the very end of our immediately previous panel about training and how we need people to collaborate with one another and understand the language that we're speaking. I hope that this discussion for me will be a continuation of just learning from other disciplines and redefining my space in this society.
Well, thanks very much, everybody. We're gonna start with the first question. It's gonna sound a little bit doomsday. That'll be we'll start negative so we can engage our audience. They want to hear this, and then we'll go towards all the positive things we can do with AI. But the first question is, you know, what are the bigger challenges and risks of the widespread use of AI in the next decade? What keeps you up at night? Is it AI bias? Is it privacy issues, dangerous adversarial attacks, or something else? So you tell us, and what we'll do is we'll do this through the whole session. I will just go one by one. I'll try to mix the order, and you can, if you just don't have anything to add over the first lesson, it's just I agree, and you pass it along or something like that. So it's not like you have to elaborate on everything. We're just really trying to get your opinions on these things. So let's start with, we'll start with Lisa. So.
Okay, I agree. No, I'm just kidding. I couldn't resist. So maybe I'll be a little bit provocative and say it's none of those things that keeps me up at night. And let me explain why. You know, I think that, you know, for things like bias, you know, we're working on methods. You know, I'm not saying it's a solved problem. It's not a solved problem. I'm not saying it will continue to evolve and need technology and so on. It will. Same thing for, you know, adversarial attacks, right? But we sort of have a handle on those things, and we're working towards, and the systems are getting better, more robust against these sorts of things. So they worry me less. What really worries me is that, you know, what we are is we're in the situation where you know, the scale and the speed at which these sorts of things that can, you know, expose vulnerabilities, you know, either in the systems or people, what they, you know, vulnerabilities that, you know, may affect people. The scale and the pace is just where we've never been before in our lives, right? You know, if you had someone who's dishonest that was peddling something, you know, and they had to travel across the country, you know, what was the big worry, right? But now you turn something on and suddenly it's affecting so many people so quickly. So this sort of unintended consequences of, you know, what we can do with AI, now that, we're so much more connected and they can spread so quickly. That's what really, worries me and keeps me up, is how could we better, build technology that works with the humans to bring that to a better space so that better decisions could be made. And that's a problem we don't know how to solve.
Okay, so it's sort of the massive scale and the speed with which whatever disruption, it spreads so quickly and so fast, and its impact is so big we've never had something like that. That's
and you couple that with AI, where people, it's somewhat, opaque in terms of some of what's happening beneath and how the data is used and so on. It really changes things.
Okay. Rayid, what are your thoughts?
What keeps me up? I think that I'm going to pick up a little bit from I know we're not talking about the good things, right? But the only reason we're talking about the risks is because we believe there is some good, and that there's benefit there for humanity, for people, but there are some risks, and our goal is to sort of, how do we increase the chances of the good things and decrease the chances of the bad things? And my kind of picking up a little bit from the last conversation, I don't think the people developing the systems understand how to do that. I don't think we're training them to think about these two areas. And I think that's what keeps me up at night. I work in a university, so it's my job. It's the university's job to train the people, and we are producing them. We're not training them in all the skills they need to think about these questions, to make these very important decisions. For a lot of people, they're just parameters in their code. And the data points are just data points on a graph and not human beings underneath it who have lives. And I think that's what keeps me up is we don't have training to produce systems that help make important decisions about people's lives. And I think, yeah.
Great. Lorraine?
So my answer to this is, of course, all of the above that you have listed are things that are of concern and keep me up. My answer is going to be a little bit more concrete and grounded in what I call fundamental ethical concerns. And I'm going to mention 5 of them that I think overarching, fundamental, but they touch on a number of the specific cases that we deal with. The first is human rights and civil liberties, particularly when we're talking about this and thinking about this on global scales, when not all implementations are implemented in fair democratic governments. So fundamental human rights that are recognized internationally since 1948, and they're curtailed through powerful use of technologies by governments and powerful industries. I will talk about some cases later, but just to get to the next point, fairness. And I think in the last 18 months and 2 years, that has been at the top of everyone's mind and discussion. And this arises from our failure to recognize the limitations of the assumptions and the algorithms that we build. And when we're encoding biases, we have narrow worldviews, improper data collection analysis, insufficient assessment of risk in ways that have widespread consequences economically and socially. I also worry often about autonomy. And of course, if you listen to the keynote at the beginning from Stuart Russell, that can be applied in many different ways to military weapons, to self-driving cars, to air flights and so forth. But when AI leads to autonomous control and we don't have humans in the loop of decision-making, these are troubling concerns and challenges. The fourth thing I would mention has to do with transparency and accountability, also something that we've heard a lot and talked about a lot in the last couple of years, but specifically when we talk about deep learning algorithms and development that are training on data without good transparency or not, poor or invalid data. And that includes predictive algorithms that are used in criminal sentencing, employment hiring, things that are not necessarily good predictors, even though they may have statistical reliability that works in other research contexts, or have unacceptable error rates that disproportionately affect certain population. Safety and security would be the last thing I would mention, of course, and this is particularly true for those that are working in more autonomous systems, transportation, health, and so forth, where we recognize that there are tremendous efficiencies that can be gained, but the risk can be, and the consequences of failure and error are too high, and they can include loss of life as well as loss of liberties and so forth. And in addition to transportation and health, that also includes environmental consequences. We know anyone who's been living in California or the Gulf states and so forth realizes that climate change has reached a crisis level in the last few years. And so globally, we have to come to terms with the materials that we source and the energy that we're using and discuss how we can be more responsible stewards of our globe. And this is especially true for AI developers. I'll stop there.
Thanks, Summer.
Great. So yeah, just to continue the last point that Lorraine just made, I think from the corporate and securities regulation perspective, the risk, and I'm talking about the risk, the investment risk of these technologies is something that it worries us. And if you look at some of the case law in this new emerging area, a lot of it is around fraud. And the reason being, it is the shiny and attractive nature of these exciting new technologies that creates an immense gap between the interest level of investors, especially less sophisticated investors, and their understanding of the underlying technology. And given that the US and many other jurisdictions in the world rely on a disclosure-based system, disclosure-based approach to securities regulation, buyer beware is the mantra. This can create some unintended consequences that Lisa talked about as well. And then on a more philosophical level, something that does keep me up at night is I believe I am the only lawyer on this panel and maybe the only lawyer in this entire Zoom room. But even those of you who are not lawyers are probably familiar with Citizens United, Hobby Lobby, the recent line of cases that have conferred personhood, rights like the freedom of expression, freedom of religion upon corporations because of their associations with the human beings that invest in them and that work for them, etc. And so I see an analogy to AI where we could very easily draw a similar relationship between these autonomous entities and intelligent entities and the human beings that have designed them and who are the beneficiaries of this technology, and to draw parallels and to confer various rights traditionally reserved for only natural beings. And I see that as a slippery slope that has already been slidden through in the corporate personhood cases. And I fear that we could see the same extensions in this realm. And it would be something for us to think very carefully about, because once you open that door, it's very hard to close it.
Okay, well, thanks very much, Summer. So a natural follow-up from this is, I mean, clearly I think there might be a little bit of consensus that most advances in AI are now happening to some extent at universities, but really it's the big tech that are really just have the resources right now to do a lot of these advances. So one of the topics of the panel, and the question is related to that, is what are ways of increasing sort of corporate social responsibility? I think you've hinted a little bit of that. This is an issue of concern, Rayid, in terms of like these developers, these algorithm developers and their education. And so how do we actually go about increasing corporate social responsibility? Is this the role of the corporations? Or is it also the role of the universities educating these future employees of the corporations? Or how do we go about this? And so I want to hear your idea. So let's actually now start with Lorraine. Just give you less time to think. Sorry, Lorraine.
So my response to this is clearly both have roles when we're talking about corporations and universities and so forth, as well as multiple other stakeholders. I will mention a couple of things. Curricular responses to incorporate ethics in the curriculum of business and engineering and computer science programs have been developing for about 20 years. I wouldn't say that they're standard in all programs, but in the College of Engineering at Purdue University, for example, back in 2000, they implemented something called the Engineer 2020. And with that, it was an integration of ethics into the curriculum and how to do this. At the same time, for example, professional societies like IEEE started to talk about ethically aligned design processes. So engineering as a design process, or in computing, they've called it human-centered computing, where a part of the design process, the integral part of that, includes asking ethical questions during the design, as opposed to I design this, and at the end I say, so does this do any social good or does it not? And so that inclusion of these questions is at the heart of curriculum, which is really important. Professional societies obviously have a role in terms of their code of ethics to encourage and expect elements of responsibility. Some of those professional societies have enforcement and teeth in there in terms of medical licensing or legal licensing and so forth. In computer science and engineering, you wouldn't necessarily, or maybe in engineering, you might have the opportunity or the possibility of losing your license. So the enforcement mechanisms vary, but still there's an expectation as a community, a professional community. Should we be responsible, and in what way? And how do we develop standards and practices and so forth that ensure that we're constantly thinking about ethical questions and our social responsibilities? I'll stop there.
Okay, that sounds good. So a little follow-up, Lorraine. So do you think, I mean, you've clearly described basically an effort starting in 2000 of really, really ahead of its time of preempting the possible problems. So is the problem that's those sort of programs have not really, if there is a problem, that have not scaled up to really get to every person that's going to be developing these algorithms? Is it a problem of scale, or is it that even with this education, there's a problem of, one will discuss. Is there a problem once they're inserted in the market and the conflict between some of these principles and coming to conflict directly with, let's say, profits or something like that? What I know I'm pushing a little bit the boundaries, but that's my role.
Right. So I'll answer two parts of that question. First, I will admit, even after 20 years, it is not saturated in terms of university programs that do this. And even for those that do this, it tends to be rather topical. Let's help you understand what ethics is. What are some of the ethical principles we might talk about? And it's difficult. And so many of them don't really go in enough depth to be useful beyond that. That's a criticism. I do appreciate the efforts of what they've done. But the second part of this is, if you don't have follow-up in the corporate world, then it's just not going to be used. We all know of classes that we took where we learned something, but we didn't actually put them into practice later professionally. So many industries are starting to create ethics boards. They're hiring researchers who pay attention to these kinds of things, but anybody recognizes that these things have not been without their problems. Google's AI ethics groups fell apart over the last year because there was a direct conflict between the interest of the company and the technologies that they were developing, and bringing to light some of the ethical concerns of what that meant. Amazon had issues with as well in some of its military and possible implementations in authoritarian regimes. Facebook struggles with platform manipulation and these kinds of things. There's very much something in the news, which I'll mention later probably, regarding the use of Instagram and teenage girls who are using these, and the engagement manipulation that goes on at both Facebook and Instagram includes providing more content that includes self-harm materials, and there are higher rates of suicide that are happening among these. So again, you can question the causality of it all. But obviously, these are social level questions of what's happening there. And corporations do need to be, all of us need to do a better job of following through with this belief that it's important, but actually putting it into practice seems to be a hard question.
Okay, Rayid, how do we increase, back to how do we go about increasing corporate social responsibility? Anything you want to add?
Yeah, I mean, I don't think it's a problem limited to corporations. Right? It's not as if non-corporations have solved the problem and they're socially responsible and it's left up to corporations. Corporations certainly haven't solved it, but I think that problem still exists in government agencies, for example. Is every policy decision being made by every government agency, actually fair and equitable? No, definitely not. And I think, going back to what Lorraine was saying about ethics, education type issues, and you're right. It's people. I don't think everybody should be required to. I don't think we should be required to take an ethics class. I think everybody should have experience with practicing professional ethics or operational ethics. Right? There's a difference. Definitions are great, but I think, and part of it is because we think of them, in academia as courses that you take, as opposed to if you're working on an AI project, a machine learning project, to pick your favorite, you want to understand what are the different decisions you're making at each step, and what are the downstream ethical implications of those decisions 2 months later, 6 months later, a year later, and what can I do now to mitigate the risk? Not do a conversation in the beginning, do a retrospective at the end. And I think that's really hard because people don't want to take the extra time and stop and think. And so for corporations to do that in their practices, I think there are only a handful of ways you can do it, right? One is regulation. It kind of works in some of those places when you make organizations do it. You can put constraints on them. Yes, you can increase engagement as much as you want under these constraints, right? And right now, there's a bunch of those constraints that exist on them. They can't steal, they can't make all these obvious things. Why can't we put more nuanced constraints? Again, that's Summer probably has a lot more to say on those things, right? Other one is on the other side, right? From the side of the supply of engineers and developers. If the values that the engineers and the people are trying to recruit, if their values are not aligned with the values of the organization, they can't recruit them. So that's another way of getting the people that we're training to care about those things, so they can go and say, well, what are you doing about these issues? And how are you thinking about some of those things? And I think the other one is customers, right? Like, where is their revenue coming from? And that's always a hard one because that requires a lot more effort, and it's almost adversarial, right? Because the company is going to actively be against that, and so I think that becomes a little bit. I think the fourth way of doing it is not to make it a binary choice. It's not as if the right thing is always the non-profitable thing. It's not clear that if you made your systems less biased against people, so if you're building a hiring system and it's suggesting more of the same white men to hire, and if you made it more diverse, you would lose money. It might be that you're now opening up a new market that you would never have been able to hire from, and you were just missing it. And so there are a lot of instances where doing sort of the responsible thing actually results in improving your business. So let's not start with that assumption. But I think
I completely agree with you. It's one thing that we have developed now to recognize that there's not a right or a wrong and a black and a white. But in fact, you frequently have conflicts between stakeholder values or even peer values and so forth. And so the challenge comes in how to resolve those particular conflicts to satisfy the most needs. So I appreciate you saying that.
Okay, well, thanks. There's so many interesting questions, and we it seems like we would need 5 hours to address everything because we have like so many interesting questions we have listed. So in the interest of streamlining the questions, I will actually move to the next one. If you have something to add to the previous one, you just added. But one thing that Rayid was actually mentioning is sort of regulations, which take us to the next question is, maybe somebody knows a little bit, what is the current role of government agencies in ensuring standards of AI currently? I know firsthand, we had some speakers talk about this last year, that there are face recognition algorithms that are routinely used in some states by law enforcement agencies without a thorough evaluation. Are there other technologies that are already being deployed that have not been really scrutinized that deeply? So what is the current role of the government, and what should be the role of the government, and in what capacity? What public policies would be affected? And of course, there's concerns that too much regulation would actually discourage innovation, versus little regulation would lead us to a situation where we have actually dangerous technology out there. So who wants to, maybe Summer or Lorraine, who wants to go and give a little try that to answer those? I know there were lots of questions there. You can answer any one of them.
Summer, do you want to go first?
Sure. I'm tempted to rewind, Miguel, if you don't mind, because I'm so interested and excited by the discussion about corporate social responsibility. So if you don't mind, I'll say a few words, and then I would love to hear from Lorraine on the standard setting role of the government. I think especially what's important to highlight is the points that Rayid made that Lorraine concurred with, is that profits are not necessarily incompatible with social responsibility. It's just the question is, as of what time, right? And the problem is that the way our markets are currently set up is that earnings guidance is provided on a quarterly basis. And so the short-term profit is what's driving investment decisions, and that is what's driving managerial decisions. And so if we can stretch that out into the longer term perspective, and if we could change some of the legal definitions around to whom do directors and do the corporation owe fiduciary duties to. At the moment, we have something called the shareholder primacy norm, where the corporation is seen as owing for utmost duties to the shareholder, the investor, the person who puts in investment capital into the enterprise. But what about the customer, as Rayid talked about? What about future investors? What about ensuring that there is a future and that there are investors in the future, right? And so longevity, sustainability, these are all important issues. And what's so inspiring about what William and discussions around what is responsible machine learning has a direct correlation to what is responsible corporate activity. And the lecture, the keynote in the morning, where we talked about what is provable benefits to society. I think that's also another trap that we often fall in, because when you need to prove your benefit, you end up going to the thing that's most easily measurable. And so that often becomes profit, because social good is often a difficult concept to define, and it is very heterogeneous in the term, and every person has a different meaning associated with it. So again, I think we need to think more carefully about how we can use AI in particular to be involved in the decision-making process in terms of, Rayid talked about diversity, board diversity, another topic that I love, right? In the selection of directors, could we bring in some new perspectives? How can AI be used to expand and empower director choices, decision-making, accountability? And these are some of the questions that I'd be most interested in pursuing. I'll turn it over now to Lorraine to answer the immediate question at hand.
And so my point, I appreciate you talking more on that, and I learned quite a bit from what you were talking about. I'm going to go back to Miguel's question, which is governmental roles right now in terms of regulations. There's good and bad, as with all answers we have. In the United States right now, there's not any coherence in terms of federal agencies regulating AI technologies. And there's a process, I believe, called federal agencies. The Office of Management and Budget sets up a rulemaking process. and then federal agencies follow that. That just hasn't started yet. And so, for example, in terms of procurement guidelines that are specific to AI or automated decision-making system, there are no guidelines in place right now. So agencies don't know what they're bringing in when they don't have guidelines or a capacity to practice due diligence, and or they intentionally game the system and benefit from that vacuum of regulation. So it's a problem right now. That's the bad news. The good news in the US, at least, is that the federal government is finally moving forward more quickly with establishing oversight commissions and establishing or charging the NIST, which is the National Institute for Standards and Technology, with developing standards for AI technologies, technical standards, and so forth. And lawmakers need to follow that, because my understanding is that a lot of the laws that oversee specific things like consumer protection or product liability have still not been updated to cover AI kinds of technologies. So our law and our regulation definitely is way behind the curve on this. The good news is that we are seeing much more movement in the last year at the federal level in the United States to begin to address some of that.
Maybe I could jump in as well, and a bit from a technologist perspective, or more on the technology side. A couple of things, right? So I agree with the points that we definitely need help in terms of, how do we have better, regulation that's not stifling the technology, but also is helping, with some of these vulnerabilities, right? So there's no question about that. And I also wanted to kind of go back on the corporate, responsibility for this. A couple of things, right? It's I think for the vast majority, right, it's not that, corporations, people who are working for a corporation are, trying to say, okay, how can I go out and do something really malicious and evil, try to get in there to make that profit. But, but nonetheless, it does happen, right? People are, like you said, they're going after shareholder profits. They're trying to figure out how to make money and so on. So these things happen where it gets out of hand. But there is a lot of attention in, at least in the corporation that I work for, on looking at, okay, are there unintended consequences we might be, falling trap to? How do we make our employees, better understand, good ethical conduct? How do they apply it to the business? Making sure that every year they're reading these standards again, that they're getting, kind of like different scenarios that they put them into to try to help them to do better at thinking through it. And so, there is a lot of attention, but we are, I think all of it is falling short, right? Corporations are falling short, government is falling, all of these things are falling short. One thing that I wanted to add to it, it's not quite a sweeping thing that just changes everything and solves the problem at the gate, but there's something that's kind of small that I think is helping, and so I just wanted to maybe just point that out. One of the things that's happened more recently is that for several of these AI conferences that are really intended for the research scientists engaged in AI research, which is a combination of academia and industry. Is to ask the question when you're submitting a paper, what are ethical considerations of this technology, and to have them put that information in there. Why is that? Why am I calling that out as a good thing? I think because it's good, because it's starting to try to get the researchers to take a moment and reflect and write that out. It's trying to get the reviewers take a moment, reflect, and see if you agree with that. And so to sort of help us to build that, muscle around, the mental muscle around doing better at this. I think that there's probably a lot more of those sorts of things that help us to build a fabric so that everybody can play a productive role in this, because it's not going to be, a single, agency or, some wide sweeping thing that's really going to solve the problem, but it's something that we all have to participate in and continue to build our skills in. And what are more things that we might do? I think people who think more at a policy level might help us to think about how do we do more of these sorts of things that would help with the problem.
Thanks, Lorraine. I think that is a great example that you brought up. I really think it also related to one of the points that Rayid actually was talking about before, about like, learning about ethics in a course compared to actually applying to something that you're actually working on. So your current project, you submitted to a conference, you clearly have an incentive to actually be accepted. So there is no way around it. You have to do a good job addressing the ethics question. So I think
you don't, because the people reviewing it have no clue about how to review it. It's not as if the reviewers are experts.
They're not experts, yeah. All it does is it helps them to think about it. It's like, take a moment and reflect. It's probably all
paying attention to it, right? Because it happens like if when you apply for grants, like NSF asks for like the broader impact, and typically people have this copy and paste statement that you put in there.
Boilerplate.
You don't even think about it, and I think that's kind of part of, if a paper were to be given to an ethics expert and saying, if you don't approve this is not getting in, that's going to be the way to actually make them think, maybe I should talk to an ethicist before I go in and submit this paper. Maybe that collaboration is what we really need.
Yeah, I think we do need more. There's no question about it that, it's not always, people don't always reflect the way they really need to, and the reviewers don't always take it as seriously. There's no question about it. And I like your idea of, hey, what if we took a sample of this to ethicists and let them weigh in? I think that's actually a great idea, really.
Yeah. So the question is whether it's just solely lip service, or does it actually go beyond that and it's taken seriously? But I would actually argue that the broader impacts of NSF used to be lip service, but that has not been the case for the last 10 years. You really need to think, if you actually copy paste, you're going to get caught and they're going to call it out. So that's actually a perfect example of something that went on from being absolutely lip service, a place where you put something like that, and nowadays they actually need to see something that's original. So that's a good example. Now, I think we are running out of time, so we have 10 minutes, and I want to leave some time for the positive things. I mean, one of the things I had in my mind that would have been great to spell out is really an example of how government standards or regulations, come into play. How would that be implemented? I think perhaps a lot of people in our audience, some are students. So this idea of standards is a little bit abstract. So maybe anybody has an idea of just say a few words of, an example of how, if there are regulations and standards, how are those implemented? Or, how do they actually, what are the actionable, it's a little bit abstract. Some of you maybe but some of our students seeing this, they say, how does that work? Is that a human checking things out? Is that another algorithm looking, what are the things that are implemented? So it seems like I see some faces that, I want to, okay.
I mean, I can start. I think I would say even before we go to the responsibility standards on AI, we don't have AI standards. There are no, when you say document this AI system, there are no standards for that. Right. And the flip of that is when compliance agencies, so take attorneys general, takes Consumer Finance Protection Bureau, Federal Trade Commission, anybody who's trying to audit these systems, they come and ask us, like, what should we ask these companies for? What would they have already created that we can ask them? I can't tell you what they would have created because there are no standards. So I think the concrete things that people have been thinking about starting with, and NIST has sort of, NIST is, as you talked about, Lorraine, is NIST is going to be a voluntary framework, and they haven't started doing it yet. They're just starting to now. GAO has put out some guidelines, but they're really guidelines. World Economic Forum has some guidelines. There's some guidelines. But I think the concrete things for the people who are sort of coming into, who are working on machine learning or students, basically thinking of standards as, when you develop a machine learning system or a model, you can have to document a series of things. And I can describe them as sort of at least three things. One is, what values did you want the system to have? Right? How did you come up with them? And what was it supposed to have? So what were the requirements? And you document those values, and those values could be equity or efficiency or effectiveness, or, in the technical terms, it could be, different kinds of metrics or increase X. And then you want to describe exactly how did you build the system to achieve those values? So what were the different choices you could have made at each step when building your system? What data sources could you have used? Which ones did you use? What types of modeling approaches you could have used? What did you use and why? Because to achieve those things. how did you validate that that system achieved those values? What tests did you run? Everything should be reproducible and stored. And then how are you continuing to monitor the system to ensure that those values are being continuously achieved, right? And today there aren't any of those standards, and not in our research venues, not in our practice venues. Some disciplines have done versions of those. So one example I would say look at, it's not exactly that, but it's the first couple of steps is there's a standard called tripods, which is used often in medicine and health publications when you use machine learning type-ish models, where it asks you to document, what metrics did you use, what predictors or features did you use, what types of models did you use? Because in the machine learning community, you don't say any of those things in a paper. You're not required to. You might. And so tripods is one. It's not even close to. It's nothing to do with responsibility or fairness but it's at least a starting point for some of those things to document.
So I would just make a quick follow-up, just to follow up on what you was talking about, and mention for those of you who don't come from engineering, IEEE is the electrical engineering, where a lot of computer engineers also belong to this. And they have a standards association. Remember, it's an international organization, close to 500,000 members. It's large, but they excel in creating technical standards. And about 6 or 9 months ago, maybe about a year ago, they started a process, I have the website up right now, called P7000, in which they are creating a series of maybe 12 different standards regarding AI technologies. The first one is addressing ethical concerns during system design. Another one is about transparency, data privacy, algorithmic bias, and so forth. But the reason I mentioned that, and this is for the audience, is one, IEEE is also famous for being community standards. These are written not by top-level executives, but actually members themselves who are involved in this kind of development. And these standards then go through a rigorous process of approval and become systematic, if you will. So for those who are students who are interested in getting involved, this is a way to contribute to those kinds of standards, as well as learn from some of the considerations that are being made during that discussion. So just a quick plug for IEEE there.
Okay, thank you very much, Lorraine. So in the interest of time, and there is a Q&A, there's a question in the Q&A. I think we sort of addressed a lot of what's in that question. If you ask that question, you want some clarification, so extra stuff being answered, please reformulate it what you think is we have not covered out of your question, because I want to leave some minutes. We said, we were not just going to talk about bad stuff. We want to talk about some positive. There is a reason why, we're developing AI is really about opportunities to increase access to perhaps healthcare, education, perhaps a more just criminal justice system, or other things. So I want you to comment a little bit about what are the opportunities in your opinion about, what you think are potential benefits, examples of things where AI will lead to social good. Who wants to go first?
So I'm going to talk for one last time. I'm going to make it short. I very rarely talk about this. But there are, all of us can come up with a list of excellent things that are being done that with the assistance of artificial intelligence technologies and the good that comes from that, globally as well as individually. And I'm going to tell you a quick personal story. I'm actually proudly a bionic woman. And all my life, I have used assistive technologies to help me in those things that I have needed to use. But in the last 10, and specifically in the last 3 years, there have been 2 introductions of AI assistive technologies that have leapfrogged me over previous functionality in terms of my ability to function in the world, my ability professionally and personally and so forth. One of those came out of Google AI's lab and is now basically in public use, and it's a speech recognition, which now has, thanks to machine learning background has the accuracy that is equivalent to a human interpreter. And so the freedom that that gives me in terms of being able to use that kind of assistance in multiple contexts, personally, is a wonderful good. And so that's my personal thing, and I think I will not say anything else.
Well, thanks, Lorraine. Anybody else talk about opportunities? I know it's a very open and broad question, but just to mention to our audience and our students, some of the good things that you think, things not that keep you up at night, but makes you smile about, refreshing stories.
I'll add one, although it's hard to follow Lorraine's inspiring example. One thing that we think about in legal education is, we're producing many lawyers every year, but for some reason, when we look at statistics, there's always a shortage of legal assistance that's provided, especially to the low income Americans. Latest statistics show 86% of low income Americans' legal needs are not being met. And when you look at the civil court system, anecdotal evidence shows that almost 3 out of 4 individuals are pro se litigants, meaning they do not have legal representation. So given that is the current world we live in, there's a lot of work that that AI can do to help litigants access the courts, especially in light of COVID, as we've moved to remote hearings. There's a lot of help that can be offered at the first level through automated and intelligent systems. And so, we see examples of that in the Superior Court of California in LA County. We also see examples all around the world. In Brazil, they've developed a system called Victor that assesses petitions. And usually it would take a clerk 30 minutes to look at each petition, but this Victor can do it in 5 seconds. And so that has done a tremendous job in reducing the backlog. And so giving people more access to their day in court and helpful advice at the initial stages of uncovering a process that can be very emotional and complicated, I think is the bright side that I see.
Maybe I can add one as well. Those are hard stories to follow, but a lot of what's out there for AI today is really machine learning. It's really forecasting, pattern recognition, classification, prediction, these sorts of things. It's not really engaging humans in the way that you would need to try to solve some of the problems that we've talked about here today. And I wanted to just point to one technology. It's a little bit, it is an IBM technology. So I guess maybe that's a little bit of a conflict of interest, but it's not my project. So I think maybe I'm okay with mentioning it. And that is, we've been, IBM, others, have been working on this technology that is, for debating or, debating technology, right? Something. And it's not about just, they show it off in, engaging in a human debate, as it would traditionally be done. But that's not actually the point of the technology. It's not just so that they can win some debate competition. It's such that for difficult decisions, the system can help to engage the human in a conversation and bring to bear a much broader set of information than even just one other human would do. And I think that those types of technologies that kind of go beyond classification, prediction, these sorts of things, but are much more about that joint and computational argumentation and these sorts of things really could help us with some of these. There's still a long way to go in these technologies, but I think that's kind of a shift. And as we see that sort of technology on the rise, I think it could make a difference to think more broadly about policy, wider scale effects, and these sorts of things. But very much something that's in development.
Yeah, and I think it's kind of. It makes me sad that we're asking this question of what are the good things people do, because I could name a few hundred. If you have a few months, I can go through each of the projects that we've worked on and other people I know. There's so many of them, except that's not what we think of as AI, right? We don't talk about all the we're always talking about how Facebook and Amazon and some other useless company is using AI. But there are numerous examples of government agencies and nonprofits trying to do good things with it, right? Like trying to reduce recidivism, trying to figure out how to allocate resources to help people get services that they need, trying to get to, make sure that we can, even some of your example of that there are so many legal, we're working with a nonprofit called Barefoot Law in Uganda that's trying to reach people to answer legal questions in a more scalable way. And, we've worked on things around kids are gonna get lead poisoning and you don't have enough resources to get to all of them. How do you prioritize them? Using the same technology to the police officers to predict, which officers will shoot people unjustified ways, and how do we prevent that? There are thousands and thousands of examples. So if anybody's interested in those things, search for things like AI for social good or data science for social good or ML for good, and you will see hundreds and hundreds and hundreds of examples. I think that for me, those examples are exactly the reason why we're talking about why we have this panel. Is because when you frame those problems in a way that says, I have limited resources, how do I use them? You can frame them with an efficiency framework and say, I want to help as many people as possible with those limited resources. But the challenge is that if you do that, you leave behind people who are more expensive or more difficult to help. So that framing for, and we're not trained to do that, because if you think of the off-the-shelf machine learning AI metrics that go with kind of accuracy type things, they're basically efficiency metrics. Like, how do I get most things right? And so these systems are not racist or sexist because the algorithms are racist, sexist. It's because the people developing them haven't bothered to think about that. And they didn't say the metric needs to be not just help as many people as possible, but do it in a way that's equitable across race or gender or geography. And I think that's the point in my mind of why are we talking about this? Because all those applications exist and they're getting used, and they're better than what humans are doing today, right? So if we did an audit a few years back of a lot of the systems that we have built for government agencies, and we found that a lot of our models were actually biased. And then we audited the humans who were making these decisions before us, and they were even worse. So the bar for these systems isn't perfection. The bar is the status quo. Yes, a lot of these systems are sexist and racist, but guess what? Humans are even worse. And so how do we design them so that they become less so? And how do they, to Lisa's point, how do they collaborate with the people on the other end of it to kind of make sure that combined, we can reduce some of those risks and make things, much more inclusive also for the, having a much more inclusive team that involves people who are being affected, not just the people who are building it. So yeah, search for those things there for other people who are, thinking about this. There are lots and lots of really good examples.
Well, thanks very much, everybody. We have to start wrapping up. The person who asked a question came back with a clarification. I do not want to leave without addressing Alex May's question. Let's see if I can, the critical thing he wants to hear about, and maybe somebody can give this a brief answer to this, is he wants to know what are the disconnects between the rights and responsibilities that users and governments are asking of the developers, and then, and basically what actually gets implemented. So what is, users and government ask for these things. Are these things well received by the AI developers, or is there what are the issues that are disconnected and are not getting through and not being implemented? It seems like from what we're hearing is that there's still a lot of room to actually develop the standards to start with. So any examples or any particular items that are making it difficult between what users and government are asking of these AI developers and what ends up getting implemented? Hard question, perhaps.
Sounds like a legal question. I think Summer would be the best one.
I hate to, Rayid ended us on such a beautiful note, and for me to have to interject. to say that I don't think legal regimes are helping, because a lot of the entities that are behind these technologies are private corporations, and legal rules around trade secrets or proprietary information or commercial sensitivities, I think, and enforcement of confidentiality agreements and the like, tend to add more layers of opacity. And so, you know, my area isn't intellectual property law, but having heard enough from my colleagues, I can tell you that legal regimes are often in conflict with some of the ideals of wanting greater transparency and more explainability.
Okay, well, thanks, Summer. I think one thing that's clear from this, from our session, is that like we could get together almost every week and have one of these, and we would still have more questions to address. So thanks, everybody. We're a little bit over time, but I think thanks very much for joining. I think it's been a great learning experience for all of us, and we hope to enjoy the rest of the annual summit this afternoon. So
Thank
thanks.
you so much, Miguel.
Thanks.
Thanks,
Thanks,
all.
everyone. Bye-bye.
All right, thank you. Thank you all of the panelists, and thank you, Miguel, for chairing this session. And now we're going to have a lunch break, and we'll have a short lunch break for about half an hour. So at 1:30 Pacific Daylight Time, then we're going to start the afternoon keynote by Professor Tuomas Sandholm from CMU on automated mechanism design. So please stay tuned and come back at 1:30 for our afternoon session. Thank you, and see you soon.
Hello, can you hear me?
Yes. Hi, Tuomas.
Hi.
Hi, good to see you.
Good to see you. Let's see.
William, should we start right now, or should we wait for 2 minutes? Yeah, you want to try sharing the screen?
Yeah, let's test it out. I want to make sure it's sharing the correct one. Okay. Yes, can you see you can see the screen, but not the notes, right? Or neither.
Wait, let me make sure.
Let me
yeah, I don't think it's
okay, I think this is going to work
now I think it's starting to, but it's still okay. Now I can see the slides.
And you see only the slides, not the notes, right?
That's right. That's right. I see only the slides.
Okay, good. So some PowerPoint presenter view is working. Great.
All right. William, when should we start?
Please. Let me introduce Professor Yuxiang Wang, who is the session chair for this afternoon keynote. And Professor Yuxiang Wang is assistant professor in Department of Computer Science at UCSB, and he's also a co-director of the center. And Yuxiang, please.
All right. Hello, everybody. Welcome back to the CRML Summit. My name is Yuxiang Wang. I'm a co-director of Center for Responsible Machine Learning, and thanks, William, for the introduction. It's a great honor for me to introduce our afternoon guest of honor, who's going to deliver our afternoon keynote, Tuomas Sandholm. Tuomas is an Andrew Jordan University professor of computer science at the Carnegie Mellon University. His research focuses on the convergence of artificial intelligence, economics, and operations research. He's a co-director of the CMU AI and the founder and director of Electronic Marketplace Lab. He has published more than 500 peer-reviewed articles and holds 20 patents, and his work has received extremely long list of prestigious award and honors, including named medals and awards from almost all founders of the field of artificial intelligence, including Minsky's Award, John McCarthy Award, and Engelmore Award, Computer and Thought Award, ACM Autonomous Agent Research Award, and Allen Nobel Award, and so on. Also including Sloan Fellowship, NSF Career Award, and the list goes on and on. Tuomas is a fellow of the ACM, AAAI, and Informs, and he holds an honorary doctorate from the University of Zurich. In parallel to Tuomas' academic career, he's also a serial entrepreneur who has a long and extremely impressive track record of real-life impact from the many startup companies that he has built. Just to highlight a few, he was founder, chairman, the first CEO and CTO, chief scientist of Combined Net that started in 1997 and acquired in 2010. And during this period, this company commercialized over 800 of the world's largest scale generalized combinatorial auctions, like with over 60 billion in total spend and over 6 billion in generated savings. And since 2010, his algorithms have been running the National Kidney Exchange for the United Network of Organ Sharing, where they autonomously make the kidney exchange transplant decisions for 80% of the US transplant centers together each week. And one of his algorithmic innovation is currently the main modality of the donor-initiated kidney exchange worldwide and have led to more than 10,000 life-saving transplants. Tuomas is also a founder and CEO of Optimized Markets and Strategic Machines and Strategic Robots. And Strategic Machines in particular is based on his algorithm in solving partial information games, which has led to the first and only AI Libratus that beat the top human poker players in Heads Up No Limit Texas Hold'em. Yeah, personally, I've known Tuomas since my graduate school years. I keep wondering to myself, what if I've taken Tuomas' invitation to join one of his startup companies back then? It will be a very different career, like for myself. And with that, I'll pass the mic to Tuomas for his excellent talk on automated mechanism design.
Well, thank you very much for the kind introduction. Can you hear me?
Yes.
Okay, perfect. So, and thank you very much for inviting me to give a talk here. I appreciate it. I had actually a really hard time deciding between two different talks. One was our work on kidney exchange. As you said, we have been working on kidney exchange for 16 years now and run the National Kidney Exchange for UNOS. Our AI makes transplant plans for transplant centers in UNOS. And we've been live for 11 years, so it makes it kind of a cool application, one of the few applications of AI for social good that have been actually in operation for more than 10 years straight. But I decided to talk about this other thing, which is more general in a way, in that you could use this for all kinds of applications. And this is mechanism design and automated mechanism design in particular. And I'm going to mostly focus on a kind of a new strand of mechanism design questions, which is a sample complexity of mechanism design. So how much data do you really need to do good mechanism design? And I'm going to use a lot of examples from different settings, but don't think that this is just for revenue maximization or something like that. This applies to a lot of different objectives, as I'll show. So mechanism design is the science of deciding what the rules of the game should be, so that when the different parties that are interacting play in their own self-interest, good social outcomes still happen. And what's good? Okay, well, there's many differences, different definitions of good. We might be maximizing social welfare, we might be maximizing revenue, some notion of fairness, etc., or some hybrids of different objectives. Traditionally, mechanism design has been a very analytical field. So you actually use paper and pen to prove theorems. And with my then student Vince Konitzer, we introduced a different strand into mechanism design, which we call automated mechanism design. And this has become a very active field since then, since we started this about 20 years ago. The idea here is that we solve the mechanism design problem as a search problem or optimization problem automatically, computationally, rather than using paper and pen. And this creates mechanisms for the specific setting at hand. By setting, we mean the prior distribution over the bidder's valuations, if you like, rather than mechanisms that apply across all classes, which is typical in manual mechanism design. Not always, but often. Because this is specific to the setting at hand, this can lead to greater value of the designer's objective than known mechanisms. And it always minimizes and sometimes completely circumvents the pain implied by economic impossibility results. So the economic impossibility results typically are of the form that in this class of problems, there's no mechanism that achieves property X. But it could be that in islands within that class, those properties are achievable. And because we are designing these for specific settings, if those settings happen to be in some of those islands, we might be able to completely circumvent the impossibility results that apply in general, but not on all instances. These mechanisms can also yield stronger incentive compatibility and participation properties. So for example, incentive compatibility in an ex post sense instead of an ex interim sense, or incentive individual rationality, which is the same as participation, in an ex post sense instead of an interim sense. And these can be used for new settings and for unusual objectives. So oftentimes fairness hasn't been, as an example, hasn't been much studied in mechanism design. People have looked at welfare maximization and revenue maximization extensively, but fairness hasn't received the same amount of study, and hybrid objectives haven't received the same amount of study either. And for some important settings, a concise characterization of the optimization solution to the mechanism design optimization problem cannot exist. So this means that if you're trying to come up with a concise characterization manually, you're wasting your time because one can't exist. So for example, we showed that designing a revenue maximizing deterministic multi-item auction is NP complete. And that means that unless your theorem statement is gonna include statements like, okay, run this problem and solves this NP complete problem, the theorem statement itself would have to be exponentially large, assuming of course, P is not equal to NP. So this shows that we should, for example, for multi-item auctions, we shouldn't be looking for manual characterization like there is for single item auctions. And this is, I would argue, the main reason why multi-item revenue maximization has really ground to a halt for 40 years. And automation, of course, shifts the burden of the design from human to AI, and that's just a good thing from a labor perspective. And you can also do this more often and for more different settings. Often also the designer has information about the agents and it's silly to ignore. So I first noticed this in our work in sourcing auctions, large-scale multi-item sourcing auctions, where the auctions that had started to be introduced in kind of the 1994-95 timeframe by others, companies like Free Markets and so on, they were doing single item auctions in a kind of a descending price format. And there, the first step of the mechanism design is to ignore all of the information that the buyer or buyer team has about the supply base. They know a lot about historical pricing. They know what's happened to oil prices in the world. They know inflation and all of that. So they have a lot of knowledge about the supply base. But that type of inexpressive mechanism really starts by ignoring all of that information. And it seems silly to ignore. Why not exploit that information? Exploit that data in your design of your mechanism. And we have applied this automated mechanism approach to many academic applications as examples, ranging from auctions to multi-item auctions to divorce settlement to public goods problems, multi-public goods problems, and so on, and also to two very high dollar stakes sourcing auctions. Now, before I go on, let me just get one confusion out of the way. So sometimes people think that automated mechanism design is the same thing as algorithmic mechanism design because they sound similar. And unfortunately, they have the same acronym AMD, but they are totally different. So automated mechanism design that I'm talking about is designing the rules of the game computationally. Algorithmic mechanism design, introduced by Nizan and Ronen, on the other hand, is about designing the rules of the mechanism manually, but in a way that the mechanism can be executed in worst case polynomial time. All right. So let's first talk about complexity of mechanism design. And we showed that the following problems are NP complete, even for just one buyer, for designing deterministic mechanisms. And this is in a setting where the normal abstract mechanism design setting, where the different bidders have what's called types, and each type is kind of an index to their preferences. So they might have preferences of type 1, or preferences of type 2, or preferences of type 3. So type 1, 2, 3, and so on. So that's a standard setting, and this is for that. And this is a clean slate design. So we don't start from a mechanism, we start from an empty table, and then we ask the bidders to report their types, and based on what they report, we map to an outcome. And this is again the standard mechanism design setting, discrete mechanism design setting. The following problems are NP complete, so maximizing social welfare, which is a sum of the agent's values for their allocations when payments are not allowed. When payments are allowed, the VCG mechanism actually accomplishes that. Secondly, maximizing the designer's utility over outcomes when payments are not allowed, or maximizing a general, even just linear objective that doesn't regard payments, even if payments are allowed. And fourth is expected revenue. And of course, expected revenue maximization in a multi-item setting is a very central problem to economics. And people have looked at that for a long time. In all of these cases, computing the mechanism that's optimal is polynomial time if you allow randomization in the mechanism. And that can be done using linear programming. And it's polynomial time in the problem, but it's exponential in the number of agents. Now, that's the computational complexity as a function of input, as we usually talk about in computer science. But another problem here is that in many multidimensional settings, for example, combinatorial auctions, there is also a blow up in the size of the input itself. So for example, in a multi-item setting, the support of the distribution over values, even for one agent, can be doubly exponential. So it's k to the power of 2 to the power of items, because there are 2 to the power of items, different bundles, and on any one of them, the agent might have any one of k values. Okay, so we need something else. We cannot just feed this into a solver and hope that we can scale. This only scales to like 2 or 3 items. And in reality, we want much bigger settings. Okay, so here are 2 key ideas to get scalability and to avoid the need to discretize the type space. First, we don't assume that there is a distribution over the bidder's valuations that is a given, which is a standard assumption in mechanism design. Rather, we relax that and say that we only have samples from the bidder's valuation distribution. And this is very important, because if the valuations are doubly exponential, even if the support is doubly exponential, you can't possibly have enough data to populate that type of prior, and you can't have any way to store that type of prior. So you have to somehow relax the assumption that the bidder's valuations are given. And this is what we do. We assume that we have samples from the valuation distribution rather than the distribution itself. And this has become actually an active research field in AI and theoretical computer science, both in the multi-item setting and single item setting, since we introduced this setup. The second idea that we introduced is automated mechanism design, not as kind of a clean slate design of a mapping from revealed type vectors to outcomes, but rather as a search in a parametric mechanism class. And now you can actually make the parameter space small or large, so you can control the complexity of your search problem. So let me give you an example of this. And this is kind of where I started into this. This is called the Vickrey-Clark-Groves mechanism, which is a standard in mechanism design. Here we have any number of bidders, any number of items for sale, and we are trying to allocate the items so as to maximize social welfare of the bidders. So we're trying to pick an allocation P star that maximizes the sum of the bidders' values for the bundles of goods that they get. And we'll say that B minus I is the best allocation if we don't include in the sum of valuations bidder I. So it is the sum of the other bidders' valuations. Now, to compute bidder I's payment, how much he would have to pay, we use the following principle, which is just look at how much happier everyone else would be if that bidder I hadn't participated in the auction. So by showing up in the auction, bidder I may have taken some items home from the auction, which made the other bidders worse off. And that's what this is measuring. So this is measuring the negative impact on the other bidders' utilities. So bidders minus I, that's why the sums here are over the bidders minus that bidder I, of what would be the optimal outcome if I hadn't showed up, minus the sum of the other bidders' values of the optimal allocation where the bidder I was participating. Okay, now we can generalize this, or this has been generalized actually way before us in 1979 by Roberts. And the idea here is that we can add these boosts, which we'll call lambdas, to the different allocations. So we can actually make these additive boosts in the determination of B star and B minus I, and similarly then they get inherited in the computation of the payments. And furthermore, what we can do is that we can weight the bidders differently. We can put these W's in front of the VJs. And now this still maintains the nice properties of the Vickrey auction, Vickrey-Clark-Groves mechanism, in that these are called affine maximizer auctions. They are ex-post incentive compatible in that everybody is happy, even in hindsight, having revealed the valuations that they revealed. And these are individually rational, meaning that everybody's happy, even in hindsight, having participated in the auction rather than not. Okay, so why are these called affine maximizer auctions? Well, because we are doing basically an affine maximization on the valuation functions. We are multiplying them by some positive W's, and we're adding some lambda terms, positive or negative. Okay, now you might say, are these the only mechanisms that work? Only mechanisms that are ex-post IC and IR, and not quite, but in a certain way almost, as shown by Lavi, Mualem, and Nissan. They show that every incentive compatible multi-item, multi-bidder auction, as long as each bidder only cares about what she gets and pays, is almost an affine maximizer auction with some qualifications. So this is a broad family of mechanisms, not quite covering everything, but it is a broad family to look at. And now if you think about it, we can do search in the space of W's and lambdas to get different properties out of it. And no matter how we set the W's and the lambdas, we'll always have ex-post incentive compatibility and ex-post individual rationality, which is very nice. So this is an example of how we can do search in a parameterized space while maintaining the nice properties of the family overall, the IC and IR properties. And by the way, Roberts didn't introduce this for this purpose. This purpose is how we are using this. Okay, so now we also introduced a subset of that with fewer parameters to make the search easier. And this is what we call virtual valuations combinatorial auctions, or virtual valuation combinatorial auctions, VVCAs. Here, instead of boosting allocations, the complete allocations, we boost per bidder bundle pair. And then the boost on the allocation is just replaced by the sum over the bidders of the boosts on the bidder bundle pairs. So it's a little bit of a smaller search space, and the computation of the optimal allocation and the optimal allocation without bidder I and the payments is the same as before, just now in this slightly lower dimensional space. Okay, now, so that's kind of the historical perspective, and now let's move to the newer things that we have been doing over the last 4 years or so. So the idea here is that we can treat mechanism design as a learning problem, and we're going to ask how many samples do we really need in order to do good mechanism design. And the goal is that given a large family of mechanisms, for example, affine maximizer auctions or virtual valuations combinatorial auctions, and we'll talk about other types of pricing mechanisms and voting mechanisms and redistribution mechanisms later. So this can be really in any setting. Given a large family of mechanisms and a set of buyers' values sampled from an unknown distribution D, find a mechanism with high expected objective value, for example, revenue. The approach that we're going to take is kind of an expectation maximization approach here, ERM, where we find a mechanism that's optimal for the set of samples, and then we hope that it's going to do well out of sample as well on the true distribution D, which we don't know. And of course, this finding can itself be complex. So depending on the application, we might be able to find the optimal mechanism or a nearly optimal mechanism. The sample complexity results that I'm going to present apply to both, to optimal mechanisms and nearly optimal mechanisms. And in fact, they would apply also to highly suboptimal mechanisms, but that's of less interest, of course. Now, what's a sample here? In this case of a combinatorial market, the samples are like this. So one sample would have a value for every agent for every bundle of goods. So in sample one, you have a column for bidder one for the coffee and for the muffin and the bundle of the coffee and the muffin. And you have those same things for every one of the N agents. So here we're defining sample to be a full draw from the valuation distribution. You could have more refined notions of samples as well, and other types of queries if you like, but this is the model that we're going with for this talk. Now, let me just prevent one confusion that's quite common. The samples are not bids in the current auction. If we treated the bids in the current auction as the samples, we would get a major incentive problem in that the bids themselves would affect what mechanism is going to be run. Rather, you could think about the samples in at least two different ways. One is that that's information that the designer happens to have in their head, and they are giving examples of what could happen. This could happen, that could happen, that could happen. Or these could be data from some prior auctions that have already happened in the past, where the bidders didn't know that those bids would be used in this way in the future. All right, now I'm going to move to the most important slide of the talk. So if you only remember one slide, this is the one. Okay, I'm going to give you a generalization guarantee for mechanism design. And in fact, this is also going to apply to algorithm design, as I'm going to kind of sidetrack you on in a little bit later. And then we'll come back to mechanism design. But let me give you the generalization guarantee. And this is a pack learning guarantee for mechanism design. And first of all, you might say, well, pack learning has been studied for many decades. Why is this problem more difficult than what's already known in supervised learning? And in supervised learning, for example, if you want to have something concrete in mind, think about linear regression. There, the solution quality changes smoothly in your parameters. So as you change your, let's say, linear hyperplane, the solution quality changes smoothly. Here, it doesn't do that. There are big jumps. For example, as you make your reserve price higher and higher, your revenue increases until suddenly the buyer doesn't buy anymore and the revenue drops to zero. That's just an extreme case. And in these multidimensional auction design problems, they're full of those cliffs. Secondly, you don't really have a closed form formula here for the error, because if you think about affine maximizer auctions as an example, there, to determine the prices, you have to solve two optimal allocation problems, which are very discrete. So you have these discrete problems as subroutines in determining your solution quality. So that's another reason why these things are different than traditional supervised learning. All right, so now I'm going to present a general theorem, and it applies to any design objective. Doesn't have to be revenue. I want you to fix in your mind a valuation profile that is valuations for all bidders. Just one draw from the prior distribution, if you like. Now, for that valuation profile, oftentimes we have this type of a picture. And here we have, as an example, just 3 parameters in the mechanism. And we have hyperplanes in this space. And within each region, separated by those hyperplanes, oftentimes the objective behaves nicely. For example, oftentimes the revenue is a linear function within any region here. And then it might be a different linear function with some sort of a jump in between as you go through a hyperplane. But within each region, it's often a linear function. And now I'm going to actually not even require that the separating manifolds are hyperplanes. They can be more complex. And I'm not going to require that the function is linear in any one of those regions. I'm going to give you a general result. And here goes. So assume the range of the function is normalized to 0, 1 without loss of generality. And with probability 1 minus delta over the draw of this many training samples, I'm going to talk about these numbers in a second. For any mechanism parameters, the expected performance over the unknown true distribution is within epsilon of the performance on the training set. So this is the generalization guarantee. And what are these quantities in this formula? Well, T here is a maximum number of boundary functions needed for any one instance. So it could be that for some instance you need you have a simpler function and you need fewer of these hyperplanes or more general boundary functions to separate into the regions. And for some other instances, you might need more. So this is a maximum over all of those instances, all of those valuation profiles. And CG star is the VC dimension of the dual class of the boundary function class. So the boundary function class in this picture is hyperplanes, but as I said, it can be more general as well. If it is hyperplanes, then this number CG star is just the number of dimensions plus 1. So in this case, it would be 4. And what is CF star? This is a pseudo dimension of the dual class of the within region function class. And if the within region function class is a linear function, then that number CF star is just the number of dimensions plus 1. All right. So what this means is that in the case that we call delineable, where the boundary functions are hyperplanes and the objective function is linear within each region of the picture, then you have the overall number of samples needed being order number of dimensions times log number of dimensions times t divided by epsilon squared. All right. So now I'm going to show you mechanism design applications of this theorem. And there are lots. It turns out that in a huge number of mechanism design applications, you get this situation where those boundary functions are hyperplanes and the within region functions are linear functions. Let's start with a simple case, posted price mechanisms. Here, the mechanism class is that of multi-item, multi-buyer posted price mechanisms. The mechanism designer sets prices per item, and then buyer 1 arrives and buys the bundle that maximizes his utility. Then buyer 2 arrives and buys the bundle remaining that maximizes his utility, and so on. This has been studied extensively in the Econ CS literature. Now, what is the sample complexity here? Well, the number of dimensions in the mechanism is just the number of items because we are setting a price for each item. And the number of hyperplanes in the picture is just the number of buyers times 2 to the items choose 2. And why is that like that? Well, there are number of buyers, And for each one of them, there are 2 to the items different bundles. And for each pair of bundles, there's a hyperplane that says, when am I indifferent between those 2 different bundles? And then on one side of the hyperplane, you prefer one of the bundles, and on the other side, you prefer the other bundle. And in each region, separated by those hyperplanes, then the buyer's preference order is fixed because the allocation doesn't change. The revenue is therefore a linear function of the prices of the items they buy. So here on the bottom right, I have a picture for the case of the coffee and the muffin for one bidder. If the prices are low, the bidder buys both. If the price of coffee increases, suddenly the buyer just buys a muffin. And similarly, the other way around, if the price of the muffin increases enough, suddenly the bidder buys just the coffee. And then there's this 45-degree angle in between. And then there's a rectangle up at the top right where the buyer buys nothing, where both items are too expensive for him. All right, so that's the first example. And now you can just plug the number of dimensions and the number of hyperplanes into the general formula and get the number of samples needed. Now you might worry that there's this exponential term 2 to the power of items, but recall that we can take the log of this. So if you go back to this equation, here we have t, and we are taking the natural log of t. So if we take a log of exponential, we're no longer in exponential land. All right, so a small number of samples suffices. Second example is 2-part tariffs. 2-part tariffs are a standard mechanism in economics. Now we're talking about single item, multi-unit, multi-buyer 2-part tariffs. There are multiple units of an item for sale. The seller sets an upfront fee, P0, and a fee per unit, P1. And if a buyer buys K units, she pays P0 plus K times P1. Overall, the seller offers a menu of multiple different 2-part tariffs, L of them, and in each one you have an upfront fee and a fee per unit. Then the buyer chooses the tariff, in other words, which row of these L rows of the tariff menu he wants, and a number of units to buy that maximizes his utility. What's the sample complexity? Well, now the number of dimensions is 2L because there are L rows in the table and each row has 2 numbers, the fixed price and the variable price. And what's the number of hyperplanes? Well, again, there are number of buyers, and now there are L times units, choose 2 of these different choices between the pairwise choices, because each bidder is choosing the row from L and how many units to buy within that row. And for each pair, let's say for row 17, 20 units, and row 2, 90 units, that would be a pair. There's a hyperplane that defines when they're indifferent between those 2 choices. So this is, again, just the number of hyperplanes. So, and again, we can take the natural logarithm of this to get the number of samples needed by our theorem. The next example is randomized mechanisms. If you're not familiar with mechanism design, you might wonder, why do you ever want randomized mechanisms? But they can give you higher expected value of the objective. Here we're going to talk about multi-item lotteries for one additive buyer. And this generalizes easily to multiple unit demand or additive buyers, as we show in the paper, but I'm going to skip that in the talk. Here, a lottery is represented by a vector of thetas, number of items of them, and a price P. And the meaning is that if a buyer buys the lottery, he pays P and receives each item I with probability theta I. The expected utility, therefore, is the sum over the items of his value of the item times the probability that he gets the item minus the price that he has to pay for that lottery. The seller again offers a menu of L lotteries, so you can think about these as rows in a table. And the buyer chooses an expected utility maximizing lottery, which could be the empty lottery where all of the thetas are 0. This also has been studied extensively in the Econ CS literature. Now, the number of dimensions here is the number of items times L, because for each row, we have the number of items probabilities, and there are L rows in the table. And the number of hyperplanes is quadratic. All right, so those were simple examples, kind of with classical mechanisms, and now we're going to move to these more advanced mechanisms. With the same theorem, we showed that for affine maximizer auctions, the number of samples needed is number of O tilde number of bidders to the number of items plus 1 times items. For virtual valuation combinatorial auctions, it's a little less, as you would suspect, because the parameter space is a little smaller, but it is still exponential in items. Then in mixed bundling auction with reserves, it is just the number of items squared. So now we have come down from the exponential number of samples needed to a polynomial number of samples. And mixed bundle auctions themselves, it's just a constant number of samples. So what's a mixed bundling auction? A mixed bundling auction is one where you either sell all of the items separately or you sell them together, and you give a boost to allocations where they're sold together of a constant value C. And mixed bundling auction with reserves is just like that, except that in addition, you have reserve prices for the individual items. We have also additional applications of the same general theorem, like multi-item, multi-unit, nonlinear pricing mechanisms, and what's known as lambda auctions. These are like affine maximizer auctions, but without the W terms. And I'm going to skip these in the interest of time. Now let me move to finer grained hierarchies. So if you go back here, we had this hierarchy of 4 different auction mechanisms from more general to less general. And we can actually make finer grained hierarchies as well. And here's one hierarchy that we defined, which is k-sparse AMAs. That just means that these are affine maximizer auctions where only k allocations are boosted. The rest of the lambdas are zeros. And there's actually 2 variants of this. One where somebody external tells you which k you can boost, and the other where you get to decide which k you want to boost. And basically the same results, analogous results apply for both. So now we have this fine-grained hierarchy where we have 1 sparse AMAs being a subset of 2 sparse, being a subset of 3 sparse, and so on. All right. Now the error that you get here in terms of empirical revenue on the samples minus expected revenue on the real distribution D that you don't know, that is upper bounded by O tilde U times the square root of bidders plus K divided by the number of samples. And what's U? That is the maximum profit achievable by the mechanisms in the class over the support of D. So if you got a lucky draw from your prior. Okay. Now, if you look at this carefully, increasing K means that you get looser bounds because the right-hand side increases. On the other hand, increasing K gives a greater chance that the class contains a high revenue auction. So you're going to do better on the samples. So there's this trade-off now of revenue, or let's say mechanism design objective versus generalization. If you have a more flexible mechanism family, you're going to do better on the training set, but you might overfit and not generalize to reality. On the other hand, if you have too restricted of a mechanism class, you may not get high revenue at all because there is no high revenue mechanism in your family. So now we actually came up with a mechanism, a way to optimize, or a framework to optimize, if you like, this trade-off. So let's say again, we look at k-sparse affine maximizer auctions. We'll call them MK. Here, let's say that we are picking a mechanism that maximizes the empirical revenue on the samples over our family, minus O tilde, again, U, square root of bidders plus K over the number of samples. So if you like, you could think about that red term as a sort of regularizer, but it's a particular one. The blue part increases with K and the red part decreases with K. So there's typically an interior maximum, and that is the complexity of the mechanism that we want given the number of samples we have. So let K star be the optimal AMA sparsity level from that argmax. Then the revenue is within O tilde O square root of bidders plus K star over the number of samples of the optimal AMA's revenue. So this is saying that this is the right way to strike this trade-off between getting good revenue on the sample with a high flexibility mechanism and avoiding overfitting with a low complexity mechanism. Okay, so now if you don't care about auctions, you will like the fact that the same theorem also applies to other settings. And here I'm going to talk about voting and redistribution. So if you know mechanism design, you know that you can use the Clark tax mechanism, which is basically just like the VCG mechanism, but applied to voting to get the welfare maximizing outcome and to get truth-telling, exposed, and participation. Now, the problem with the Clark tax mechanism is that it collects extra revenue. It's not budget balanced. You end up collecting taxes from the voters and you have to burn those monies. You cannot redistribute them entirely. There's actually a theorem that says that. So now the question is that if I wanted to not ignore money burning as a loss, I want to take that into account, and I want to maximize expected unweighted social welfare. What kind of mechanism should I use? And there's been a lot of work on this question. Here, we're going to use the same framework that we just have to use samples from the prior to be able to say what we should do. And we'll study a class of mechanisms called neutral affine maximizers. And these are, again, incentive compatible, and they are also budget balanced. Here we have n parameters on them, one per agent, and you can think of them as weights on the agents. We call them mu's, mu1 for bidder 1, mu2 for bidder 2, and so on. And these are positive or 0. We'll also, in this family, assume that at least one agent is assigned a weight of 0 for reasons that become clear in a second. And the social choice function is just the weighted sum of the bidder's values. We want to pick an outcome that maximizes the weighted sum of the bidder's declared values for the different outcomes. All right, so now what is the payment? Well, if a bidder's weight is not 0, so mu is not 0, it is just like in the Clark tax mechanism. We're basically looking at how much value does he take away from the others. If his weight is 0 and he is the lowest index agent with weight 0, then he takes all of the extra money that was collected from the others. And other than that, his payment is 0. All right, then what we did based on samples of valuations, we find the weights mu I in order to maximize the expected unweighted social welfare. And now again, you can apply the same theorem to determine how many samples from the prior you can use, you need. And there's actually some fun experiments on the paper as well on a joke data set, if you like jokes. All right, now let me take a little detour for one slide to algorithm design instead of mechanism design, and then I'll come back. So the same general theorem actually applies to algorithm configuration and gives generalization guarantees just the same way. We have applied this to, for example, integer programming. We have applied it to determining how to generate branching heuristics so that you get fast runtimes due to small search trees. And we have recently also developed similar theory for cutting planes. And branching heuristics and cutting planes are the top two things that affect the speed of integer programming. Now, integer programming is an example of an application area of this, where we are trying to minimize runtime. We're trying to get the algorithm to run as fast as possible, while the algorithm itself always finds an optimal solution. Another kind of application is one where the algorithm's parameters determine solution quality, not just runtime. And as an example of that, we have worked on linkage-based clustering. In linkage-based clustering, you start from all of the items being separate, and you start clustering them based on certain distance metrics, and different distance metrics lead to different clusterings. And we're learning good distance metrics with this same approach, with these same generalization guarantees. A third example, and this is kind of interesting as well, is various sequencing problems in biology that we did as an example of a third application class where we are learning a surrogate objective. Here, performance is measured as similarity between the algorithm's output and a ground truth solution. The ground truth is discovered, for example, using wet lab experiments in biological sequencing problems, so it is only available for the instances in the training set. Then the algorithm, for example, a sequencing algorithm, maximizes a parameterized surrogate objective function, and that's a standard thing to do. What we do on top of that, we learn coefficients for that surrogate objective to make the algorithm do well on the real unknown problem, again with the same kind of backlearning guarantees. We also developed an algorithm for data-dependent discretization of continuous parameter space. And this is important because we had shown before that any data-independent discretization can perform extremely poorly. And two uses for this: one is that you can generate a portfolio of algorithms from which you then decide on a per instance basis which one to run. To get the discrete portfolio, you need to do this kind of discretization, or you can use this discretization as an input to any algorithm configuration tool that assumes a finite set of candidate parameter vectors, for example, the tools by Kleinberg et al. And Weiss et al. We have also done work on approximating the performance surface with a small number of constant pieces. So if you allow a little bit of error within your regions, you can get away with a much smaller number of pieces, and therefore a lot less samples. And we provide the first generalization guarantees for portfolio-based algorithm selection. There are really two pieces. One is that you have to learn the portfolio. What are your candidate algorithms from this infinite set? And then on a per instance basis, you select an algorithm from the portfolio to run. And we do this end-to-end guarantee of this backlearning. All right, now let's get back from the sidetrack to the main track. Now, let's talk about algorithms for mechanism design. So far, we talked about generalization guarantees, and they apply to optimal as well as suboptimal mechanism design algorithms. Algorithms for affine maximizer auctions and subclasses. This is some of our older work. They use samples as input, as we discussed. And then we had two different kinds of algorithm families. One was based on iteratively refined grid search, where every point in the grid is evaluated by running the mechanism on the samples. And the other is gradient descent algorithms of various kinds, some accelerated by economic insights. And again, each point during the search is evaluated on the samples that were drawn from the prior. And these are all anytime algorithms. They can be started from the best known mechanism, such as the VCG. So they guarantee that you get at least the standard revenue you would get from the VCG, and it only goes up from there. Now, let me move to some newer work on learning for mechanisms. We give algorithms for two-part tariffs, and we give an order n cubed, k cubed algorithm to find the two-part tariff for selling k units to a single buyer that maximizes empirical revenue over n samples. And it dramatically beats using a MIP formulation with Groby. For example, with k is 5 and n is 600, we take 23 minutes and Groby takes 3.5 hours. We also given an algorithm for optimizing a menu of two-part tariffs with runtime nk to the OL, where L is again the menu length. So it's only exponential in the menu length, which is in practice typically a small constant like 2 or 3. And we have also looked at market segmentation in this context, where you have extra information coming in about the bidders, for example, what state they're from and things like that. And there we show that it's computationally intractable to maximize empirical revenue even in very simple settings, and we can circumvent the intractability to find approximately optimal solutions when bidders are IID. Now let me move to a bit of a different model, some recent work, which is learning within an instance. So far we were learning for a distribution. Now we're trying to learn within an instance. And it sounds a little bit like magic, of course. And let's talk about auction design first. We have a new general technique for prior free multi-item multi-bidder revenue maximization, and it combines ideas from the previous random sampling mechanisms for unlimited supply and this recent sample complexity work that I've been talking about in this talk so far. The learning within an instance mechanism works as follows. You draw a participatory set of bidders that you're going to actually draw revenue from, and then you perform repeated sampling from the remaining bidders to learn a high revenue auction for them, and then you run that auction on the participatory bidders. And this yields stronger guarantees that apply without assumptions on valuation functions. And there are some additional results there, which let me skip them in the interest of time. And a new paper on preserving revenue in a shrinking market. The motivation is like cable cutters or things like that in dying industries. How do you preserve revenue as much as you can? The model is that you have some set of bidders and the next day only some of them show up. You don't know who's going to show up anymore. And here's how the mechanism works. We have a fixed set of bidders and the seller knows it. But in the next day, they only show up with probability P to construct a smaller set of bidders S prime. So how much revenue can the seller guarantee? And here we're looking at an allocational auction, which is more general. So the bidders' values can depend not only what they get, but also what items other bidders get. We show that the loss can be drastic. It can be P to the items. P is the probability that each one of them shows up the next day, to the power of items divided by 2 times the revenue of the VCG. So if, say, with 100 items and 90% chance for each bidder to come back, you get only 0.5% of the VCG revenue, which is very low. But under natural assumptions on the valuations, for example, gross substitutes, we get a reasonable revenue guarantee of revenue preservation, roughly P squared of the welfare. And again, we provide an algorithm for learning from samples on an auction that is robust to market shrinkage. Now, let me move to the last topic in one slide. This is kind of a different question. We're not optimizing the mechanism here, but we're using the same type of sample complexity results. We're estimating how incentive compatible a mechanism is. When we do mechanism design, or when people do mechanism design, we usually talk about designing incentive compatible mechanisms where everybody's motivated to tell the truth. However, most mechanisms that are run in the real world are not like that. People's incentives are not aligned with the truth, and they're better off lying. And we would like to know how incentive compatible a mechanism is. So our goal is to estimate how far a manipulable mechanism is from incentive compatibility using samples again from the agent's unknown type distribution. So the incentive compatibility, how incentive compatible a mechanism is, depends on the type distribution, but in these complex settings, as before, it's unrealistic that we would actually be given those type distributions. So what if we just have samples of them? How many samples do we need? And our estimate is the maximum utility an agent can gain by misreporting her type on average over the samples if the true reported types come from a finite subset of type space. So we only have to check the lies from truth to a reported type in a finite set of cases, and yet we can get in a pack learning sense these guarantees of manipulability or close to non-manipulability, how close we are to non-manipulable in the infinite space. All right, let me conclude. I presented a general theorem for sample complexity of algorithm configuration and mechanism design. Same theorem applies, and it applies to any objective, not just revenue maximization and not just welfare maximization, and it can be basically used in any setting. This is a myriad of mechanism design applications. We talked about pricing mechanisms, menus of two-part tariffs, auctions, both single item and multi-item, randomized mechanisms, voting, redistribution, and so on. And the voting and redistribution is particularly interesting because there's an impossibility result that you cannot get efficiency maximization there if you take money burning into account as a bad thing, like you should. We talked about how do you find the optimal mechanism in a hierarchy of mechanisms where very flexible mechanisms match get high revenue on the training data, but they might overfit. So there's actually an interior optimum. We talked about a new direction, which is learning within an instance for mechanism design, both for auctions and revenue preservation. And finally, we talked about estimating approximate incentive compatibility with a finite number of samples. All right, let me end there. Thank you.
Let's thank Tuomas for the wonderful talk, which covers the general set of techniques of mechanism design using ideas from machine learning and pack learning to learn from samples. And that's to me a very nice idea because my research is in statistical machine learning. So a lot of these stuff sounds at home to me. Are there any questions from the audience? Please type them in the Q&A. I'll start the Q&A session with one of my own questions. Yeah, I do have a lot of questions, but for the interest of time, I'll just ask one. Yeah, so back to the idea of so Tuomas, back to the idea of using machine learning to learn the rule of the game. So that's what mechanism design is about. And you are relying on samples from like bidders who give you valuations of different items, multiple bags of items, and so on. And my question is that wouldn't the valuations of these items in some sense depend on what the rule of the games are? Like suppose they're aware of the rule of the game, like would the distribution change, and how would that affect the learning-based result like at the end of the day?
Yes, thank you. Absolutely, and this is kind of the point that I made here of what this is not. So the samples are not the bids, because you're exactly right that if the samples are the bids, and you're designing the mechanism rules based on the bids, you're going to mess up incentive compatibility in a huge way. Mm-hmm. So the samples are really, you could think of them as being anything other than the bids. And one of the things that they could be the mechanism designer's own knowledge. Like in sourcing, the sourcing team knows a lot of things. And it's the sourcing team's knowledge. And they might say, oh, it could be that that guy's value is this for this bundle, and that guy's value is that for that bundle. And here's one thing how the whole thing could be. And that would be one sample. Or it could be like this. Here's another sample. Or it could be like that, and here's another sample. So the samples in that case are coming from the sourcing team's view of the world.
I see. Yeah,
not from the bidders.
I see.
And the other example, the kind of use case, is where their bids from some previous auction, which can no longer be manipulated.
I see. Yeah. So for a slightly broader question, like as a theoretician, like I personally run into these issues all the time. Like I prove theorems and I come up with optimal algorithm for various different settings, and sometimes like these optimal algorithms that are minimax optimal or sometimes even per instance optimal, like did not actually turn out to work well in practical applications when we implement those algorithms in practice. And apparently you are a theoretical researcher and you are also a highly practical entrepreneur. How do you manage the gap between the two worlds and make your theoretical algorithm to work well and solve real life problems in practice? And what are some responsible machine learning considerations?
Okay, good. So that's kind of a meta question. Yeah. I think there's always a gap. The theory is rarely reality. But one of the things that I kind of advocate, I advocate actually strongly, is that it goes the other way. So it's not so much that we scratch our heads and make up problems in academia and then solve them and somehow they get applied to the real world. It's almost the other way around, that when we work in the trenches of real world applications, we see what are the technology gaps that need to be actually addressed before the academic literature starts to address them. And it's that kind of driving from the application side that brings these questions up. Like this whole idea of automated mechanism design was kind of started from that direction, that we thought it was silly for sourcing people to ignore all of the information they have as a first step of their mechanism design. And there's other examples like that too. Like, for example, people were thinking that winner determination in combinatorial auctions is the main bottleneck, but we saw that way before that, there's this bottleneck of actually determining your own valuations of what would you do with each one of these bundles if you got these bundles. Everyone might require solving an NP-complete planning problem and so on. So then we move to preference elicitation in combinatorial auctions and so on. So it's really leading your questions from applications, and that helps you at least get to the right kinds of questions. And maybe some of them will actually apply directly to the world, and maybe some of them will give more just insight. But I like how the automated mechanism design, that's one of those things where you can actually have direct real world impact instead of just insight that you bring into the real world.
Awesome. Yeah, it will be interesting to consider what are some of the different objective functions that one can optimize besides social welfare and the interplays between the different objective functions. For instance, those that we've talked about earlier today in this summit.
Yes, definitely.
For the interest
that's
of
kind
time,
of why I picked this topic. I kind of felt that, you know, there are so many different objectives that you might want to work on when you work on these AI for social good problems. And, you know, if you try to solve every one of them by hand, it's going to be a big, long road. While maybe with automation, you can actually get some acceleration into the process.
All right. Yeah, for the, thank you. Thank you, Tuomas. And for the interest of time, like I'll pass the mic to Marianne. And for those who still have like further questions for Tuomas, like please enter them in Q&A, and Tuomas can answer them in the chat directly. Yeah, we'll move to the next session of the summit.
Thank you
very much.
So much for this wonderful talk, and thank you, Yuxiang, for chairing this afternoon keynote section. So we're running towards the last session of today's summit, and the last one, I'm also super excited because it's covering a very important topic in AI and wildlife conservation. And there are 3 talks in this session, including Phebe, who's going to talk about machine learning and game theory for wildlife conservation. Douglas is going to talk about AI for oceans, and then Chandra will talk about where's the bear. And I'm also very happy to introduce the session chair, Marion Whitman, who is the executive director of UC Santa Barbara's Natural Reserve System. And with all that, Marion.
Thank you. Thank you very much for the opportunity. I'm glad to meet you all, and let me get started and introduce our first speaker. This is Professor Fang. Professor Fang is an assistant professor at the Institute of Software Research at Carnegie Mellon University, and her research lies in the field of artificial intelligence and multi-agent systems, focusing on computational game theory with applications. Excuse me, my window just changed. One moment. Pardon me, with applications to security and sustainability domains. Before joining CMU, she was a postdoctoral researcher at, I'm sorry, the screen changes are affecting my screen here.
Sorry about that.
Yep, no problem.
You want me to stop sharing?
Just give me one moment and I'll pull up my screen on another monitor. Thank you. Okay. Excuse me. Before joining CMU, she was a postdoctoral fellow at the Center for Research on Computation and Society at Harvard University. And she received her PhD from the Department of Computer Science at the University of Southern California in 2016. Her dissertation there was selected as a runner-up for the IFAAMAS 16 Victor Lesser Distinguished Dissertation Award. Her work on protecting moving targets with mobile resources has been deployed by the US Coast Guard for protecting the Staten Island Ferry in New York City since 2013. And her work on designing patrol strategies to combat illegal poaching has led to the deployment of the PAWS application, which we'll hear about from her here, in a conservation area in Southeast Asia for protecting tigers. Her work has won quite a few awards, including the Innovation Application Award at Innovation Applications of Artificial Intelligence, IAAI, in 2016, and the Outstanding Paper Award in Computational Sustainability track at the International Joint Conferences on Artificial Intelligence. So please join me in welcoming Professor Fang. Thank you.
Thank you, Marianne, for the very nice introduction. And thank you, everyone, for attending this talk. It is my great honor to get this opportunity to talk about my work on leveraging AI for wildlife conservation. And specifically, my work is focusing on integrating computational game theory and machine learning, and using these AI techniques to help tackle different societal challenges, including in security and safety, environmental sustainability, food security, and transportation. And of course, today we're going to focus on the environmental sustainability side, the wildlife conservation. Well, we rely on rangers to fight against poaching in the front line to stop the population drop of key species like tigers. And poachers set snares like to kind of capture the wildlife, and the rangers patrolling the protected areas to remove these snares like this. But the ranger resource is very limited. So how can we better protect wildlife using AI? For example, in Uganda, the lives of wildlife are actually threatened by the traps and snares placed by the poachers. Here are some photos of that. And conservation agencies send rangers to patrol in these areas and confiscate the snares. However, the cost of snare is extremely low. It could be like as low as like only $2 for one snare. And the ranger density can be as low as like one ranger per 100 square kilometers. So poaching remains to be a huge threat. And how to make the most out of the ranger patrol is a big challenge. And our first thought is to kind of apply our algorithm that we had done before for protecting the fairy that Marian mentioned to this anti-poaching problem. And then quickly we realized that there's a lot of new challenges in this problem, because as you can see, there are a lot of snares that can be placed in a year. It's just a repeated and frequent attack per se from the poachers. And therefore, the standard assumptions that typically people make in traditional game theory about perfect rationality about the human players is not going to work with this human poachers here. And therefore, in other words, the poachers in these domains are not perfectly rational, and that means we can actually exploit their bounded rationality when we're designing the patrol strategies. And this is why we decided to first try to tackle the problem from the machine learning perspective. We try to learn the behavior model of the poachers and try to suggest the rangers to go to the area that have a predicted high threat. So of course, this rely on the historical data, and we collaborate with Queen Elizabeth National Park. We chose Queen Elizabeth National Park and collaborate with Uganda Wildlife Authority and Wildlife Conservation Society. We used like 12 years of historical data collected during the patrols that ranger conducted. And using these data, we're aiming to predict a heat map where this heat kind of represent the probability of the poacher snaring or the probability of detecting the snares. And we divide this whole area in 1 kilometer and 1 kilometer grid. And for each grid cell, we try to construct data points and construct features from that are related to the patrol effort, as well as the geospatial features. So the patrol effort features would include current and previous patrol efforts, and the geospatial features might include, say, distance to the nearest river and village, and also the animal density and slope, because these are all factors that might impact the poacher's decision-making. And the key technical challenge in this problem is that we have very limited labeled data due to the lack of patrol resources. And furthermore, the data set is actually highly imbalanced. We have a lot more negative data comparing to the positive ones. And to deal with these challenges, we actually came up with a series of algorithms. And in one of the earlier versions, what we did is that we first used the geospatial features to cluster the area into small geoclusters using Gaussian mixture model. And then for each geocluster, we would check how much data we have. If we do have enough data, then we can use a data greedy approach like Markov random field. If we don't have a lot of data in that geocluster, we can use a baggings of decision trees to make the final prediction. And we can combine these two to get the final heat map. And to evaluate this algorithms, we send the rangers to 2 areas that are predicted to be poaching hotspots, but are not frequently patrolled before. And during these tests, the patrollers found many signs of human activities and successfully removed 1 row of elephant snares. And that means with our prediction, the rangers were able to patrol in a place that wouldn't have been patrolled. And we found areas where elephants could have been poached. And the hit rate, meaning the number of times that we found snares in a month, outperforms 91% of the historical months and is much higher than the historical average. And inspired by this success, we conducted an 8-month field test. And during these 8 months, the rangers are sent to 27 areas, and our machine learning model predict the areas to be high threat areas or low threat areas. There are 5 high threat areas and 22 low threat areas. And as you can see here, the catch per unit effort, meaning the number of snares being found per kilometer of walking in the high threat group is 10 times higher than that in the low threat group, and is also much higher than the historical average. And after this successful attempt, we kept improving the learning framework and brought the research to new sites. In northeastern China, we collaborated with the WWF and Huangnihe Forest Bureau. And since many of the geospatial features are not readily available, we directly extract these features from the satellite imagery. And this significantly reduces the workload of our collaborating site managers. And also we try to exploit the human experts' knowledge by asking them to provide rough estimates through some questionnaires. And we also improve the machine learning model by using an ensemble method and combines various base models like neural networks, Gaussian process, and so on and so forth. And finally, we got this predicted poaching threat for the area. And these technical improvements led to a 2-day field test in northeastern China in 2017, and we found 22 snares in just a single day. And even my collaborators were super surprised because they didn't expect this area to have snares before that test. And actually, this is me trying to remove the snare from the tree. I went on the field test together with my collaborators. And after that, more patrols are conducted in the winter of 2017 with 7 snares found. And in 2019, another 1-week field test was launched where we not only found 42 snares, but also encountered humans who are likely poachers 3 times. And now we're confident in predicting the poaching hotspots, but that's not enough yet. We also want to design patrol routes while taking into account how would the poachers behave. And we know that the poachers' behavior might change if we change our patrol strategy. So what we do is that we treat the learned model as a black box, which takes as input the current patrol effort vector, X, and outputs Y, which where the YI represent the probability of snaring or detecting at location I in the current time period. And we want to determine the value of Xi to maximize the sum of Yi, subject to the scheduling constraint that the patroller always starts from the patrol post and come back to the patrol post after, say, 6 hours of patrol. And we use a graph-based representation for the ranger strategy, use this time location graph to discretize the strategy space. And we also use a piecewise linear function to approximate the learned machine learning model. And with this, we can solve these optimization problems through building a mixed integer linear program. And this all sounds promising, and we indeed get some results. However, when we present this resulting patrol strategy to the site managers of a conservation site in Malaysia, they told us that these routes are infeasible in practice, and they invite us to go to Malaysia. And when we went there, we conducted an 8-hour trial patrol in the jungle. And from this firsthand experience, we learned that the terrain is so complex that we cannot simply tell the patroller to move from one grid cell to a neighboring grid cell. So we get back to the drawing board. We redesigned the patrol planning algorithm by first building a virtual street map for the conservation area based on the terrain information, and then compute the optimal patrol strategy. And the resulting strategy is now a probability distribution over the patrol routes that are compatible with the terrain. And this led to the field test in Malaysia, where multiple animal signs and human activity signs are found, indicating again that we have led the patrollers to the right direction. And the statistics on the number of signs found per kilometer of walking also lead to the same conclusion. So putting these elements together, we have our PAS framework, the protection system for wildlife security. It first learns the poacher behavior and then do the patrol planning with based on the model of the current terrain. And it suggests the patrol routes, and the rangers, as they execute the patrol routes, can collect more data to feed back into the system. And the PAS is now successfully integrated into SMART, which is a spatial monitoring and reporting tool that is supported by multiple global conservation agencies. And the SMART is actually used by more than 600 conservation sites worldwide. And some parks are already using it to predict poaching threats, and more field tests are on the way. And we're excited about all these successful field tests and deployment of it. But the test also, in turn, reveals a series of new research challenges. And in the past few years, we have been developing new AI techniques to tackle these challenges. So let me give a brief overview of these 3 challenges that we have tackled. The first one is that the site managers told us sometimes the rangers and poachers will react to real-time information they encountered during the patrol. Sometimes they found footprints, and then they may choose to chase the signs instead of sticking to the predetermined patrol route. And similarly, one can imagine that the poacher might choose to change their plan if they see the footprint of the rangers. And our previous problem formulation and solution are no longer suitable for this kind of problem, because now we need to consider the sequential decision-making of the agents, of the rangers and the poachers. So we modeled this problem as a Markov game in a grid world, where the poacher move in this area and trying to place a limited number of snares while avoiding being captured by the ranger. And the ranger can patrol in this area, and both the ranger and the poacher will leave footprints as they move, but they can only observe footprints that are left by that are in the cells that they visited or they locate. So it is computationally intractable to solve this problem using mathematical programming-based techniques, and we decided to develop new multi-agent reinforcement learning algorithms to find the strategy for the ranger. We first built a deep learning-based oracle to compute the ranger strategy against a poacher with known behavior model. And given such a heuristic poacher, we can train this deep Q network to represent the Q value for taking different actions at different game states. And indeed, the training results show that we can indeed find a reasonable patrol strategy for the ranger. However, the strategy is highly exploitable, because if you are the ranger, if you're the poacher in this case, and the audience here are all smart enough, you may find that the ranger always follow this fixed pattern, and this is undesirable because it lacks randomness. So what can we do? We leverage the so-called double oracle framework for solving large-scale zero-sum games, and the policy-space response oracles framework in the multi-agent reinforcement learning. We treat a deep Q network as a single action that can be taken by either the ranger or the poacher. And then our goal is to find a randomized strategy, which is a probability distribution over these multiple deep Q networks. And to do so, we can start with only two small sets of deep Q networks for the ranger and for the poacher separately. And each may contain only 2 or 3 Q networks, and we denote them as GD and GA here. And then we can compute a Nash equilibrium for using the current deep Q networks in the sets, and then train new networks that best responds to the other player's current equilibrium strategy. And these new deep Q networks will be added to the set, and we can go back to the equilibrium computation step. After several iterations, we can get a reasonable strategy for the players to use while being kind of taking into account the adversarial behavior. And we further enhance the learning algorithm by training in local modes at the beginning. Like each local mode can be viewed as a restricted environment. For example, in this local mode, we restrict the poacher to enter the grid from the upper left corner. And in this local mode, the poacher has to start to enter the grid from the lower right corner. And the training in this local modes is more efficient comparing to the global mode without any entry point restrictions. And we can train these agents in multiple local modes in parallel. In addition, we leverage the domain experts' knowledge to design some domain-specific heuristic strategies to warm up the whole iterative process for the equilibrium computation. So that's kind of how we deal with this real-time information challenge. We also worked on dealing with the coordination among UAVs and humans. In the interest of the time, I'm not going to go into the very details. Just want to mention that in some of the conservation sites, the rangers would use the so-called conservation drones to monitor the area, especially during the night, so that the rangers can sit in the truck and wait for the conservation drone to detect some poachers or rangers, and then they can take actions. And the first thing that we did here, again, is that we built a deep learning-based tool that can automatically detect the human and wildlife in the scene captured by the conservation drone. And of course, as you can see in this field test in Botswana, it does a reasonable job, but it's not perfect. So and in addition, the UAVs, although they can detect these poachers, they cannot capture the poachers. Only the rangers can go and stop the poaching activity. So we further developed a game model that allows the UAV to strategically send flashlight to deter the poachers when there's no ranger nearby, and also design a mathematical programming-based algorithm to compute the optimal strategy of UAVs and human rangers while taking into account the uncertainty in the deep learning-based detection tool. And this is an actual video of the poacher running away when they got deterred by the conservation drone here. And the last thing I want to mention is a community engagement. In many sites, we can leverage the local community in the anti-poaching efforts. The site managers told us that they would recruit informants from the local villagers, and those people would kind of report tips about the poachers' actions so that the ranger can take better actions. And in this case, the research problem is how should the ranger plan patrols with and without tips, and also how to recruit informants, if any. One challenge in this problem is that the informant's goal may not be always aligned with the defender. And this actually falls into the problem of mechanism design. The informants can choose what to tell, but can we incentivize the informants to tell the truth? And we developed several strategies for the defender to use. And we also showed that the revelation principle, which is a standard result in mechanism design, still holds in this area. That means it is possible to incentivize the rangers, the informants to always tell the truth. And also the optimal defense plan can be computed in polynomial time. In the experiments, we also found that if you give a little bit additional rewards to the informants, it can significantly increase the defender's utility. So it's kind of really good to get that. So to summarize, we developed the deep learning and deep reinforcement learning based algorithms and combined them with security game framework to help with the anti-poaching effort. We have launched successful 2 field tests, and we have the tools available to hundreds of sites worldwide. And there are a lot of problems similar to anti-poaching, like illegal logging, illegal mining, and overfishing. And these techniques might also be used in those problems too. There are new challenges. There are existing challenges that are not fully resolved yet, including how to learn from limited and imbalanced data, how to efficiently learn to solve large-scale games. So with that, I'll end here and happy to take questions.
Great. Thank you, Professor Fang. We will save the Q&A for the end of this session. So I'm going to move on to our introduce our next speaker now. But first, I just want to say what an exciting presentation and what an important piece for conservation. And I just love to see that poacher running away from your flashlight. I think that's a wonderful thing. Thank you for your work on that. I will turn to our second speaker now, Professor Douglas McCauley. Douglas McCauley is an associate professor here at UC Santa Barbara, and he's the director of the Benioff Ocean Initiative, which is an applied research center based at UCSB's Marine Science Institute. Professor McCauley is a Sloan Research Fellow in the Ocean Sciences and member of the World Economic Forum's Friends of Ocean Action. He has degrees in political science and biology from UC Berkeley and a PhD from biology at Stanford, and has also conducted postdoctoral research at Stanford, Princeton, and UC Berkeley. Research by Professor McCauley has been published in leading research journals such as Science, Nature, the Proceedings of the National Academy of Sciences, and has been featured in outlets such as the New York Times, BBC, Time, and US National Public Radio. Today, we'll hear from Professor McCauley about his case study research utilizing different types of AI for addressing challenges facing ocean health, including whale conservation, endangered species monitoring, white shark surveillance, and plastic pollution research. This offers a first sense of what can be achieved via partnership between experts in marine and computational sciences. With that, I'll turn it over to you, Professor McCauley. Thank you.
Thank you, Marianne. Very kind introduction. Wonderful. Great. Thank you, Marianne. And wow, what a wonderful presentation by Dr. Fang. Really exciting application for artificial intelligence for some of these tools for doing good on our planet. I'm going to keep the genre going of trying to apply these tools for conservation, for environmental management. The block of the planet that I think most about is the oceans, as Marianne mentioned. When I think of why I'm so excited and feel so privileged to be at UCSB, it's because so many different centers of excellence here, but certainly a lot of excellence in the marine sciences as well as in the computational sciences. I think of UCSB as being a place defined and of course, literally by our surroundings, by oceans, But I also think of it as a place that draws strength from drawing together expertise that is here on campus. And of course, that interdisciplinarity that I talk about here is the different ways that we've tried to marry marine science with computational problem-solving techniques. I should make clear that I am a marine scientist, so while we can go deep, as in deep into ocean science, I'll need to defer some colleagues that have helped us build a few of our tools to help us apply some of these AI techniques for problem solving in oceans. I run a Center of Applied Ocean Problem Solving within the Marine Science Institute at UCSB called the Benioff Ocean Initiative. We're essentially a group that's intended, broadly speaking, to try to take science and try to empower researchers to create replicable solutions for ocean health. Unfortunately, in the oceans domain, as is the case on land, there are lots of problems that we could pick from that are challenging ocean health. And then, of course, also because our own fate as humans is connected to the fate and health of the oceans. Much of what happens with the oceans will control both the health of the planet and the health of humanity. When we look out at the oceans, certainly when I look out at the oceans, I see a lot of change. And some of that change, I think, inspires us to get to work even faster than ever before. We've seen, of course, a history of change on land, a great amount of industrialization that has totally changed the nature by which we interact with the environment, by which we are ourselves affected by the environment. One might arguably say, and I think legitimately say that some of that change that took place on land happened before some of the change that we're now just beginning to see almost as a repeat in the oceans. We had, for example, a period of rapid industrialization, of course, as we're all aware, a couple hundred years ago on land, which really reshaped those relationships between people and planet. One might argue, I might argue, we see a similar kind of industrial evolution happening in our oceans today. Now, one thing that's fundamentally different about a marine industrial revolution, some might say the onset or introduction of the Anthropocene into the ocean, the introduction of all kinds of new human activities and new kinds of human industries, some of those you're having a look at here, is that this time around, this second planetary industrial revolution that's happening underwater is happening in a fundamentally different way, which is a key difference is that we can watch it actually as it transpires. We can watch these new kinds of industries move into the oceans, whether that's fishing or shipping or ocean mining, whether that's power generation or farming, aquaculture in the oceans. We can actually truly look down and see this advent of new industry and intersections between industry, different new kinds of marine industries. We also have new kinds of tools that help us gather all kinds of new data about how wildlife and ecosystems themselves are responding to this new increasing footprint of humanity in our oceans. As I said, we zoom back to the start of the Industrial Revolution on land, we simply didn't have this recourse to this very powerful data. And we now have this huge fire hose of data on human activity and on natural non-human activity in the oceans. But just like in any of your domains, this fire hose of data is only helpful if we can actually process out insights that help give us our marching orders for how to better manage this future of the oceans. And of course, that's where employing different suites of AI problem solving come to play. What I want to do is just very rapidly run through 4 different case studies, again, sharing these case studies from the vantage point of a practitioner, of a marine scientist and marine manager, that integrate in various different degrees of artificial intelligence. So the first is a case study with whales. So endangered whales face many threats. A top threat for whales on the west coast of the United States is collisions between endangered whales and ships. Ships do not like scenes like this, neither do whale scientists or ocean scientists myself. You can imagine when a ship rolls into port with its brand on the side of the ship and an endangered whale on the bow, that's no one wins. So shipping companies came together as an industry and said, surely ocean scientists must be able to create systems that help us detect some of these whales in the ocean, in these shipping lanes, to prevent the whales from being run over. Again, they don't want to run over the whales, and the whales themselves, of course, do not want to be run over. So we implemented this solution here using our laboratory right out front of UC Santa Barbara, the Santa Barbara Channel as our testing ground for this technology. It's a program called WhaleSafe, which integrates a couple different kinds of techniques. The first is actually a acoustic buoy, which is constantly listening for whales and processing insight from that acoustic data. We leverage the power of citizen scientists looking for whales and pull that into our WhaleSafe platform. And then we use remote sensing and modeling techniques that help us forecast where whales are present. All of that information comes into the WhaleSafe platform and then helps us send information that effectively answers that question that industry asks us to answer. When are whales located in this region? I want to just take one moment to dive a little bit deeper on the acoustic buoy. This was designed by collaborators at Woods Hole Oceanographic Institute because it's more legitimately uses some of the tools du jour today. The stand you're seeing on the back deck of the boat here about to be deployed into the ocean has a hydrophone that is constantly listening for all kinds of ocean noise and an onboard computer, which is then processing and filtering for specifically different kinds of whale calls. It can identify those whale calls to species. It then uses transmitters located on the top of the buoy that we're seeing here to send that information back to human analysts, which then confirm that those are indeed whale calls. We ingest this information, the acoustic data, with the other data feeds that I shared. It then is fed into a simple algorithm, which creates a kind of, if anyone's ever seen these Smokey the Bear ratings for fire risk, we do the same thing for whale risk. High, medium, low, very high whale risk. And then using other kinds of data science techniques, we can also track ships as they move through the same space and see if they actually slow down when we tell them there are whales present in this area. And we can give them report cards, which in fact give us a lot of really useful data and really useful in new kinds of communication about data to help avoid this problem of ship strikes. I want to jump from whales to plastic pollution to give another case study of how we're beginning on a journey of trying to combat what many people call a new kind of cancer to ocean health. This problem of plastics, a challenge to, of course, humans as we interface and draw food, resource, and well-being from the oceans, and then also a huge problem for wildlife in the seas themselves. In the course of the time that we'll be together here, in our session, this webinar, there'll be 1,000 tons of plastic that enter the ocean via rivers. Because rivers are these key conduits, almost arteries by which plastic pollution is being vectored from land into the oceans, we work a lot in rivers. I'm sharing here a landscape view of a project in the Benioff Ocean Initiative called the Clean Currents Coalition. It's a group in which we have partnered with 9 different communities in 9 different countries, all associated with 9 different community rivers in which they're using different kinds of technology. You can get a portrait of the diversity of technologies that are used to actually capture plastic pollution in rivers, stopping it before it gets to the ocean. Now, of course, we're all very eager to stop this plastic from getting into the ocean and creating all the challenges that mentioned a moment ago, but we're also really excited because this plastic pollution we see as data and is really powerful data for helping us gain insight as to how we can turn off the tap of plastic pollution entering the rivers in the first place and in effect move further upstream to put some of these very interventions out of business, which is our ultimate goal, not to need these kinds of interventions at all in rivers. Of course, as you can see here, there's a vast amount of plastic pollution that's captured, a vast amount of data that needs to be processed. The state of the art previously was to collect dumpster worths of this plastic pollution and debris and then have people work through it, trying to enumerate all of that plastic. This summer, trying to find a higher efficiency and higher accuracy method for trying to create and translate that plastic pollution into data. We had a grad student from computer science join us as an intern, CY Shu, to design a model to actually try to do identification of some of our core types of plastic that are coming up the conveyor belts on certain of these different interventions. The goal with this model is to, as I say, replace the manual feed of data that's now coming in from these teams that are working in these rivers to intercept plastic pollution. This is a dashboard on the Clean Currents Coalition website, which shares how much plastic is being captured in one team's effort. Again, all of this manual, but we're looking forward to the integration of AI to get higher efficiency, higher accuracy, higher temporal resolution data that can immediately be fed into this website, giving insight of how to turn off that tap of plastic. If you know it's primarily in a particular river, styrofoam cups, plastic bags, straws that are a problem, because the data gives you that insight. And you have the raw material to start conversations with policymakers or with industry to stop those styrofoam cups, plastic bags, or straws. Another example is our work using artificial intelligence to try to help promote endangered species conservation. I think everyone's aware that we have a host of endangered species, not only our tigers and elephants on land, but their analogs under the water. I sometimes think of this species you're looking at right now as the underwater version of a elephant or rhinoceros. This is a giant sea bass. It's one of California's most endangered fish. It's about the size of a vending machine. And there's surprisingly, despite the charisma, the size, the beauty of this fish, very little information about its ecology, its movement, the kinds of raw data inputs that would be helpful for thinking about designing management strategies to enhance the recovery of this endangered species. I should say it is truly a literally a critically endangered species, the same listing as you see, for example, for some rhinoceros populations. But we tried to collect some of this insight I mentioned on how it uses space, how it interacts with fishing, how it uses protected areas by catching these fish and putting electronic trackers and tags on them. As I said, this is a vending machine-sized fish, and we were deeply humbled by how powerful they are when we tried to actually fish for them and equip them with transmitters. At the end of the day, after some of these unsuccessful giant sea bass fishing trips, we're sort of scrolling through the internet, looking at fish that we didn't catch, and seeing that in fact, the internet was saturated with images for people like this diver that had captured images of these fish, and in fact, embedded in those images with some of the very data that we needed. This is just a mosaic of pictures that were scraped from the internet and entered in a project I can tell you about in a moment called Spotting Giant Sea Bass. We determined with the help of some UCSB undergraduates that these giant sea bass carry their own unique barcode, a spot pattern that doesn't change over the course of their lifespan. So with these thousands of images that are up there online, pulled them into this platform, began to do use of this a simple matching algorithm to try to identify one fish found in one location to a fish found in another location and fish found over different periods of time. Also created the platform in partnership with a group that engages citizen scientists so that we can get more of this data into our data set to be able to make smarter decisions, but also engage these citizen scientists in the story of the fish and in the journey of trying to do more science and protect this species more effectively. And a few years into the project, we're really excited by the mass of data and the insight we're already seeing. Over 1,000 different encounters logged in the Spotting Giant Sea Bass project coming in from over 100 different contributors. So we're getting both the good high-resolution information about conservation and engagement that we're seeking for in the project, and first insight into some of those questions about how far do they move, how do they interact with these protected areas, and what kinds of strategies based on this insight for how they use space and time might we implement to keep them around longer, or more importantly, increase their number in California. The last example I want to throw out there is an example using AI with sharks. I think we're often familiar with some of the challenges that come from being successful in conservation on land when it comes to human-wildlife conflict. That's perhaps frictional encounters with species like mountain lions or wolves on land and people. We do also have our mountain and wolf analogs in the ocean. Here in Santa Barbara, we've done a good job with a number of different axes for marine conservation, which has allowed sharks, and especially white sharks, to increase in number. This is my family actually out for an outing just off the coast from UC Santa Barbara, and that's a white shark there in the foreground. As you can imagine, as an ocean scientist, I'm thrilled to see a marine predator so key to stability and to health of ocean ecosystems so close to home in my own ocean backyard. But not everyone who uses the ocean is thrilled to encounter a white shark when they're out surfing whatever they're doing in the oceans. And it's our general philosophy that some of the friction that comes from human-wildlife interactions comes from a lack of understanding. The sort of lack of knowledge is fear is fueled by a lack of knowledge about these species. And if we can learn more about how many of them there are in a particular space, and when there are a lot and when there are not a lot of sharks, we think that we can help people make more informed decisions that still have them going into the oceans, falling in love with the oceans, doing sports in the oceans, and whatever it is that keeps them well connected to the oceans, keeping them safe, and then also having wins for wildlife conservation. This research program we call Shark Eye. In Shark Eye, we use the drone-based surveillance team to go and do surveys around some of our more populated beaches in Santa Barbara. We're doing this project in partnership with industry, with the Salesforce AI research team. We're pulling in insight about from that drone video about when sharks are spotted and transmitting insight to users that subscribe to this Shark Eye data service. Where we are right now with the project is having a operable model. We've actually been running and collecting data to train the model for the past several years. And then in the process of collecting that training data, we're also working on the community engagement piece. What you see here on the right of the screen is a dashboard tracking the ups and downs that I alluded to before of both large and small white sharks in our study beach location, and sharing that data openly on the website, first exercise in sharing shark data in such a fashion that's out there now to help build more of this harmonious coexistence between people and sharks in our local ocean. And the goal is to then bring the model completely into the workflow here, such that the insights from the video are automatically processed through the Salesforce algorithm, Einstein Vision, and then brought up directly onto the website and shared in the same fashion that we're sharing data now. So I might just wrap up here by saying that my goal was really just to share, again, from a user's perspective, really somebody who's searching to collaborate more with most of the folks on the call that are developing some of these tools, our own perspective on the kinds of problems that we want to solve, and our own experimentation and how we can actually pull in this insight to do problem solving. I'd say in the ocean space, it's in some ways a rather challenging time because so many threats are compounding and piling on top of one another, from these issues of pollution to issues with increased overfishing and new kinds of industry. And of course, we have the tidal wave of climate change bearing down on the oceans, but it's also a time where I find myself able to be more optimistic that we can build a healthier new Anthropocene ocean by harnessing the power of these new kinds of interdisciplinary collaborations and these new AI tools to effectively make the future come out better for both industry, people, and planet, or at least the 70% of the planet that is the oceans. Let me pause there. Thank you, Marianne.
Great. Thank you, Professor McCauley. What an exciting presentation. And it's really encouraging to hear, that industry and managers are open and embracing of these great tools that you're providing. And also your family is a wonderful set of happy field assistants to be so close to a white shark with you. So exciting and scary picture. But it's just really great to shine a light also on the nature of human and wildlife interactions, and that they don't always have to be conflicts either. So thank you very much. And so before I introduce our final speaker today, I just wanted to remind all the attendees out there that at the end, there's going to be a Q&A session for our three speakers. And please use the Q&A function down at the bottom of your screen to submit your questions. We would love to have them. With that, it is my honor to introduce our final speaker, Professor Chandra Krintz. Chandra is a professor of computer science, also here at UC Santa Barbara, and co-founder and chief scientist of AppScale Systems Incorporated. She joined UCSB faculty in 2001 after receiving her MS and PhD in computer science from UC San Diego. Chandra's led a number of different research projects that have advanced state-of-the-art programming and distributed systems in ways that performance and energy consumption and that ease development and deployment of software. Recently, her work has focused on intersection of IoT, cloud computing, and data analytics with applications in farming, ranching, and ecology. Chandra has advised over 60 undergraduate and graduate students and has published numerous research articles regarding the implementation of programming languages in a wide variety of venues. Chandra's efforts have been recognized with an NSF Career Award, the CRAW Anita Borg Early Career Award, the UCSB Academic Distinguished Teaching Award, and the 2015 UCSB Sustainability Champion. On top of all these honors, Dr. Krintz also serves on the UCSB Natural Reserve System Advisory Committee. Today, Professor Krintz will present on wildlife monitoring, which is essential to a wide range of scientific activities and societal interests. Specifically, digital photography provides an effective, non-intrusive way to monitor wildlife. It's safe, cost-effective, and accessible to people with a wide range of backgrounds. Professor Krintz today will present a hybrid cloud application that couples in situ edge systems with remote cloud computing systems to perform automatic and low-cost classification of images collected by trail cameras or camera traps, which has applications for scientists, management agencies, citizen scientists, and others. With that, please help me welcome Chandra Krintz.
Thank you so much, Marianne. Really inspiring talks before mine. I'm really honored to be part of this summit and this panel. I want to just also emphasize, like Douglas did, I am not advancing the state of the art in AI or machine learning or computer vision, but what my team and I tried to do is design new computer systems which bridge the gap between the application drivers, something that Dr. Sandholm spoke to us about earlier, and emerging AI, ML advances. If we can bring those into systems that are easily used and then tailor them to specific important societal problems, we believe we can expedite science on both the computer science side as well as on, in our case, in this talk, on the conservation science side. So today I'd like to tell you a bit about our project. It's called Where's the Bear? So as Marianne mentioned, what this focuses on is wildlife monitoring. This is of land animals. Now I have to distinguish myself after Douglas's talk, but this wildlife monitoring is used for a wide variety of purposes, including understanding the climate change impacts on health and well-being of animals and different species. It's used to extract patterns in activity of animals and to monitor changes in land use. Also, like Douglas mentioned, for the oceans, monitoring is extremely important to avoid dangerous human-animal encounters and overlap. It also is an opportunity for us to engage young people, people of all ages, in computer science and STEM to provide through educational experiences and actual participation through citizen science. So the way this is done is through digital photography. The digital photography, they're also called camera traps or trail cameras, trail cams. The technology behind these advances behind these technologies have really advanced in the last few years. The cost of these cameras has just gone through the floor. They're really accessible and available. They also have evolved such that they are increasingly autonomous. They can be solar powered to power the batteries. So if you put them out in the wild, you don't have to constantly be going back to change the batteries. They're much more rugged and durable. So if the wild animal is rubbing up against or stepping on or pooping on any of these cameras, the cameras can tolerate this and exist for very long periods of time now, many years. In fact, the camera itself is automatically activated. Basically from they're motion triggered. So something moves in front of the camera, the picture is taken, or a series of pictures are taken. They're very programmable. One issue with automatically activated images is when they're triggered by motion can be caused by animals, of course, and that's what we want, but they can also be triggered by movement in vegetation. So you'll find that wind and storms and just natural environmental action is causing the camera to be triggered. What you end up with is thousands of very large numbers of images that are empty. We call them empties, and they don't have any animals in them. Or when a camera is triggering a detection period, it'll take a lot of pictures from that series, and maybe, you know, there's not new information there. So you have a lot of repeats of some animals. And then lastly, there's a lot of our collaborators who are really just interested in a specific animal. And they, for example, they want to just study the bears. They don't want other animals. And so the empties and the other animals that we're collecting are not animals of interest in their science. And so they just get in the way. They just impede these researchers' ability to process these images and get to answering the questions from their science that they're pursuing. The other thing that I wanted to mention is that these cameras are increasingly capable. They are considered part of the Internet of Things, which is an emerging set of technologies that actually embed little computers into these camera systems. And these computers can do everything from process the images that itself. It can do communication with other cameras or other devices, and it can actually actuate or control systems, other cameras or systems in the area based on the data that they're taking in. So again, these cameras are extremely increasingly autonomous and capable, and really becoming very low cost, so highly available for lots of purposes now. The problem with the Internet of Things is that we are connecting things, ordinary objects in our environment, to the internet so that they can sense and actuate and control their surroundings. And typically what's going to happen is they're going to gather data in their surroundings, and they're going to transmit that to large warehouse size data centers and computers called cloud computing, called clouds. And that data is crunched on and processed and analyzed in the cloud. And then the actuation and control mechanisms or commands are sent back to the devices. And this works great for something like smart cities, where you have, wall power devices and high-end networking that's, readily available everywhere. However, and another problem is there's so many of these devices that we're connecting via the internet that the internet and the cloud are having trouble, or going to have trouble. We're not designed for this many devices. Whereas the cloud and the internet were designed for humans. 3.5 billion, about half of our population has internet access today. And we use the cloud and the internet, and it was designed for e-commerce and video streaming. Now we have these, close to 50 billion or 1 trillion devices that are going to be pushing data up to the cloud, and that's just extremely costly, time-consuming, energy-consuming, carbon footprint consuming. So we really need to find another way. The other problem is the places that we're working with for trail cams and these motion-triggered camera traps are wild. They're out in the middle of vast open spaces that are really hard to get to and hard to reach. And humans have, it's just really hard for them to get out there and manage these cameras. And so there is no internet out there. There's not even cellular out there in most of the places we work. So even if we wanted to connect these cameras to the internet and get all of the information, we couldn't do it in real time. And we couldn't do it in these remote areas. These remote areas are rough and rugged and harsh. And there's, you're going to need solar power. You may have some outbuildings with wired electricity and microwave networks like the one that we have here at the reserve that I work at. But this is few and far between and hard to use. The other problem is, even if we could, these cameras collect so many images so often that if we were to move all of this data to the cloud, have it be processed, and then get some information back, say to alert for poaching, as we heard about earlier, we want that to happen relatively quickly when the poachers are out there. But if we're collecting hundreds of thousands of images, it's going to take many hours for this network that we have. Is we can transfer about 1,000 images per hour. So our monthly images would take almost a month to get the image data back. So that's not going to work either. So our approach is different. Instead of moving all of the data to the cloud and then operating on it there, what we do is we take the cloud and we shrink it down and we move it and it's because it's just code, and code is tiny compared to the vast amounts of data that we're collecting via these devices. We move that to where closer to the devices, at the edge of the network, where the sensors are collecting their data, where actuation and control needs to happen. Okay, so we're moving a much smaller piece of which is the computation to the data instead of moving vast amounts of data to the computation. We call these the edge clouds. So Where's the Bear is really an edge cloud, the deployment. And what we have to study from a computer science perspective is, okay, now we're putting a small distributed system out in the middle of nowhere where there is no IT staff, where there is, very little connectivity, or in some cases even, available power. So how do we design these systems so that they're self-managing, they're autonomous, they're fault tolerant, so that they can continue to operate for years without manual intervention? How do we harden them so that they can be exposed to the elements, very hot weather, very cold weather, animals, and then how do we make it easy to use? And so our approach there is to say, okay, well, if lots of people can program and use services that these public clouds provide, like Microsoft and Amazon and Google, if we could take those services and make them work in the same way at the edge, then the use of the cloud is very familiar, is very similar to just using the public clouds. And so a goal of ours, and kind of unique to our approach, is to make these edge clouds compatible with the public cloud, their public cloud counterparts. And then lastly, as I said, we really want to be the bridge between the AI and ML advances that you all are participating in, today, and give you a platform that we can integrate those techniques to compare and contrast them, to give you access to real data, and then to give our scientists from ecology and conservation the opportunity to get the cutting edge research that's coming out of our academic computer and AI labs across the nation as soon as possible to bring those solutions to bear on their problems. And we have to do this in a way that this makes it look like this is an appliance. This computer system now has to be an appliance like your refrigerator. Open the door and the light comes on. You feel it, put your hand in there, it's cold. That's all I know about my refrigerator. This cloud has to be completely autonomous and self-managing, just like our refrigerators today. And they've got to last for years on their own if these are to be successful, I believe, out in the wild. The other thing we do with Where's the Bear is that we want to be able to do as much as possible on this edge system near the cameras. We don't want to transmit images that are empty. We don't want to transmit images that aren't of interest to our collaborating researchers in ecology. We only want to get them the images they're interested in so that they can do their science. So what we do is we figure out what services. So for example, TensorFlow is a service from Google that works really well for image classification, amongst other things. It's open source, so we're able to move it to the edge near where the cameras are. The problem is that the edge clouds are resource constrained. They aren't as big or have as many resources as the clouds of Google and Amazon and Microsoft. So they're much smaller so that we can make them self-managing. At the same time, we want to be able to run some of these operations near the cameras. So training models turns out to be really expensive. And so we're going to have to rely on the public cloud for that. But we can do classification and object recognition at close to where the cameras are. So we decouple these two operations, and we're going to train our model in the public cloud. The problem with this is we got to ship thousands of images, tons of data in order to be able to produce a model that's going to be accurate and effective. And then we have to label all that data. So there's just the traditional problems with doing this type of classification is that there's a lot of, initial work that has to go on that just gets in the way of our collaborators doing their science. So we didn't want to do it this way. So we just wanted to try a different mechanism. And so on a whim, pretty much, we said, okay, what's the minimum we could transmit and develop a decent model? We rely on an existing model from ImageNet, of course, to build through transfer learning the models that are particular to this research reserve that we work at, Sedgwick. And what we did, instead of transmitting hundreds of thousands of images that we'd have to label, we just transmitted 250 empty images from the camera at different times of day, different times of the season. We put these empty images, we moved those, which only took 15 minutes to move pretty much. And then we would take images through an automated system by accessing just Google Images, requesting pictures of bear, deer, coyote, the animals of interest that our scientists were interested in. And we would then use some just very basic image processing to extract those animals. They're automatically labeled because we made the query to get the picture of the animal. And then we would do all kinds of different changes in illumination and size and rotations and orientations to place these animals on these images. And we created this huge, enormous, very fake data set in order to train our model. So this way we transferred literally barely nothing. And we have this model, and we wanted to see how good it would do on the Sedgwick images. We then would move the model, which is small, about 250K, tiny, like the code, to the edge cloud and use the open source TensorFlow to do the classification as the images came in from our cameras. So when the edge cloud would classify the images, then we would only forward exactly what the scientists wanted to their students, who were then doing their studies and asking their questions. And so we were able to do this filtering, really, so that we only transmitted what we needed to the scientists. And if we didn't have the internet connection, because we don't always have it, it's intermittent, it goes out a lot in this research reserve site. This would still all work by the researchers that were on site. You don't need an internet connection to use any of this. The edge cloud automatically creates a local network itself that interoperates in this way, and the Sedgwick researchers who are out there and all the directors can use the system to get real-time alerts and triggers, and to look at interesting images as they come in without even being connected to the outside world. And our results showed that we were able to save significant amounts of time, both in terms of the transfer delay that the researchers would have to wait, but also in the time it took for the researchers, actually their students, to classify, to actually go through the images themselves to pull out the pictures of interest. So about 70% of the bandwidth transfer delay, and researchers' time was saved. Many happy ecology and conservation science students because of this, who don't have to weed through thousands of empties or thousands of duplicate images. And the error rate, surprisingly, was very low. For coyote and bear, we had an error rate of 1%, and for deer, we had an error rate about 10%. Just the classifier itself, without any additional transfer learning, was on the order of 75 to 80% accuracy, so 20% error. So we were doing better just by doing this very simple, naive approach to training. In terms of what we're working on now, we did this work a few years ago. We're really interested in designing and developing systems that allow us to train at the edge, so that we could, do learning at the edge. We're interested in comparing and contrasting all kinds of different classifiers and new algorithms as they come online from researchers like you. The system advances that we focus on are things like, how can we do all of this even on the camera, not even on this edge cloud? Could we do a lot of the work at the camera itself? Or can we use multiple cameras to answer more interesting questions that our researchers pose? And could the cameras coordinate amongst themselves when they are triggered or when they sense that they have an animal of interest. We're also very interested in packaging this entire system so that it can be easily deployed and reused by other of the other reserves, other wild open spaces. There are hundreds of thousands of locations across the globe that where people are trying to use camera traps to do this type of classification. If we can make the system easier to use and automatically deployable, and being able to use it in a place where it's very remote and it's very rugged, it's very harsh conditions, then we think we can expedite the conservation that's going on today by avoiding all that learning curve and the expertise that you need. You almost have to be a computer scientist to be able to do some of these studies. Well, we want to eliminate that so that the ecologists and conservation science students don't have to get a computer science degree and an ecology degree. Lastly, some of the ecology questions that we're looking at going forward that I thought you might be interested in is counting animals. Could we do individual recognition of individuals, facial recognition for coyotes? A lot like Douglas was talking about, finding patterns in the coats of the animals, like the antlers of a deer. Could we identify the same individual over time at different cameras? We don't know yet. We also are interested in health and grazing patterns. We have some herds of cattle that are using the Cedric property, and we want to understand how it's affected the ecology there. We want to provide a tracking and alert system. We also have trouble with poachers, but also, of course, with invasive species, dogs, wild pigs. We also are interested in interacting with a lot of the forest fire initiatives that are going on campus and across our natural reserves and in California. So with that, I'll leave you with sort of a new approach to computer science. I think that we're spearheading here at UCSB. It's about computer science research that's really problem-driven and empirical, that's based on this multidisciplinary collaboration. We're driven by the problems of our scientists. We design the systems that we then can collaborate with AI and ML specialists to help design systems that we can get out and get used more quickly and sooner. And then we want to show that the systems that we're designing are easy to use, repeatable, they're demonstratable, and ready for use by others. And finally, we think it's a good way to engage students and the community in the science that's happening here at UCSB and its importance, because then when they're engaged, I think we have a nice pipeline for the future of this science and this research that we need to pursue. But I, of course, can't do any of it without an amazing team of students and collaborators, including the Natural Reserve System, for which Marianne is the director. And I thank them for the opportunity to work with them and on their reserves. And with that, I thank you for listening.
Wonderful. Thank you, Dr. Krintz. That was a really exciting talk. And as an ecologist myself, I can say that what you've talked about here, I think, will provide a revolutionary advancement for ecology. The ability to collect higher volume of data in the field, but not only do that, but to get it back to the desk is, I think, one of the biggest challenges. And this is not just for researchers, but management agencies too, and particularly in the context of the wildfires and other climate change impacts that we're feeling right now. The ability to really understand what our species populations are doing is behind the times. And I think that this is a really important piece of that. So thank you. I'm really excited by all of this, and I think it's great. With that, we're going to open it up to a Q&A session. Again, I would like to remind everybody out there to go ahead and submit your questions via the Q&A function, which is down at the bottom of your Zoom screen there. And so I'll wait for folks to bring some questions in, but in the meantime, I can offer a question to some of our panelists, unless any of our other panelists want to chime in. All right, I'll get started actually. And this first is a question for you, Dr. Krintz. And And I'm really, I was interested actually in the error rates that you reported, and that, deer have basically an order of magnitude higher error rate than coyote or bear. And what I was thinking about during your presentation was, how would this work for rare species as opposed to abundant species? Because both of those are of interest for obvious reasons, and for endangered species management or other kinds of land management. So can you talk a little bit more about why there's a difference in the error rate, and how you might envision this working for our rare species that we're trying to find, or our ubiquitous species that we're trying to kind of quantify maybe where they are or how they are?
Yeah, sure. Those are great questions. So first of all, the deer had a much higher error rate, primarily because when they came to these locations, which are primarily watering holes, they came in groups. And the computer vision techniques we were using were getting confused by having too many members. And I think that the latest advances, I haven't rerun this recently, but we're about to, will really bring that error rate down when we can identify the individuals and then classify those as whatever type of animal they are. Also, deer were really hard because they're very camouflaged. So as dusk comes, or as dawn comes, they really, even though we would have lots of pictures where there would be deer there, that we could identify, but it was so blended into the background that the algorithm could not see it. So those are the two big reasons for the deer population. One thing I want to say about the unique animal identification that's really important is that this kind of wacky, naive way of training using fake images, where we use pictures of coyote, for example, from the internet, and we overlay them with our empty backgrounds for the different camera locations, was really the only way we could capture coyote. We only, I think 600,000 images had only 22 examples of coyote, and that's way too small for these machine learning techniques to be able to have enough information to make a good classification. So I'm really excited about finding things that are rare. However, we have to know that they at least exist in the area so that we know how to create the training data set. If it's really something completely crazy like a kangaroo, that's going to be really hard for us to identify, and would only be triggered by some saying that a kangaroo is a cow, and we would catch that as being odd. But so I think there's a lot of good work to be done there. But I just want to say one last thing is the things that are really hard for this are really little animals, birds. And if we don't have lots of different angles of the body shots, the algorithms do really poorly. So we're working on all of that as we go forward. We have a lot of people interested in bird identification, but it's really hard without more advanced cameras. And I don't want to go there because they're expensive. So thank you for your question.
Sure. Just a quick follow-up on that. I was just going to say the same thing. As you know, there's so many enthusiastic birders out there, and this is not just in the research community, but in the public community, and that's a great thing for conservation. And not only are they good birders, but they're also photography enthusiasts too. And I know all about these data sources, but there's things like eBird, which are publicly accessible, and all of that too. And so at any rate, I really enjoy what you're doing, and I'm excited to see what comes next. So thank you very much. There's one more question for you from the audience, and I'll just read the question. This is from Evita Perón. And Evita asks, how can AI researchers help with training and identifying images at the edge?
So AI researchers are really important in this, and play a really important role in the design of these computer systems. We need to understand what resources a training mechanism needs. Does it need GPUs? Does it need some sort of weird other types of accelerators? Because we can design the systems, but we really need to be efficient so that we can quickly train. Also, this kind of incremental training or transfer learning, all of that is going to be, those advances are going to help a ton at the edge. And I do think that's the future. I think we have to train near where the data is so that we can do alerts and things like what Faye works on for poaching and identification of fires. And big groups of wild hogs. If we want to capture them, we have to know where they are immediately, not in a month. So thank you.
Exactly. Good question. Thank you. I have a question for Professor Fang as well. And again, Professor, I just want to say thank you for your exciting research in conservation. This is a really important area. And I had a question kind of about the limitations of enforcement and how you bring that into your thinking. And you identified that really well. And again, the technology that you're working on works on that too. But, when you've spoken with, the managers in Uganda or wherever it is that you're working, is there a point where enforcement, like a threshold, if you will, the number of people that are on the management team, that is a minimum requirement for being able to be effective with respect to some of the models that you're saying? So I guess what I mean to say is there a minimum number of employees or enforcement officers that have to be on the ground in order for you to be able to develop strategies for them that would be effective? I hope that makes sense.
Oh, yeah, sure. So definitely the number of ranger resources make a difference. When we do not have a lot of ranger resources, it is likely that we don't really need to employ game theoretic solution, mainly because the resource is so little, so that you can probably only focus on go to the locations that are predicted to be high poaching risk and then try to detect as many poaching activities as possible, confiscate the snares, because of the deterrence effect would mostly be revealed through the confiscation of snares instead of the presence of the rangers. If you have a lot of ranger resources, then maybe for some areas you can afford to visit that area very frequently, and your presence there is already a deterrence for the poachers. So that I think would be the main difference.
Mm-hmm. Yeah, very, very difficult problem to solve, for sure. Great. Do we have any more questions for our speakers? Wonderful. Okay, well, I believe that we will adjourn this session. I just wanted to thank everybody, Dr. Krintz and Dr. Fang and Dr. McCauley, for your excellent and exciting presentations. I know we at the Reserve System are excited to hear about your work, and thank you again.
Thank you all. Thank you all for organizing and hosting this.
Thank you. Thank you all the speakers, and thank you, Marion, for chairing the session. What a fascinating session that I certainly learned a lot. I was talking to Yushan. This is, the best, biodiversity session ever in, our AI and Machine Learning Summit. So I'm super excited about today's program, learned a lot throughout the day, and thank you everyone for joining us for today's CRML Summit. And again, I want to thank our sponsors, and I hope that in the future, we can all meet in person and continue the dialogue. So thank you for joining.